The preface to a short account of the history of mathematics by W. W. Rouse Ball, 1893. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King. http pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Preface. The subject matter of this book is a historical summary of the development of mathematics, illustrated by the lives and discoveries of those to whom the progress of the science is mainly due. The first edition was substantially a transcript of some lectures which I delivered in the year 1888 with the object of giving a sketch of the subject that should be intelligible to anyone acquainted with the elements of mathematics. In this edition I have revised the whole and have made some changes in detail, but the general character of the work as a popular account of the leading facts in the history of mathematics remains unaltered. The scheme of arrangement will be gathered from the table of contents at the end of this preface. Shortly, it is as follows. The first chapter contains a brief statement of what is known concerning the mathematics of the Egyptians and the Phoenicians. This is introductory to the history of mathematics under Greek influence. But as the Ionian Greeks were considerably indebted to the Egyptians and Phoenicians, it is convenient to commence with a concise account of the attainment of the latter. The subsequent history is divided into three periods. First, that under Greek influence, chapters 2 to 7. Second, that of the Middle Ages and Renaissance, chapters 8 to 13. And lastly, that of modern times, chapters 14 to 19. In discussing the mathematics of these periods, I have confined myself to giving the leading events of the history, and frequently have passed in silence over men or works whose influence was comparatively unimportant. Doubtless an exaggerated view of the discoveries of those mathematicians mentioned may be caused by non-allusion to minor writers who preceded and prepared the way for them, but in all historical sketches this is to some extent inevitable, and I have done my best to guard against it by interpolating remarks on the progress of the science at different times. Perhaps also I should here state that generally I have omitted all reference to practical astronomers unless there was some mathematical interest in the theories they proposed. In quoting results I have commonly made use of modern notation. The reader must therefore recollect that, while the matter is the same as that for any writer to whom allusion is made, his proof is sometimes translated into a more convenient and familiar language. I am of opinion that it is undesirable to overload a popular account with a mass of detailed references. Usually, therefore, I have collected in a single footnote for each school or mathematician references to the chief authorities on which I have based my account or with which I am acquainted. And I have not given the authority for every particular fact mentioned unless I regard it as difficult to verify without a definite reference. I hope that these footnotes will supply the means of studying in detail the history of mathematics at any specified period, should the reader desire to do so. The greater part of my account is a compilation from existing histories and memoirs, as indeed must necessarily be the case where the works discussed are so numerous and cover so much ground. When authorities disagree, I have generally stated only that view which seems to be the most probable. But if the question be one of importance, I believe that I have always indicated that there is a difference of opinion about it. I have struck out the long list of standard histories which I published in the first edition. Most of the facts and opinions for the first and second periods into which I have divided the history are quoted or criticized in the closely printed pages of M. Cantor's elaborate Vorlesungen über die Geschichte der Mathematik, to which the reader desires further information on any particular point would naturally turn. To that work H. Henkel's brilliant but fragmentary Geschichte der Mathematik, Leipzig, 1874, and in a lesser degree F. Hofer's Histoire de Mathématique, Paris, 3rd edition, 1886, and to M. Marie's Histoire des sciences de mathématiques et physique, 12 volumes, Paris, 1883 to 1888. I am usually indebted, when no specific reference is given. I frequently refer to these works by the names of the authors only. For the last 2 or 3 centuries, the general histories give but little assistance, and the student must rely mainly on special monographs. My thanks are due to various friends and correspondents who have called to my attention points in the first edition. No one who has not been engaged in such work can realize how difficult it is to settle many a small detail, or how persistently mistakes which have once got into print are reproduced in every subsequent account. I shall be grateful for notices of additions or corrections which may occur to any of my readers. W. W. Rousball, Trinity College, Cambridge, April 21st, 1893. This concludes the preface to the short account of the history of mathematics. A short account of the history of mathematics by W. W. Rousball. Chapter 1. Egyptian and Phoenician Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics, Chapter 1. Egyptian and Phoenician Mathematics. The history of mathematics cannot with certainty be traced back to any school or period before that of the Ionian Greeks, but the subsequent history may be divided into 3 periods, the distinctions between which are tolerably well marked. The first period is that of the history of mathematics under Greek influence. This is discussed in chapters 2 to 7. The second is that of the mathematics of the Middle Ages and the Renaissance, and this is discussed in chapters 8 to 13. The third is that of the modern mathematics, and this is discussed in chapters 14 to 19. Although the history commences with that of the Ionian schools, there is no doubt that those Greeks who first paid attention to mathematics were largely indebted to the previous investigations of the Egyptians and the Phoenicians. This chapter is accordingly devoted to a statement of what is known concerning the mathematical attainments of those races, but our acquaintance with the subject is so imperfect that the following notes must be regarded merely as a brief summary of the conclusions which seem to me most probable. The actual history of mathematics begins with the next chapter. On the subject of prehistoric mathematics, we may observe in the first place that, though all early races which have left records behind them knew something of numeration and mechanics, and though the majority were also acquainted with the elements of land surveying, yet the rules which they possessed were in general founded only in the results of observation and experiment, and were neither deduced from nor did they form part of any science. The fact, then, that various nations in the vicinity of Greece had reached a high state of civilization does not justify us in assuming that they had studied mathematics. The only races with whom the Greeks of Asia Minor, amongst whom our history begins, were likely to have come into frequent contact were those inhabiting the eastern littoral of the Mediterranean, and Greek tradition uniformly assigned the special development of geometry to the Egyptians, and that of the science of numbers either to the Egyptians or to the Phoenicians. I will consider these subjects separately. First, as to the science of numbers. So far as the acquirements of the Phoenicians on the subject are concerned, it is impossible to speak with any certainty. The magnitude of the commercial transactions of Tyre and Sidon must have necessitated a considerable development of arithmetic, to which it is probable the name of science might properly be applied. According to Strabo, the Tyrians paid particular attention to the sciences of numbers, navigation, and astronomy. They had, we know, considerable commerce with their neighbours and kinsmen the Chaldeans, and Bach says they regularly supplied the weights and measures used in Babylon. Now the Chaldeans had certainly paid some attention to arithmetic and geometry, as is shewn by their astronomical calculations, and whatever was the extent of their attainments in arithmetic, it's almost certain that the Phoenicians were equally proficient, while it is likely that the knowledge of the latter, such as it was communicated to the Greeks. On the whole, I am inclined to think that the early Greeks were largely indebted to the Phoenicians for their knowledge of practical arithmetic or the art of calculation. It is perhaps worthy of note that Pythagoras was a Phoenician, and according to Herodotus, but this is more doubtful. Thales was also of that race. Next, as to the arithmetic of the Egyptians. Their civilization, and in particular their astronomical calculations, have been generally accepted as implying that they were fairly proficient in the science of numbers. But about 25 years ago a hieratic papyrus forming part of the Rhind collection in the British Museum was deciphered, and this has thrown considerable light on the mathematical attainments of the Egyptians. The manuscript was written by a priest named Ahmes somewhere between the years 1700 BC and 1100 BC, and is believed to be itself a copy with emendations of an older treatise of about 3400 BC. The work is called Directions for Knowing All Dark Things and consists of a collection of problems in arithmetic and geometry. The answers are given, but in general not the process by which they are obtained. The first part deals with the reduction of fractions in the form of 2 divided by 2n plus 1 to a sum of fractions whose numerators are each unity. For example, Ahmes states 2 divided by 29 is a sum of 1 over 24, 1 over 58, 1 over 74, and 1 over 232. And 2 over 97 is a sum of 1 over 56, 1 over 679, and 1 over 776. In all examples, n is less than 50. Probably he had no rule for forming the component fractions, and the answers given represent the accumulated experiences of many previous writers. In one solitary case, however, he has indicated his method, for after having asserted that 2/3 is a sum of 1/2 plus 1/6, he adds that therefore 2/3 of 1/5 is equal to the sum of a half of a fifth and a sixth of a fifth, that is 1 over 10 plus 1 over 30. The next part of the book is devoted to examples in division and subtraction. Ahmes then proceeds to the solution of some simple numerical equations. For example, he says heap its seventh, its whole it makes 19, which means find a number such that the sum of it and 1/7 of it shall be together equal to 19. And he gives us the answer 16 plus 1/2 plus 1 over 8, which is correct. The latter part of the book contains various geometrical problems to which I allude later. He concludes the work with some arithmetico-algebraical questions, 2 of which deal with arithmetical progressions and seem to indicate that he knew how to sum such series. This appears to represent the most advanced arithmetic to which the Egyptians became acquainted. At any rate, it is all that they communicated to the Greeks. Throughout the work, Ahmes rarely explains the process by which he arrives at a result, but in one numerical example, where he requires to multiply a certain number, say a, by 13, he points out the method he has used. In this instance he first multiplied 2 and got 2a, and then he doubled the result and got 4a, and then he again doubled the result and got 8a, and lastly he added together a, 4a, and 8a, a process strictly analogous to what is now called practice. The arithmetical part of the papyrus indicates that Ahmes had some idea of algebraic symbols. The unknown quantity is always represented by the symbol which means a heap. Addition is represented by a pair of legs walking forwards, and subtraction by a pair of legs walking backwards or by a flight of arrows. and equality by the sign, one that looks like a less than or equal to sign which is upside down. As we shall see in the next chapters, the Greeks shewed no aptitude for algebra, and it was not until the development of mathematics passed again into the hands of members of a Semitic race that any considerable progress was made in the subject. A large part of Ahms's arithmetic is devoted to fractions. It may be noticed in passing that the treatment of fractions presented great difficulty to all early races. The Egyptians and Greeks reduced a fraction to the sum of several fractions, in each of which the numerator was unity, so that they had to consider only the various denominators. The sole exception to this rule being the fractions 2/3 and 3/4. This remained the Greek practice until the 6th century of our era. The Romans, on the other hand, generally kept the denominator constant and equal to 12, expressing the fraction approximately as so many twelfths. The Babylonians did the same in astronomy, except that they used 60 as the constant denominator, and from them, through the Greeks, the modern division of a degree into 60 equal parts is derived. Thus, in one way or the other, the difficulty of having to consider changes in both numerator and denominator was evaded. Before leaving the question of early arithmetic, I should mention that for practical purposes the almost universal use of the abacus or swan pan rendered it easy to add and subtract or even to multiply and divide without any knowledge of theoretical arithmetic. These instruments will be described later in chapter 7. It will be sufficient here to say that they afford a concrete way of representing a number in the decimal scale and enable the results of addition and subtraction to be obtained by a merely mechanical process. This, coupled with a means of representing the result in writing, was all that was required in primitive times. Second, as to the science of geometry. Geometry is supposed to have had its origin in land surveying, but while it is difficult to say when the study of numbers and calculation, some knowledge of which is essential in any civilized state, became a science, it is comparatively easy to distinguish between the abstract reasonings of geometry and the practical rules of land surveying. The principles of land surveying must have been understood from very early times, but the universal tradition of antiquity asserted that the origin of geometry must be sought in Egypt. That it was not indigenous to Greece and that it arose from the necessity of surveying is rendered the more probable by the derivation of the word from the earth and I measure. The Greek geometricians, as far as we can judge by their extant works, always dealt with the science as an abstract one. They sought for theorems which should be absolutely true, and would have argued that to measure quantities in terms of a unit, which might have been incommensurable with some of the magnitudes considered, would have made the results mere approximations to the truth. The name does not, therefore, refer to their practice. It is not, however, unlikely that it indicates the use which was made of geometry among the Egyptians from whom the Greeks learned it. This also agrees with the Greek traditions, which in themselves appear probable, for Herodotus states that the periodical inundations of the Nile, which swept away the landmarks in the valley of the river and by altering its bed increased or decreased the taxable value of the adjoining lands, rendered a tolerably accurate system of surveying ground indispensable, and thus led to a systematic study of the subject by the priests. The Egyptians certainly studied geometry. A small piece of evidence which tends to shew that the Phoenicians and Jews had not paid much attention to it is to be found in the mistake made in 1 Kings chapter 7 verse 23 and 2 Chronicles chapter 4 verse 2, where it is stated that the circumference of a circle is 3 times its diameter. The Babylonians also assumed that pi was equal to 3. Assuming then that a knowledge of geometry was first derived by the Greeks from Egypt, we must next discuss the range and nature of Egyptian geometry. For any accurate amount of this, we have to rely on the Rhind papyrus mentioned above. This, as I have already stated, was probably a summary of the information which was familiar to the priests, and was not a book of research. At any rate, we have reason to believe that some time before the year 2000 BC, that is, some centuries before it was written, the following method of obtaining a right angle was used in laying out the ground plan of certain buildings. The Egyptians were, we know, very particular about the exact orientation of their temples, and they had therefore to obtain with accuracy a north and a south line, and also an east and a west line. By observing the points on the horizon where a star rose and set, and taking a plane midway between them, they could obtain a north and a south line. To get an east and a west line, which had to be drawn at right angles to this, certain professional rope fasteners were employed, who stretched a rope round three pegs, the two of them which were nearest together being fixed along the north and south line, so that the sides of the triangle formed were in the ratio 3:4:5. The angle opposite the longest side would then be a right angle. A similar method is constantly used at the present time by practical engineers. This property can be deduced as a particular case of Euclid 148, and there is reason to think that the Egyptians were acquainted with the results of this proposition and of Euclid 147 for triangles whose sides are in the ratio mentioned above. They must also, there is little doubt, have known that the latter proposition was true for an isosceles right-handed triangle, and that it is obvious if a floor be paved with tiles of that shape. But though these are interesting facts in the history of the Egyptian arts, we must not press them too far as shewing that geometry was then studied as a science. Our real knowledge of the nature of Egyptian geometry depends almost entirely on the Rhind papyrus, and therefore at the earliest does not go further back than the year 1700 BC. Ahmes commences that part of the papyrus which deals with geometry by giving several numerical instances of the contents of barns. Unluckily, we do not know what was the usual shape of an Egyptian barn. But where it is defined by three linear measurements, say a, b, and c, the answer is always given as if he had formed the expression a times b times open bracket c plus half c closed bracket. He next proceeds to find the areas of certain rectilineal figures, in some of which he is certainly wrong, and then to find the area of a circular field of diameter 12, no unit of length being mentioned. In the latter case he gives the area as open bracket d minus 1/9 d quantity squared, where d is the diameter of the circle. This is equivalent to taking 3.1604 as the value of pi, the actual value being very approximately 3.1416. Lastly, Ahmes gives some problems on pyramids. These long proved incapable of interpretation, but Cantor and Eisenlohr have shown that Ahmes was attempting to find by means of data obtained from the measurement of some of the external dimensions of a building the ratio of certain other dimensions which could not be directly measured. His process is equivalent to determining the trigonometrical ratios of certain angles. The data and the results given agree closely with the dimensions of some of the existing pyramids. It is noticeable that all the specimens of Egyptian geometry which we possess deal only with particular numerical problems and not with general theorems, and even if a result be stated as universally true, it was probably proved to be so only by a wide induction. We shall see later that Greek geometry was from its commencement deductive. There are reasons for thinking that Egyptian geometry and arithmetic made little or no progress subsequent to the date of Ahmes's work. And though for nearly 200 years after the time of Thales, Egypt was recognized by the Greeks as an important school for mathematics, it would seem that, almost from the foundation of the Ionian school, the Greeks outstripped their former teachers. It may be added that Ahmes's book gives us much that idea of Egyptian mathematicians which we should have gathered from statements about it by the various Greek and Latin authors, some of whom lived nearly 15 centuries later. Previous to its translation, it was commonly thought that these statements exaggerated the acquirements of the Egyptians, and its discovery must increase the weight to be attached to the testimony of these authorities. We know nothing of the applied mathematics, if there were any, of the Egyptians or Phoenicians. The astronomical attainments of the Egyptians and Chaldeans were no doubt considerable, though they were chiefly the results of observation. The Phoenicians are said to have confined themselves to studying what was required for navigation. Astronomy, however, lies outside of the range of this book. I do not like to conclude the chapter without a brief mention of the Chinese, since at one time it was asserted that they were familiar with the sciences of arithmetic, geometry, mechanics, optics, navigation, and astronomy nearly 3,000 years ago, and a few writers were inclined to suspect, for no evidence was forthcoming, that some knowledge of this learning had filtered across Asia to the west. It is indeed almost certain that the Chinese were then acquainted with several geometrical or rather architectural implements, such as the rule, square, compass, and level, with a few mechanical machines such as the wheel and axle, that they knew of the characteristic property of the magnetic needle, and were aware that astronomical events occurred in cycles. But the careful investigations of L.A. Seydiot have shewn that the Chinese of that time had made no serious attempt to classify or extend the few rules of arithmetic or geometry which they knew, or to explain the causes of the phenomenon with which they were acquainted. The idea that the Chinese had made considerable progress in theoretical mathematics seems to have been due to a misapprehension of the Jesuit missionaries who went to China in the 16th century. In the first place, they failed to distinguish between the original science of the Chinese and the views which they found prevalent on their arrival, the latter being found on the work and teaching of Arab missionaries who had come to China in the course of the 13th century, and while there introduced a knowledge of spherical trigonometry. In the second place, finding that one of the most important government departments was known as the Board of Mathematics, they supposed that its function was to promote and superintend mathematical studies in the empire. Its duties were really confined to the annual preparation of an almanac, the dates and predictions in which regulated many affairs both in public and domestic life. All extant specimens of this almanac are extraordinarily inaccurate and defective. The only geometrical theorem with which, as far as I am aware, the ancient Chinese were acquainted was that in certain cases, namely when the ratio of the sides was 345 or 1 root 2, the area of the square described on the hypotenuse of a right angled triangle is equal to the sum of the areas of the squares described on the sides. It is barely possible that a few geometrical theorems which can be demonstrated in the quasi-experimental way of superposition were also known to them. Their arithmetic was decimal in notation, but their knowledge seems to have been confined to the art of calculation by means of the swan pen and the power of expressing the results in writing. Our acquaintance with the early attainments of the Chinese, slight though it is more complete than in the case of most of their contemporaries. It is thus specially instructive, and serves to illustrate the fact that a nation may possess considerable skill in the applied arts, while they are almost entirely ignorant of the sciences on which those arts are founded. From the foregoing summary it will be seen that our knowledge of the mathematical attainments of those who preceded the Greeks is very limited, but we may reasonably infer that from one source or another the early Greeks learned as much mathematics as is contained or implied in the Rhind papyrus, and it is probable that they were not acquainted with much more. In the next 6 chapters I shall trace the development of mathematics under Greek influence. End of chapter 1. Chapter 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 2. The Ionian and Pythagorean Schools, 600 to 400 BC. First period, mathematics under Greek influence. This period begins with the teaching of Thales circa 600 BC and ends with the capture of Alexandria by the Mohammedans in or about 641 AD. The characteristic feature of this period is the development of geometry. It will be remembered that I commenced the last chapter by saying that the history of mathematics might be divided into 3 periods, namely that of mathematics under Greek influence, that of the mathematics of the Middle Ages and of the Renaissance, and lastly that of modern mathematics. The next 4 chapters, chapters 2, 3, 4, and 5, deal with the history of mathematics under Greek influence. To these it will be convenient to add one, chapter 6, on the Byzantine school, since through it the results of Greek mathematics were transmitted to Western Europe, and another, chapter 7, on the systems of numeration which were ultimately displaced by the system introduced by the Arabs. I should add that many of the dates mentioned in these chapters are not known with certainty and must be regarded as only approximately correct. Chapter 2. The Ionian and Pythagorean Schools, circa 600 BC to 400 BC. With the foundation of the Ionian and Pythagorean schools we emerge from the region of antiquarian research and conjecture into the light of history. The materials at our disposal for estimating the knowledge of the philosophers of these schools previous to about the year 430 BC are however very scanty. Not only have all but fragments of the different mathematical treatises then written been lost, but we possess no copies of the elaborate histories of mathematics written about 325 BC by Eudemus, who was a pupil of Aristotle, and Theophrastus respectively. Luckily Proclus, who about 450 AD wrote a commentary on Euclid's Elements, was familiar with the history of Eudemus and gives a summary of that part of it which dealt with geometry. We have also a fragment of the general view of mathematics written by Geminus about 50 BC, in which the methods of proof used by the early Greek geometricians are compared with those current at a later date. In addition to these general statements we have biographies of a few of the leading mathematicians and some scattered notes in various writers which allusions are made to the lives and works of others. The original authorities are criticized and discussed at length in the works mentioned in the footnote to the heading of the chapter. The Ionian School. Thales. The founder of the earliest Greek school of mathematics and philosophy was Thales, one of the 7 sages of Greece, who was born about 640 BC at Miletus and died in the same town at about 550 BC. The materials for an account of his life consist of little more than a few anecdotes which have been handed down by tradition. During the early part of his life he was engaged partly in commerce and partly in public affairs, and to judge by 2 stories that have been preserved he was then as distinguished for shrewdness in business and readiness in resource as he was subsequently celebrated in science. It was probably as a merchant that Thales first went to Egypt, but during his leisure there he studied astronomy and geometry. He was middle-aged when he returned to Miletus. He then seems to have abandoned business and public life and to have devoted himself to the study of philosophy and science, subjects which in the Ionian, Pythagorean, and perhaps the Athenian schools were inextricably involved. He continued to live at Miletus till his death circa 550 BC. His views on philosophy do not here concern us. We cannot form any exact idea as to how Thales presented his geometrical teaching. We infer, however, from Proclus that it consisted of a number of isolated propositions which were not arranged in a logical sequence, but that the proofs were deductive, so that the theorems were not a mere statement of induction from a large number of special instances, as probably was the case with the Egyptian geometricians. The deductive character which he thus gave to the science is his chief claim to distinction. The following comprise all the propositions that we can now, with reasonable probability, refer back to him. 1. The angles at the base of an isosceles triangle are equal. Euclid 1:5. Proclus seems to imply that this was proved by taking another exactly equal isosceles triangle, turning it over, and then superposing it on the first, a sort of experimental demonstration. 2. If two straight lines cut one another, the vertically opposite angles are equal. Euclid 1:15. Thales may have regarded this as obvious, for Proclus adds that Euclid was the first to give a strict proof of it. 3. A triangle is determined if its base and base angles be given. Cf. Euclid 126. Apparently this was applied to find the distance of a ship at sea, the base being a tower and the base angles being obtained by observation. 4. The sides of equiangular triangles are proportionals. Euclid 6:4, or perhaps rather Euclid 6:2. This is said to have been used by Thales when in Egypt to find the height of a pyramid. In a dialogue given by Plutarch, the speaker addressing Thales says, "Placing your stick at the end of the shadow of the pyramid, you make the sun's rays two triangles, and so proved that the height of the pyramid was the length of the stick as the shadow of the pyramid to the shadow of the stick." The king Amasis, who was present, is said to have been amazed by this application of abstract science, and the Egyptians seem to have been previously unacquainted with the theorem. 5. A circle is bisected by any diameter. This may have been enunciated by Thales, but it must have been recognized as obvious fact from the earliest times. 6. The angle in a semicircle is a right angle. Euclid 3:31. This appears to have been regarded as the most remarkable of the geometric achievements of Thales, and it is stated that on inscribing a right angled triangle in a circle he sacrificed an ox to the immortal gods. It is supposed that he proved the proposition by joining the center of the circle to the apex of the right angle, thus splitting the triangle into two isosceles triangles, and then applied the proposition above, proposition 1. If this be the correct account of his proof, he must have been aware that the sum of the angles of a right angled triangle is equal to the two right angles. It has been ingeniously suggested that the shape of the tiles used in paving floors may have afforded an experimental demonstration of the latter result, namely that the sum of the angles of a triangle is equal to the two right angles. We know from Eudemus that the first geometers proved the general property separately for three species of triangles, and it is not unlikely that they proved it thus. The area about a point can be filled by the angles of six equilateral triangles or tiles, hence the proposition is true for an equilateral triangle. Again, a rectangle, the sum of whose angles is four right angles, can be divided into two equal right angled triangles, hence the proposition is true for a right angled triangle, and it will be noticed that tiles of such a shape would give an ocular demonstration of this case. It would appear that this proof was given at first only in the case of isosceles right angled triangles, but probably it was extended later so as to cover any right angled triangle. Lastly, any triangle can be split into the sum of two right angled triangles by drawing a perpendicular from the biggest angle on the opposite side, and therefore again the proposition is true. The first of these proofs is evidently included into the last, but the early Greek geometers were timid about generalizing their proofs, and were afraid that any additional condition imposed on the triangle might vitiate the general result. Thales wrote on astronomy, and among his contemporaries was more famous as an astronomer than as a geometrician. It is said that one night when walking out he was looking so intently at the stars that he tumbled into a ditch, on which an old woman exclaimed, "How can you tell what's going on in the sky when you can't even see what's lying at your own feet?" An anecdote which was often quoted to illustrate the unpractical character of philosophers. Without going into astronomical details, it may be mentioned that he taught that a year contained 365 days and not, as was previously reckoned, 12 months of 30 days each. According to some recent critics he believed the earth to be a disk, but it seems to be more probable that he was aware that it was spherical. He explained the causes of the eclipses both of the sun and the moon, and it is well known that he predicted a solar eclipse which would take place on or about the time he foretold. The actual date was May 28, 585 BC. But through this prophecy and its fulfilment gave extraordinary prestige to his teaching, and secured him the name of one of the 7 sages of Greece. It is most likely that he only made use of one of the Egyptian or Chaldean registers, which stated that solar eclipses recur on intervals of 18 years and 11 days. Among the pupils of Thales were Anaximander, Mamercus, and Mandriatus. Of the last two mentioned we know next to nothing. Anaximander is better known. He was born in 611 BC and died in 545 BC, and succeeded Thales as the head of the school at Miletus. According to Suidas, he wrote a treatise on geometry in which tradition says he paid particular attention to the properties of spheres, and dwelt at length on the philosophical ideas involved in the concept of infinity in space and time. He constructed terrestrial and celestial globes. He is alleged to have introduced the use of style or gnomon into Greece. This, in principle, consisted only of a stick stuck upright in a horizontal piece of ground. It was originally used as a sundial, in which case it was placed at the centre of 3 concentric circles so that every 2 hours the end of its shadow passed from one circle to another. Such sundials have been found at Pompeii and Tusculum. It is said that he employed these styles to determine his meridian, presumably by marking the lines of shadow cast by the style at sunrise and sunset on the same day, and taking the plane bisecting the angle so formed. And thence, by observing the time of year when the noon altitude of the sun was greatest and least, he got the solstices. Thence, by taking half the sum of these noon altitudes of the sun at the 2 solstices, he found the inclination of the equator to the horizon, which determined the latitude of the place, and by taking half their difference he found the inclination of the ecliptic to the equator. There seems to be good reason to think that he did actually determine the latitude of Sparta, but it is more doubtful whether he really made the rest of these astronomical deductions. We need not here concern ourselves further with the successors of Thales. The school he established continued to flourish till about 400 BC, but as time went on its members occupied themselves more and more with philosophy and less with mathematics. We know very little of the mathematicians comprised in it, but they would have seemed to have devoted most of their attention to astronomy. They exercised but slight influence on the further advance of Greek mathematics, which was made almost entirely under the influence of the Pythagoreans, who not only immensely developed the science of geometry, but created a science of numbers. If Thales was the first to direct general attention to geometry, it was Pythagoras, says Proclus, quoting from Eudemus, who changed the study of geometry into the form of a liberal education, for he examined its principles to the bottom and investigated its theorems in an intellectual manner. And it is accordingly to Pythagoras that we must now direct attention. End of part 1 of chapter 2. Chapter 2, part 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 2. The Ionian and Pythagorean schools 600 BC to 400 BC. Part 2. The Pythagorean school. Pythagoras. Pythagoras was born at Samos about 569 BC, perhaps of Tyrian parents, and died in 500 BC. He was thus a contemporary of Thales. The details of his life are somewhat doubtful, but the following account is, I think, substantially correct. He studied first under Pherecydes of Syros, and then under Anaximander. By the latter he was recommended to go to Thebes, and there or at Memphis he spent some years. After leaving Egypt he travelled in Asia Minor, and then settled at Samos, where he gave lectures, but without much success. About 529 BC he migrated to Sicily with his mother, and with a single disciple who seems to have been the sole fruit of his labours at Samos. Thence he went to Tarentum, but very shortly moved to Croton, a Dorian colony in the south of Italy. Here the schools that he opened were crowded with an enthusiastic audience. Citizens of all ranks, especially those of the upper classes, attended, and even the women broke law which forbade their going to public meetings and flocked to hear him. Amongst his most attentive auditors was Theano, the young and beautiful daughter of his host Milo, who, in spite of the disparity of their ages, he married, and she wrote a biography of her husband, but unfortunately it is lost. Pythagoras was really a philosopher and moralist, but his philosophy and ethics, as we shall shortly see, rested on a mathematical basis. He divided those who attended his lectures into two classes: the listeners, or Pythagori, and the mathematicians, or Pythagoriki. In general, a listener, after passing 3 years as such, could be initiated into the second class, to whom alone were confided the chief discoveries of the school. Following the modern usage, I confine the use of the word Pythagoreans to the latter class. The Pythagoreans formed a brotherhood with all things in common, holding the same philosophical beliefs, engaged in the same pursuits, and bound by oath not to reveal the teaching or secrets of the school. Their food was simple, their discipline severe, and their mode of life arranged to encourage self-command, temperance, purity, and obedience. They rose before the sun, and began by recalling the events of the preceding day. Next they made a plan for the day then commencing, and finally, on retiring to rest, they were expected to compare their performances with this plan. One of the symbols which they used for purposes of recognition was the pentagram, sometimes also called the triple triangle. To tripono trigono. The pentagram is merely a regular reentrant pentagon. It was considered symbolical of health, and the angles were denoted by letters of the word Eveia, see below page 39. The diphthong ea being replaced by a theta, it will be noticed that it consists of a single broken line, a feature to which certain mystical importance was attached. Iamblichus, to whom we owe the disclosure of this symbol, tells us how a certain Pythagorean, while travelling, fell ill at a roadside inn where he had put up for the night. He was poor and sick, but the landlord, who was a kind-hearted fellow, nursed him carefully, and spared no trouble or expense to relieve his pains. However, in spite of all efforts, the student got worse. Feeling that he was dying, and unable to make the landlord any pecuniary recompense, he asked for a board on which he inscribed the pentagram star. This he gave to his host, begging him to hang it up outside so that all passers-by might see it, and assuring them that he would not regret his kindness as a symbol on it would ultimately shew. The scholar died and was honourably buried, and the board was duly exposed. After a considerable time had elapsed, a traveller one day riding by saw the sacred symbol. Dismounting, he entered the inn, and after hearing the story, handsomely remunerated the landlord. Such is the anecdote, which, if not true, is at least ben trovato. The majority of those who attended the lectures of Pythagoras were only listeners, but his philosophy was intended to colour the whole life, political and social, for all of his followers. In advocating self-control, government by the best men in the state, strict obedience to legally constituted authorities, and an appeal to eternal principles of right and wrong, he represented a view of society totally opposed to that of the democratic party of that time, and thus naturally most of the brotherhood were aristocrats. It had affiliated members in many of the neighbouring cities, and its method of organization and strict discipline gave it great political power, but like all secret societies it was an object of suspicion to those who did not belong to it. For a short time the Pythagoreans triumphed, but a popular revolt in 501 BC overturned the civil government, and in the riots that accompanied the insurrection the mob burnt the house of Milo, where the students lived, and killed many of the most prominent members of the school. Pythagoras himself escaped to Tarentum, and thence fled to Metapontum, where he was murdered in another popular outbreak in 500 BC. Though the Pythagoreans as a political society were thus rudely broken up and deprived of their head, they seem to have re-established themselves at once as a philosophical and mathematical society, having Tarentum as their headquarters. They continued to flourish for 100 or 150 years after the death of their founder, but they remained to the end a secret society, and were therefore ignorant of the details of their history. Pythagoras himself did not allow the use of textbooks, and the assumption of his school was not only that all their knowledge was held in common and secret from the outside world, but that the glory of any fresh discovery must be referred back to their founder. Thus Hippasus, circa 470 BC, is said to have been drowned for violating his oath by publicly boasting that he had added the dodecahedron to the number of regular solids enumerated by Pythagoras. Gradually, as the society became more scattered, it was found convenient to alter this rule, and treatises containing the substance of their teaching and doctrines were written. The first book of the kind was composed by Philolaus, circa 410 BC, and we are told that Plato contrived to buy a copy of it. We may say that, during the early part of the 5th century before Christ, the Pythagoreans were considerably in advance of their contemporaries, but by the end of that time their more prominent discoveries and doctrines had become known to the outside world, and the centre of intellectual activity was transferred to Athens. Though it is impossible to separate precisely the discoveries of Pythagoras himself from those of his school of a later date, we know from Proclus that it was Pythagoras who gave geometry that rigorous character of deduction which it still bears, and made it the foundation of a liberal education, and there is a good reason to believe that he was the first to arrange the leading propositions of the subject in a logical order. It was also, according to Aristoxenus, the glory of his school that raised the arithmetic above the needs of the merchants. It was their boast that they sought knowledge and not wealth, or in the language of one of their maxims, a figure and a step forwards, not a figure to gain 3 oboli. Pythagoras was primarily a moral reformer and practical philosopher, but his system of morality and philosophy was built on a mathematical foundation. In geometry, he himself probably knew and taught the substance of what is contained in the first 2 books of Euclid. and was acquainted with a few other isolated theorems, including some elementary propositions on irrational magnitudes, while his successors added several of the propositions in the 6th and 11th books of Euclid. But it is thought that many of his proofs were not rigorous, and in particular that the converse of a theorem was frequently assumed without a proof. What philosophical doctrines were based on these geometrical results is now only a matter of conjecture. In the theory of numbers he was concerned with 4 different kinds of problems, which dealt respectively with polygonal numbers, ratio and proportion, the factors of numbers, and numbers in series, but many of his arithmetical inquiries, and in particular the questions on polygonal numbers and proportion, were treated by geometrical methods. Knowing that measurement was essential to the accurate definition of form, Pythagoras thought that it was also to some extent the cause of form, and he therefore taught that the foundation of the theory of the universe was to be found in the science of numbers. He was confirmed in this opinion by discovering that the note sounded by a vibrating string depended, other things being the same, only on the length of the string, and in particular that the lengths which gave a note its fifth and its octave were in the ratio 1 to 2/3 to 1/2. This may have been the reason why music occupied so prominent a position in the exercises of his school. He also believed that the distances of the heavenly bodies from the earth formed a musical progression, hence the phrase the harmony of the spheres. Taking the science of numbers as the foundation of his philosophy, he went on to attribute the properties to numbers and geometrical figures. For example, the cause of color was the number 5. The origin of fire was to be found in the pyramid. A solid body was analogous to the tetrad, which represented matter as composed of the 4 primary elements fire, air, earth, water, and so on. The tetrad, like the pentagram, was a sacred symbol, and the initiate's oath ran, and I provide here a translation from the Greek not provided by the book, I swear by him that gave to our soul the tetractys, which contains the fount and root of our eternal nature. The philosophical views of Pythagoras do not further concern us, and I now proceed to discuss his work on mathematics in rather greater detail. The Pythagoreans began dividing the subjects with which they dealt into 4 divisions: numbers, absolute or arithmetic, numbers applied or music, magnitudes at rest or geometry, and magnitudes in motion or astronomy. This quadrivium was long considered as constituting the necessary and sufficient course of study for a liberal education. Here I confine myself to describing the Pythagorean treatment of geometry and arithmetic. First, as to their geometry. We are of course unable to reproduce the whole body of Pythagorean teaching on this subject, but we gather from the notes of Proclus on Euclid, and from a few stray remarks in other writers, that it included the following propositions, most of which are on the geometry of areas. 1. It commenced with a number of definitions, which probably were rather statements connecting mathematical ideas with philosophy than explanations of the terms used. One has been preserved in the definition of a point as unity having position. 2. The sum of the angles of a triangle was shewn to be equal to 2 right angles, and in the proof which has been preserved, the results of the propositions Euclid 1.13 and the first part of Euclid 1.29 are quoted. The demonstration is substantially the same as that in Euclid, and it is most likely that the proofs there given of the 2 propositions last mentioned are also due to Pythagoras himself. 3. Pythagoras certainly proved the properties of right angled triangles which are given in Euclid 1.47 and 1.48. We know that the proofs of these propositions which are found in Euclid were of Euclid's own invention, and a good deal of curiosity has been excited to discover what was the demonstration which was originally offered by Pythagoras of the first of these theorems. It would seem most likely to have been one of the following. Alpha. Any square ABCD can be split up as in Euclid 2:4 into two squares BD and DK and two equal rectangles AK and CK, that is, equal to the square on FK, the square on EK, and 4 times the triangle AEF. But if the points taken G on BC, H on CD, and E on DA, so that BG, CH, and DE are each equal to AF, it can be easily shewn that EFGH is a square, and that the triangles AEF, BFG, CGH, and DHE are equal, and thus the square ABCD is also equal to the square on EF and 4 times the triangle AEF. Hence the square on EF is equal to the sum of the squares on FK and EK. Beta. Let ABC be a right-angled triangle, A being the right angle. Draw AD perpendicular to BC. The triangles ABC and DBA are similar. Therefore, BC to AB is as AB to BD, and similarly BC to AC is equal to AC to DC. Hence, AB squared plus AC squared equals BC multiplied by the quantity BD plus DC, which equals BC squared. This proof requires a knowledge of the results of Euclid 2:2, 6:4, and 6:17, with all of which Pythagoras was acquainted. 4. Pythagoras is also credited with the discovery of theorems Euclid 144 and 145, with giving a solution of the problem of Euclid 2:14. It is said that on the discovery of the necessary construction for the problem last mentioned, he sacrificed an ox. But as his school had all things in common, the liberality was less striking than it seems at first. The Pythagoreans of a later date were aware of the extension given in Euclid 6:25, and Dr. Ullmann thinks that Pythagoras himself was acquainted with it, but this must be regarded as doubtful. It will be noticed that Euclid 2:14 is a geometrical solution of the equation x squared equals AB. 5. Pythagoras shewed that the plane about a point could be completely filled by equilateral triangles, by squares, or by regular hexagons, results that must have been familiar wherever tiles of these shapes were in common use. 6. The Pythagoreans were said to have solved the quadrature of the circle. They stated that the circle was the most beautiful of all plane figures. 7. They knew that there were 5 regular solids inscribable in a sphere, which was itself, they said, the most beautiful of all solids. 8. From their phraseology in the science of numbers and from other occasional remarks, it would seem that they were acquainted with the methods used in the 2nd and 5th books of Euclid, and knew something about irrational magnitudes. In particular, there is reason to believe that Pythagoras proved that the side and the diagonal of a square were incommensurable, and that it was this discovery which led the Greeks to banish the conceptions of number and measurement from their geometry. A proof of this proposition, which is not unlikely to be that due to Pythagoras, is given below. See page 61. Next, as to their theory of numbers. I have already remarked that in this the Pythagoreans were chiefly concerned with 1. Polygonal numbers, 2. The factors of numbers, 3. numbers which form a proportion, and 4. numbers in series. Pythagoras commenced his theory of arithmetic by dividing all numbers into even or odd, the odd numbers being termed nomons. An odd number such as 2n plus 1 was regarded as the difference of two square numbers, that is n plus 1 quantity squared, and n squared, and the sum of the nomons from 1 to 2n plus 1 was stated to be a square number, vis-a-vis n plus 1 quantity squared, and its square root was termed a side. Products of two numbers were called a plane, and if a product had no exact root it was termed an oblong. A product of three numbers was called a solid number, and if three numbers were equal, a cube. All of this has obvious reference to geometry, and the opinion was confirmed by Aristotle's remark that when a gnomon is put round a square, the figure remains a square, though it is increased in dimensions. Thus, in the annexed figure, which the gnomon AKC containing 11 small squares when put round the square AC containing 5 squared small squares makes a square HL containing 6 squared small squares. The number 2n squared plus 2n plus 1, the number 2n squared plus 2n, and the number 2n plus 1 possess special importance as representing the hypotenuse of two sides of a right-angled triangle. Cantor thinks that Pythagoras knew this fact before discovering the geometrical proposition Euclid 147. A more general expression for such numbers is m squared plus n squared, 2m times n, and m squared minus n squared. It will be noticed that the result obtained by Pythagoras can be deduced from these expressions by assuming m equals n plus 1. At a later time, Archytas and Plato gave rules which are equivalent to taking n equals 1. Diophantus knew the general rule. After this preliminary discussion, the Pythagoreans proceeded to the four special problems already alluded to. Pythagoras was himself acquainted with the triangular numbers, but probably not with any of the other polygonal numbers. The latter were discussed by later members of the school. A triangular number represents the sum of a number of counters laid in a row on a plane, the bottom row containing n and each succeeding row one less. It is therefore equal to the sum of the series n plus n minus 1 plus n minus 2 plus ... plus 2 plus 1. That is, to a half n multiplied by n plus 1. Thus the triangular number corresponding to 4 is 10. This is the explanation of the language of Pythagoras in the well-known passage in the Lucian where the merchant asks Pythagoras what he can teach him. Pythagoras replies, "I will teach you how to count." The merchant, "I know that already." Pythagoras, "How do you count?" Merchant, 1, 2, 3, 4. Pythagoras, "Stop! What you take to be 4 is 10, a perfect triangle, and our symbol." As to the work of the Pythagoreans on the factors of numbers we know very little. They classified numbers by comparing them with the sum of their integral factors, calling a number excessive, perfect, or defective, according as it was greater than, equal to, or less than the sum of these factors. These investigations led to no useful result. The third class of problems which they considered dealt with the numbers which formed a proportion. Presumably these were discussed with the aid of geometry and is done in the 5th book of Euclid. Lastly, the Pythagoreans were concerned with series of numbers in arithmetical, geometrical, harmonical, and musical progressions. The three progressions first mentioned are well known. 4 integers are said to be in musical progression when they are in the ratio a to 2ab over a plus b, half of a plus b to b, For example, 6, 8, 9, and 12 are in musical progression. After the death of Pythagoras, his teaching seems to have been carried on by Epicharmus and Hippasus, and subsequently by Philolaus, Archippus, and Lysis. About a century after the murder of Pythagoras, we find Archytas recognized as the head of the school. Archytas circa 400 BC, was one of the most influential citizens of Tarentum and was made governor of the city no less than 7 times. His influence among his contemporaries was very great, and he used it with Dionysius on one occasion to save the life of Plato. He was noted for the attention he paid to the comfort and education of his slaves and of children in the city. He was drowned in a shipwreck near Tarentum, and his body washed on shore, a fit punishment in the eyes of the more rigid Pythagoreans for his having departed from the lines of study laid down by their founder. Several of the leaders of the Athenian school were among his pupils and friends, and it is believed that much of their work was due to his inspiration. The Pythagoreans at first made no attempt to apply their knowledge to mechanics, but Archytas is said to have treated it with the aid of geometry. He is alleged to have invented and worked out the theory of the pulley, and is credited with the construction of a flying bird and some other ingenious mechanical toys. He introduced various mechanical devices for constructing curves and solving problems. These were objected to by Plato, who thought that they destroyed the value of geometry as an intellectual exercise, and later Greek geometricians confined themselves to the use of 2 species of instruments, namely rulers and compasses. Archytas was also interested in astronomy. He taught that the earth was a sphere rotating round its axis in 24 hours, and round which the heavenly bodies moved. Archytas was one of the first to give a solution of the problem to duplicate a cube, that is, to find the side of a cube whose volume is double that of a given cube. This was one of the most famous problems of antiquity. See below page 38 to 42. The construction given by Archytas is equivalent to the following. On the diameter OA of the base of a right circular cylinder, describe a semicircle whose plane is perpendicular to the base of the cylinder. Let the plane containing the semicircle rotate around the generator through O, then the surface traced out by the semicircle will cut the cylinder in a tortuous curve. The curve will be cut by a right cone whose axis is OA and semi-vertical axis is, say, 60 degrees in a point P, such that the projection of OP on the base of the cylinder will be to the radius of the cylinder in the ratio of the side of the required cube to that of the given cube. The proof given by Archytas is of course geometrical. It will be enough here to remark that in the course of it he shews himself acquainted with the results of the propositions Euclid 3.18, 3.35, and 11.19. To shew analytically that the construction is correct, take OA as the axis of x, and the generator through O as axis of z. Then with the usual notation in polar coordinates, and if a be the radius of the cylinder, we have for the equation of the surface described by the semicircle r equals 2a sine theta. For that of the cylinder, r sine theta equals 2a cos phi, and for that of the cone, sine theta times cos phi equals 1/2. These 3 surfaces cut in a point such that sine cubed theta equals 1/2, and therefore if ρ be the projection of OP on the base of the cylinder, then ρ cubed equals r sine theta quantity cubed equals 2a cubed. Hence the volume of the cube whose side is ρ is twice that of a cube whose side is a. I mention the problem and give the construction used by Archytas to illustrate how considerable was the knowledge of the Pythagorean school at that time. Theodorus. Another Pythagorean of about the same date as Archytas was Theodorus of Cyrene, who is said to have proved geometrically that the numbers presented by root 3, root 5, root 6, root 7, root 8, root 10, root 11, root 12, root 13, root 14, root 15, and root 17 are incommensurable with unity. Theaetetus was one of his pupils. Perhaps Timaeus of Locri and Brizo of Heraclea should be mentioned as other distinguished Pythagoreans of this time. Other Greek mathematical schools in 5th century BC. It would be a mistake to suppose that Miletus and Tarentum were the only places where in the 5th century Greeks were engaged in laying a scientific foundation for the study of mathematics. These towns represented the centers of chief activity, but there were few cities or colonies of any importance where lectures on philosophy and geometry were not given. Among these smaller schools I may mention those of Chios, Elea, and Thrace. The best known philosopher of the school of Chios was Euripides, who was born about 500 BC and died about 430 BC. He devoted himself chiefly to astronomy, but had studied geometry in Egypt and is credited with the solution of two problems, namely, one to draw a straight line from a given external point perpendicular to a given straight line, that's Euclid 112, and two, at a given point to construct an angle equal to a given angle, Euclid 123. Another important center was Elea in Italy. This was founded in Sicily by Xenophanes. He was followed by Parmenides, Zeno, and Melissus. The members of the Eleatic school were famous for the difficulties they raised in connection with the questions that required the use of infinite series, such for example as the well-known paradox of Achilles and the tortoise, enunciated by Zeno, one of the most prominent members, who was born in 495 BC and was executed at Elea in 435 BC in consequence of some conspiracy against the state. He was a pupil of Parmenides, with whom he visited in Athens circa 455 to 450 BC. Zeno argued that if Achilles ran 10 times as fast as a tortoise, yet if the tortoise had, say, 1,000 yards start, it could never be overtaken. For when Achilles had gone the 1,000 yards, the tortoise would still be 100 yards in front of him. But by the time he had covered these 100 yards, it would still be 10 yards in front of him, and so on forever. Thus Achilles would get nearer and nearer to the tortoise, but never overtake it. The fallacy is usually explained by the argument that the time required to overtake the tortoise can be divided into an infinite number of parts, as stated in the question, but these get smaller and smaller in geometrical progression, and the sum of them all is a finite time. After the lapse of that time, Achilles would be in front of the tortoise. Probably Zeno would have replied that this argument rests on the assumption that space is infinitely divisible, which is the question under discussion. He himself asserted that magnitudes were not infinitely divisible. These paradoxes made the Greeks look with suspicion on the use of infinite series and ultimately led to the invention of the method of exhaustions. The atomistic school, having its headquarters in Thrace, was another important centre. This was founded by Leucippus, who was a pupil of Zeno. He was succeeded by Democritus and Epicurus. Its most famous mathematician was Democritus, born in Abdera in 460 BC and is said to have died in 370 BC, who besides his philosophical works wrote on plane and solid geometry, incommensurable lines, perspective, and numbers. These works are all lost. But through several distinguished individual philosophers may be mentioned who during the 5th century lectured at different cities. They mostly seem to have drawn their inspiration from Tarentum, and towards the end of the century to have looked to Athens as the intellectual capital of the Greek world. And it is to the Athenian schools that we owe the next great advance in mathematics. End of chapter 2. Chapter 3, Part 1 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. Rouse Ball. Chapter 3. The schools of Athens and Cyzicus, circa 420 BC to 300 BC. Part 1. It was towards the close of the 5th century before Christ that Athens first became the chief centre of mathematical studies. Several causes conspired to bring this about. During that century she had become, partly by commerce, partly by appropriating for her own purposes the contributions of her allies, the most wealthy city in Greece, and the genius of her statesmen had made her the centre on which the politics of the peninsula turned. Moreover, what states disputed her claim to political supremacy, her intellectual preeminence was admitted by all. There was no school of thought which had not at some time that century been represented at Athens by one or more of its leading thinkers, and the ideas of the new science, which was being so eagerly studied in Asia Minor and Graecia Magna, had been brought before the Athenians on various occasions. Anaxagoras. Among the most important of the philosophers who resided at Athens and prepared the way for the Athenian school I may mention Anaxagoras of Clazomenae, who was almost the last philosopher of the Ionian school. He was born in 500 BC and died in 428 BC. He seems to have settled in Athens about 440 BC and there taught the results of the Ionian philosophy. Like all members of that school, he was much interested in astronomy. He asserted that the sun was larger than the Peloponnesus. This opinion, together with some attempts he had made to explain various physical phenomena which had been previously supposed to be due to the direct action of the gods, led to a prosecution for impiety, and he was convicted. While in prison, he is said to have written a treatise on the quadrature of the circle. The sophists can hardly be considered as belonging to the Athenian school any more than Anaxagoras can, but like him they immediately preceded and prepared the way for it, so that it is desirable to devote a few words to them. One condition for success in public life at Athens was the power of speaking well, and as the wealth and power of the city increased, a considerable number of sophists settled there who undertook amongst other things to teach the part of oratory. Many of them also directed the general education of their pupils, of which geometry usually formed a part. We are told that two of those who are usually termed sophists made a special study of geometry. These were Hippias of Elis and Antipho, and one made a special study of astronomy, and that was Meton, after whom the Metonic cycle is named. The first of these geometricians, Hippias of Elis, circa 420 BC, is described as an expert arithmetician, but he is best known to us through his invention of a curve called the quadratrix, by means of which an angle could be trisected or indeed divided in any given ratio. If the radius of a circle rotate uniformly around the centre O from a position OA through a right angle OB, and in the same time a straight line drawn perpendicular to OB move uniformly parallel to itself from the position OA to BC, the locus of their intersection will be the quadratrix. Let OR and MQ be the positions of these lines at any time. Let them cut in P a point on the curve. Then the ratio angle AOP to angle AOB will equal the ratio OM to OB. Similarly, if OR prime be another position of the radius, then the ratio of angle AOP prime to angle AOB will equal the ratio OM prime to OB. Therefore angle AOP to angle AOP prime will equal the ratio OM to OM prime. Therefore angle AOP prime to angle P prime OP will equal the ratio OM prime to M prime M. Hence, if the angle AOP be given and it be required to divide any given ratio, it is sufficient to divide OM in that ratio at M prime and draw the line M prime P prime, and then OP prime will divide AOP in the required ratio. If OA be taken as the initial line OP equals R, the angle AOP equals theta and OA equals A, then we have the ratio theta to half pi will be equal to the ratio r sine pi to a. And the equation of the curve is pi r equals 2a theta times cosecant theta. Hippias devised an instrument to construct the curve mechanically, but constructions which involve the use of any mathematical instruments except a ruler and a pair of compasses were objected to by Plato and rejected by most geometricians of a subsequent date. Antipho. The second sophist whom I mentioned was Antipho, circa 420 BC. He is one of very few writers among the ancients who attempted to find the area of a circle by considering it as the limit of an inscribed regular polygon with an infinite number of sides. He began by inscribing an equilateral triangle. On each side in the smaller segment he inscribed an isosceles triangle, and so on ad infinitum. Bryso. Another mathematician, probably about the same time, who attacked the quadrature problem in a similar way to that used by Antipho, was Bryso of Heraclea, who seems to have been a Pythagorean. See above, page 31. It is said that he began by inscribing and circumscribing squares and finally obtained polygons between whose areas the area of the circle lay. It is possible but not probable that for some time he taught at Athens. No doubt there were other cities in Greece where similar and equally meritorious work was being done, though the record of it has now been lost. I have mentioned the investigations of these writers, partly in order to give the idea of the kind of work of which was then going on all over Greece, but chiefly because they were the immediate predecessors of those who created the Athenian school. The history of the Athenian school begins with the teaching of Hippocrates about 420 BC. The school was established on a permanent basis by the labours of Plato and Eudoxus, and together with the neighbouring school of Cyzicus continued to extend on the lines laid down by these three geometricians until the foundation, about 300 BC, of the new university at Alexandria drew most of the talent of Greece thither. Eudoxus was among the most distinguished of the Athenian mathematicians, and it is also reckoned as the founder of the school of Cyzicus. The connection between this school and that of Athens was very close, and it is now impossible to disentangle their histories. It is said that Hippocrates, Plato, and Theaetetus belonged to the Athenian school, while Eudoxus, Menaechmus, and Aristippus belonged to that of Cyzicus. There was always a constant intercourse between the two schools. The earliest members of both had been under the influence either of Archytas or of his pupil Theodorus of Cyrene, and there was no difference in their treatment of the subject, so that they may be conveniently treated together. Before discussing the work of the geometricians of these schools in detail, I may note that they were especially interested in three problems, namely 1. The duplication of a cube, that is, the determination of the side of a cube whose volume is double that of a given cube, and 2. The trisection of an angle, and 3. The squaring of a circle, that is, the determination of a square whose area is equal to that of a given circle. Now the first two of these problems, considered analytically, require the solution of a cubic equation, and since a construction by means of circles whose equations are of the form x squared plus y squared plus ax plus by plus c equals 0, and straight lines whose equations are of the form alpha x plus beta y plus gamma equals 0, cannot be equivalent to the solution of a cubic equation. The problems are insoluble if our constructions we restrict ourselves to the use of circles and straight lines, i.e. Euclidean geometry. If the use of conic sections be permitted, both of these questions can be solved in many ways. The third problem is equivalent to finding a rectangle whose sides are equal respectively to the radius and to the semiperimeter of the circle. These lines have been long known to be incommensurable, but it is only recently that it has been shewn by Lindemann that the ratio cannot be the root of a rational algebraic equation. Hence this problem is also insoluble by Euclidean geometry. The Athenians and Cyzicians were thus destined to fail in all three problems, but the attempts to solve them led to the discovery of many new theorems and processes. Besides attacking these problems, the later Platonic school collected all the geometrical theorems then known and arranged them systematically. These collections comprise the bulk of the propositions in Euclid's Elements, books 1 to 9, 11, and 12, together with some of the more elementary theorems in conic sections. Hippocrates. Hippocrates of Chios, who must be carefully distinguished from his contemporary Hippocrates of Kos, the celebrated physician, was one of the greatest of the Greek geometricians. He was born about 470 BC at Chios, and began life as a merchant. The accounts differ as to whether he was swindled by the Athenian custom house officials who were stationed at the Chersonese, or whether one of his vessels was captured by an Athenian pirate near Byzantium. But at any rate, somewhere about 430 BC he came to Athens to try to recover his property in the law courts. A foreigner was not likely to succeed in such a case, and the Athenians seemed only to have laughed at him for his simplicity, first in allowing himself to be cheated, and then in hoping to recover his money. While prosecuting his cause, he attended the lectures of various philosophers, and finally, in all probability to earn a livelihood, opened a school of geometry himself. He seems to have been well acquainted with the Pythagorean philosophy, though there is no sufficient authority for the statement that he was ever initiated as a Pythagorean. He wrote the first elementary textbook of geometry, a textbook on which Euclid's Elements was probably founded, and therefore he may be said to have sketched out the lines on which geometry is still taught in English schools. It is supposed that the use of letters and diagrams to describe a figure was made by him or introduced about his time, as he employs expressions such as the point on which the letter A stands, and the line on which AB is marked. Cantor, however, thinks that the Pythagoreans had previously been accustomed to represent the 5 vertices of the pentagram star by the letters upsilon, gamma, iota, theta, alpha, see above, page 21. And though this was a single instance, they may perhaps have used the method generally. The Indian geometers have never employed letters to aid them in the description of their figures. Hippocrates also denoted the square on a line with the word venoms, and thus gave the technical meaning to the word power, which it still retains in algebra. There is reason to think that this use of the word was derived from the Pythagoreans, who are said to have enunciated the result of the proposition as Euclid 147 in the form that the total power of the sides of a right-angled triangle is the same as that of the hypotenuse. In this textbook, Hippocrates introduced the method of reducing one theorem to another, which being proved, the thing proposed necessarily follows, of which plan the reductio ad absurdum is a particular case. No doubt the principle had been used occasionally before, but he drew attention to it as a legitimate mode of proof which was capable of numerous applications. He may be said to have introduced the geometry of the circle. He discovered that similar segments of a circle contain equal angles, that the angle subtended by the chord of a circle is greater than, equal to, or less than a right angle as a segment of the circle containing it is less than, equal to, or greater than a semicircle (Euclid 331), and probably several other of the propositions in the third book of Euclid. It is most likely that he also enunciated the propositions that similar circles are to one another as the squares of their diameters, and that similar segments are as the square of the chords. The proof given in Euclid of the first of these theorems is believed to be due to Hippocrates, but the latter mathematician does not seem to have realized that all circles were similar. The most celebrated discoveries of Hippocrates were, however, in connection with the quadrature of the circle and the duplication of the cube, and it was owing to his influence that these problems played such a prominent part in the history of the Athenian school. The following propositions will sufficiently illustrate the method by which he attacked the quadrature problem. Alpha. He commenced by finding the area of a lune contained between the semicircle of a quadrantal arc standing on the same chord. This he did as follows. Let ABC be an isosceles right angled triangle inscribed in the semicircle ABOC, whose center is O. On AB and AC as diameters describes semicircles as in the figure. Then, since BC squared equals AC squared plus AB squared, Euclid 147, therefore by Euclid 12:2, the area of a half circle on BC equals the sum of the areas of the half circles on AC and AB. Take away the common parts, therefore area of triangle ABC equals the sum of the areas of lunes AECD and AFBG. Hence, the area of the lune AECD is equal to half of that of the triangle ABC. He next inscribed half a regular hexagon ABCD in a semicircle whose center was O, and on OA, AB, BC, and CD as diameters described semicircles, of which those on OA and AB are drawn in the figure. Then AD is double any of the lines OA, AB, BC, and CD. Therefore, AD squared equals OA squared plus AB squared plus BC squared plus CD squared. Therefore, area of half circle ABCD equals the sum of the areas of the half circles on OA, AB, BC, and CD. Take away the common parts, therefore the area of the trapezium ABCD equals 3 multiplied by the lune AEBF plus half circle on OA. If therefore the area of this latter lune be known, so is that of the semicircle described on OA as diameter. According to Simplicius, Hippocrates assumed that the area of this lune was the same as the area of the lune found in proposition alpha. If this be so, he was of course mistaken, as in the case he is dealing with, a lune contained between a semicircle and a sextantal arc standing on the same chord, but it seems probable that Simplicius misunderstood Hippocrates. Hippocrates also enunciated various other theorems which connected with lunes, which have been collected by Bretschneider and Ellmann, of which theorem last given is a typical example. I believe they are the earliest instances in which areas bounded by curves were determined by geometry. The other problem to which Hippocrates turned his attention was the duplication of the cube, that is, the determination of the side of a cube whose volume is double that of a given cube. This problem was known in ancient times as the Delian problem, a consequence of a legend that the Delians had consulted Plato on the subject. In one form of the story, which is related by Philoponus, it is asserted that the Athenians in 430 BC, when suffering from the plague of eruptive typhoid fever, consulted the oracle at Delos as to how they could stop it. Apollo replied, they must double the size of his altar, which was in the form of a cube. To the unlearned suppliants nothing seemed more easy, and a new altar was constructed, either having each of its edges doubled that of the old one, for which it followed the volume was increased eightfold, or by placing a similar cubic altar next to the old one. Whereupon, according to the legend, the indignant god made the pestilence worse than before, and informed a fresh deputation that it was useless to trifle with him, as his new altar must be a cube and have a volume exactly double that of his old one. Suspecting a mystery, the Athenians applied to Plato, who referred them to the geometricians, and especially to Euclid, who had made a special study of the problem. The introduction of the names of Plato and Euclid is an obvious anachronism. Eratosthenes gives a somewhat similar account of its origin, but with King Minos as the propounder of the problem. Hippocrates reduced the problem of duplicating the cube to that of finding two means between one straight line alpha and another twice as long 2 alpha. If these means be x and y, we have a is to x as x is to y as y is to 2 alpha, from which it follows that x cubed equals 2a cubed. It is in this form that the problem is always presented now. Formerly, any process of solution by finding these means was called a mesolabum. Hippocrates did not succeed in finding a construction for these means. End of chapter 3, part 1. Chapter 3, part 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 3. The schools of Athens and Cyzicus, circa 420 BC to 300 BC. Part 2. Plato. The next philosopher of the Athenian school who requires mention here was Plato, who was born in Athens in 429 BC. He was, as is well known, a pupil for 8 years of Socrates, and much of the teaching of the latter is inferred from Plato's dialogues. After the execution of his master in 399 BC, Plato left Athens, and being possessed of a considerable wealth, he spent some years travelling. It was during this time that he studied mathematics. He visited Egypt with Eudoxus, and Strabo says that in his time the apartments they occupied at Heliopolis were still shewn. Thence Plato went to Cyrene, where he studied under Theodorus. Next he moved to Italy, where he became intimate with Archytas, the then head of the Pythagorean school, Eurytas of Metapontum, and Timaeus of Locri. He returned to Athens about the year 380 BC and formed a school of students in a suburban gymnasium called the Academy. He died in 348 BC. Plato, like Pythagoras, was primarily a philosopher, and perhaps his philosophy should be regarded as founded on the Pythagorean rather than on the Socratic teaching. At any rate, it, like that of the Pythagoreans, was coloured with the idea that the secret of the universe was to be found in number and in form. Hence, as Eudemus says, he exhibited on every occasion the remarkable connection between mathematics and philosophy. All the authorities agree that, unlike many later philosophers, he made a study of geometry or some exact science an indispensable preliminary to that of philosophy. The inscription over the entrance to his school ran, "Let none ignorant of geometry enter my door," and on one occasion an applicant who knew no geometry is said to have been refused admission as a student. Plato's position as one of the masters of the Athenian mathematical school rests not so much on his individual discoveries and writings as on the extraordinary influence he exerted on his contemporaries and successors. Thus the objection that he expressed to the use of the construction of curves of any instruments other than rulers and compasses was at once accepted as canon which must be observed in such problems. It is probably due to Plato that subsequent geometricians began the subject with a carefully compiled series of definitions, postulates, and axioms. He also systematized the methods which could be used in attacking mathematical questions, and in particular directed attention to the value of analysis. The analytical method of proof begins by assuming that the theorem or problem is solved, and thence deducing some result. If the result be false, the theorem is not true or the problem is incapable of solution. If the result be known to be true, and if the steps be reversible, we get by reversing them a synthetic proof. But if the steps are not reversible, no conclusion can be drawn. Numerous illustrations of the method will be found in any modern textbook on geometry. If the classification of the methods of legitimate induction given by Mill in his work on logic had been universally accepted, and every new discovery in science had been justified by a reference to the rules laid down, he would, I imagine, have occupied a position in reference to modern science somewhat analogous to that which Plato occupied in regard to the mathematicians of his time. Almost the only extant instance of a mathematical theorem attributed to Plato is the following, which is traditionally assigned to him. If CAB and DAB be two right angled triangles having one side AB in common, their other sides AD and BC parallel and their hypotenuses AC and BD at right angles, then if these hypotenuses cut in P, we have the ratio PC to PB is to PB to PA is to PA to PD. This theorem was used in duplicating the cube, for if such triangles can be constructed having PD equals 2 times PC, the problem will be solved. It is easy to make an instrument by which the figures can be drawn. Eudoxus. Of Eudoxus, the third great mathematician of the Athenian school and the founder of that at Cyzicus, we know very little. He was born in Cnidus in 408 BC. Like Plato, he went to Tarentum and studied under Archytas, the then head of the Pythagoreans. Subsequently, he travelled with Plato to Egypt and then settled at Cyzicus, where he founded the school of that name. Finally, he and his pupils moved to Athens. There he seems to have taken some part in public affairs, and to have practiced medicine, but the hostility of Plato and his own unpopularity as a foreigner made his position uncomfortable, and he returned to Cyzicus or Cnidus shortly before his death. He died while on a journey to Egypt in 355 BC. His mathematical work seems to have been of a high order of excellence. He discovered most of what we know as the fifth book of Euclid, and proved it in much the same form as that of which it is there given. He discovered some theorems on what was called the golden section. The problem to cut a line AB in the golden section, that is, to divide it, say, at H, in extreme and mean ratio, that is, so that AB to AH equals the ratio AH to HB, is solved in Euclid 2:11, and was probably known to the Pythagoreans at an early date. If we denote AB by L, AH by A, and HB by B, the theorems that Eudoxus proved are equivalent to the following algebraical identities. Number 1. Quantity A plus 1/2 L all squared equals 5 multiplied by quantity 1/2 times L all squared. That's Euclid 13.1. Number 2. Conversely, if 1 be true, and AH be taken equal to A, then AB will be divided at H in the golden section. That's Euclid 13.2. Number 3. Quantity B plus 1 half A all squared equals 5 multiplied by quantity 1 half times A all squared. Euclid 13.3. Number 4. L squared plus B squared equals 3 multiplied by A squared. That's Euclid 13.4. Number 5. L plus A is to L as L is to A, which gives another golden section, and that's Euclid 13.5. These propositions were subsequently put by Euclid at the commencement of his 13th book, but they might have been equally well placed toward the end of the second book. All of them are obvious algebraically, since L equals A plus B and A squared equals B times L. Eudoxus further established the method of exhaustions, which depends on the proposition that if from the greater of two unequal magnitudes there be taken more than its half, and from the remainder more than its half, and so on, there will at length remain a magnitude less than the least of the proposed magnitudes. This proposition was placed by Euclid as the first proposition of the 10th book of his Elements, but in most modern school editions it is printed at the beginning of the 12th book. By the aid of this theorem, the ancient geometers were able to avoid the use of infinitesimals. The method is rigorous, but awkward of application. A good illustration of its use is to be found in the demonstration of Euclid 12.2, namely that of the square of the radius of one circle is to the square of the radius of another circle, as the area of the first circle is to the area of which is neither less nor greater than the area of the second circle, and which therefore must be exactly equal to it. The proof given by Euclid, as was usual, is completed by a reductio ad absurdum. Eudoxus applied the principle to shew that the volume of a pyramid or cone is 1/3 that of the prism or cylinder of the same base and the same altitude. That's Euclid 12.7 and 10. Some writers attribute the proposition Euclid 12.2 to him, but not Hippocrates. Eudoxus also considered certain curves other than the circle, but there seems to be no authority for the statement, which is found in some old books, that he studied the properties of the conic sections. He discussed some of the plane sections of the anchor ring, that is, of the solid generated by the revolution of a circle around a straight line lying on its plane, but he assumed that the line did not cut the circle. A section by a plane through this line consists of two circles. If the plane be moved parallel to itself, the sections are lemniscates. When the plane first touches the surface, the section is a figure of 8, generally called Bernoulli's lemniscate, whose equation is r squared equals a squared multiplied by cosine 2 theta. All this is explained at length in books on solid geometry. Eudoxus applied these curves to explain the apparent progressive and retrograde motions of the planets, but we do not know the method he used. Eudoxus constructed an orrery and wrote a treatise on practical astronomy, in which he adopted a hypothesis previously propounded by Philolaus 409 BC to 356 BC, and supposed a number of moving spheres to which the sun, moon, and stars were attached, and by which their rotation produced the effects observed. In all he required 27 spheres. As observations became more accurate, subsequent astronomers who accepted his theory had continually to introduce fresh spheres to make the theory agree with the facts. The work of Aratus on astronomy, which was written about 300 BC, is still extant, is founded on that of Eudoxus. Plato and Eudoxus were contemporaries. Among Plato's pupils were the mathematicians Leodamus, Nicolaides, Amyclas, and to their school belonged Leon, Theodius, both of whom wrote textbooks on plane geometry, Cyzicenus, Thasus, Hierotimus, Philippus, and Theaetetus. Among the pupils of Eudoxus are reckoned Menaechmus and his brother Dinostratus, who applied the quadratics to the duplication and trisection problems, and Aristoteus. Menaechmus. Of the above mentioned mathematicians, Menaechmus requires special attention. He was born about 375 BC and died about 325 BC. He was a pupil of Eudoxus and probably succeeded him as head of the school at Cyzicus. Menaechmus acquired a great reputation as a teacher of geometry and was for that reason appointed one of the tutors to Alexander the Great. In answer to Alexander's request to make his proofs shorter, he made the well-known reply, "In the country, sire, there are private and even royal roads, but in geometry there is only one road for all." Menaechmus was the first to discuss the conic sections, which were long called the Menaechmian triads. He divided them into three classes and investigated their properties, not by taking different plane sections of a fixed cone, but by keeping his plane fixed and cutting it by different cones. He shewed that the section of the right cone by a plane perpendicular to the generator is an ellipse, and if the cone be acute angled, a parabola, and if it be right angled, a hyperbola. If it be obtuse angled, he gave the mechanical construction for curves of each class. It seems almost certain he was acquainted with the fundamental properties of these curves, but some writers think that he failed to connect them with the sections of the cone for which he had discovered, and there is no doubt that he regarded the latter not as plane loci, but as curves drawn on the surface of a cone. He also shewed how these curves could be used in either of the following ways to give a solution of the problem to duplicate a cube. In the first of these he pointed out that two parabolas having a common vertex, axes at right angles, and such that the latus rectum of the one is double that of the other, will intersect in another point whose abscissa or ordinate will give a solution. For using analysis, if the equations of the parabolas be y squared equals 2ax and x squared equals ay, they intersect in a point whose abscissa is given by x cubed equals 2a cubed. It is probable that this method was suggested by the form in which Hippocrates had cast the problem, namely, to find x and y so that a is to x equals x is to y equals y to 2a, when we have x squared equals ay and y squared equals 2ax. The second solution given by Menaechmus was as follows. Describe a parabola of latus rectum L. Next, describe a rectangular hyperbola, the length of whose real axis is 4L, and having for its asymptotes the tangent at the vertex of the parabola and the axis of the parabola. Then the ordinate and abscissa of the point of intersection of the curves are the mean proportionals between L and 2L. This is at once obvious by analysis. The curves are x squared equals L times y and x times y equals 2 times L squared. These cut in a point determined by x cubed equals 2 times L cubed and y cubed equals 4 times L cubed. Hence, L is to x equals x is to y equals y is to 2L. Of the other members of these schools, the only mathematicians of first-rate power were Aristeas and Theaetetus, whose works are entirely lost. We know, however, that Aristeas wrote on the 5 regular solids and on conic sections, and that Theaetetus developed the theory of incommensurable magnitudes. The only theorem we can now definitely ascribe to the latter is that given by Euclid in the 9th proposition of the 10th book of the Elements, namely, that the squares on two commensurable right lines have one to the other a ratio which a square number has to a square number, and conversely. But the squares on two incommensurable right lines have one to the other a ratio which cannot be expressed as that of a square number to a square number, and conversely. This theorem includes the results given by Theodorus. See above, page 31. The contemporaries or successors of these mathematicians wrote some fresh textbooks on the elements of geometry and the conic sections, introduced problems concerned with finding loci, and efficiently carried out the work commenced by Plato of systematizing the knowledge already acquired. Aristotle. An account of the Athenian school would be incomplete if there were no mention of Aristotle, who was born in Stagira in Macedonia in 384 BC and died at Chalkis in Euboea in 322 BC. Aristotle, however deeply interested though he was in natural philosophy, was chiefly concerned with mathematics and mathematical physics as supplying illustrations of correct reasoning. A small book containing a few questions on mechanics, which is sometimes attributed to him, is of doubtful authority, but though in all probability it is due to another writer, it is interesting partly as shewing that the principles of mechanics were beginning to excite attention, and partly as containing the earliest known employment of letters to indicate magnitudes. The most instructive parts of the book are the dynamical proof of the parallelogram of forces for the direction of the resultant, and the statement that, if alpha be a force, beta be the mass to which it is applied, gamma the distance through which it is moved, and delta the time of the motion, then alpha will move 1/2 beta through 2 gamma in time delta, or through gamma in time 1/2 delta. But the author goes on to say that it does not follow that 1/2 alpha will move beta through 1/2 gamma in time delta, because 1/2 alpha may not be able to move beta at all. For 100 men may drag a ship 100 yards, but it does not follow that one man can drag it 1 yard. The first part of this statement is correct and is equivalent to the statement that an impulse is proportional to the momentum produced, but the second part is wrong. The author also states the fact that what is gained in power is lost in speed, and therefore that two weights which keep a weightless lever in equilibrium are inversely proportional to the arms of the lever. This, he says, is the explanation why it is easier to extract teeth with a pair of pincers than that with the fingers. Among the other questions raised but not answered are why a projectile should ever stop, and why carriages with large wheels are easier to move than with small. I ought to add that the book contains some gross blunders, and as a whole is not able or suggestive as might be inferred from the above extracts. End of chapter 3. Chapter 4, Part 1 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 4. The First Alexandrian School, circa 300 BC to 30 BC. Part 1. The earliest attempt to found a university, as we understand the word, was made at Alexandria. Richly endowed, supplied with lecture rooms, libraries, museums, laboratories, gardens, and all the plant and machinery that ingenuity could suggest, it became at once the intellectual metropolis of the Greek race, and remained so for 1,000 years. It was particularly fortunate in producing within the first century of its existence 3 of the greatest mathematicians of antiquity, Euclid, Archimedes, and Apollonius. They laid down the lines on which mathematics were subsequently studied, and largely owing to their influence the history of mathematics centres more or less round that of Alexandria until the destruction of the city by the Arabs in 641 AD. The city and university of Alexandria were created under the following circumstances. Alexander the Great had ascended the throne of Macedonia in 336 BC at the early age of 20, and by 332 BC he had conquered or subdued Greece, Asia Minor, and Egypt. Following the plan he had adopted whenever a commanding site had been left unoccupied, he founded a new city on the Mediterranean near one mouth of the Nile, and he himself sketched out the ground plan and arranged for drafts of Greeks, Egyptians, and Jews to be sent to occupy it. The city was intended to be the most magnificent in the world, and the better to secure this, its erection was left in the hands of Dinocrates, the architect of the temple of Diana at Ephesus. After Alexander's death in 323 BC, his empire was divided and Egypt fell to the lot of Ptolemy, who chose Alexandria as the capital of his kingdom. A short period of confusion followed, but as soon as Ptolemy was settled on the throne, say 306 BC, he determined to attract as far as he was able learned men of all sorts to his new city, and he at once began the erection of the university buildings on a piece of ground immediately adjoining his palace. The university was ready to be opened somewhere around 300 BC, and Ptolemy, who wished to secure for its staff the most eminent philosophers of the time, naturally turned to Athens to find them. The great library, which was a central feature of the scheme, was placed under Demetrius Phalereus, a distinguished Athenian, and so rapidly did it grow that within the first 40 years it, together with the Egyptian annex, possessed about 600,000 rolls. The mathematical department was placed under Euclid, who was thus the first, as he was one of the most famous of the mathematicians of the Alexandrian school. It happens that contemporaneously with the foundation of this school, the information on which our history is based becomes more ample and certain. Many of the works of the Alexandrian mathematicians are still extant, and we have besides an invaluable treatise by Pappus, described below, in which their best known treatises are collated, discussed, and criticized. It curiously turns out that just as we begin to be able to speak with certainty on the subject matter which was taught, we find that our information as to the personality of the teachers becomes uncertain, and we know very little of the lives of the mathematicians mentioned in this and the next chapter, even the dates at which they lived being frequently uncertain. The 3rd century before Christ. Euclid. This century produced 3 of the greatest mathematicians of antiquity, namely Euclid, Archimedes, and Apollonius. The earliest of these was Euclid. Of his life we know next to nothing, save that he was of Greek descent, and he was born about 330 BC. He died about 275 BC. It would appear that he was well acquainted with the Platonic geometry, but he does not seem to have read Aristotle's works, and these facts are supposed to have strengthened the tradition that he was educated at Athens. Whatever may have been his previous training and career, he proved most successful a teacher when settled at Alexandria. He impressed his own individuality on the teachings of the new university to such an extent that to his successors and almost to his contemporaries the name Euclid meant, as it does to us, the book or the books he wrote, and not the man himself. Some of the medieval writers went so far as to deny his existence, and with the ingenuity of philologists they explained that the term was only a corruption of the Greek words for key and geometry. The former word was presumably derived from kleis. I can only explain the meaning assigned to dies by the conjecture that as the Pythagoreans said that the number 2 symbolized a line, possibly a schoolman may have thought that it could be taken as indicative of geometry. From the meagre notices of Euclid which have come down to us, we find that the saying that there is no royal road to geometry was attributed to Euclid as well as to Menaechmus, but it is an epigrammatic remark which has had many imitators. Euclid is also said to have insisted that knowledge was worth acquiring for its own sake, and Stobaeus, who is somewhat doubtful an authority, tells us that when a lad who had just begun geometry asked, "What do I gain by learning all this stuff?" Euclid made his slave give the boy some coppers, since, said he must make a profit out of what he learns. According to Pappus, Euclid, in making the use of the work of his predecessors when writing the Elements, dealt most gently with those who had in any way advanced the science, and the Arabian writers, who may perhaps convey to us the traditions of Alexandria, uniformly represent him as a gentle and kindly old man. Euclid was the author of several works, but his reputation had rested mainly on his Elements. This treatise contains a systematic exposition of the leading propositions of elementary geometry, exclusive of conic sections, and of the theory of numbers. It was at once adopted by the Greeks as the standard textbook for the elements of pure mathematics, and it is probable that it was written for that purpose and not as a philosophical attempt to shew that the results of geometry and arithmetic are necessary truths. The modern text is founded on an edition prepared by Theon, the father of Hypatia, and is practically a transcript of Theon's lectures at Alexandria circa 380 AD. There is at the Vatican a copy of an older text, and we have besides quotations from the work and references to it by numerous writers of various dates. From these sources we gather that the definitions, axioms, and postulates were rearranged and slightly altered by subsequent editors, but that the propositions themselves are substantially as Euclid wrote them. As to the matter of the work, the geometrical part is to a large extent a compilation from the works of previous writers. Thus the substance of books 1 and 2 is probably due to Pythagoras, that of book 3 to Hippocrates, that of book 5 to Eudoxus, and the bulk of books 4, 6, 11, and 12 to the later Pythagorean or Athenian schools. But this material was rearranged, obvious deductions were omitted, for example the proposition that the perpendiculars from the angular points of a triangle on the opposite sides meet in a point was cut out, and in some cases new proofs substituted. The part concerned with the theory of numbers would seem to have been taken from the works of Eudoxus and Pythagoras, except that portion, book 10, which deals with irrational magnitudes. This later may be founded on the lost book of Theaetetus, but much of it is probably original, for Proclus says that while Euclid arranged the propositions of Eudoxus, he completed many of those of Theaetetus. The way in which the propositions are proved, consisting of enunciation, statement, construction, proof, and conclusion, is due to Euclid. So also is the synthetical character of the work, each proof being written out as a logically correct train of reasoning, but without any clue to the method by which it was obtained. The defects of Euclid's Elements as a textbook of geometry have been often stated. The most prominent are these. 1. The definitions and axioms contain many assumptions which are not obvious, and in particular the so-called axiom about parallel lines is not self-evident. 2. No explanation is given as to the reason why the proofs take the form in which they are presented, that is, the synthetical proof is given but not the analysis by which it was obtained. 3. There is no attempt made to generalize the results arrived at. For instance, the idea of an angle is never extended so as to cover the case where it is equal to or greater than two right angles. The second half of the 33rd proposition in the 6th book, as it is now printed, appears to be an exception, but it is due to Theon and not due to Euclid. 4. The principle of superposition as a method of proof might be used more frequently with advantage. 5. The classification is imperfect, and 6. The work is unnecessarily long and verbose. On the other hand, the propositions in Euclid are arranged so as to form a chain of geometrical reasoning, proceeding from certain almost obvious assumptions by easy steps to results of considerable complexity. The demonstrations are rigorous, often elegant, and not too difficult for a beginner. Lastly, nearly all the elementary metrical as opposed to graphical properties of space are investigated. The fact that for 2000 years it has been the recognized textbook of the subject raises further a strong presumption that it is not unsuitable for the purpose. During the last few years some determined efforts have been made to displace it in our schools, but the majority of teachers still appear to regard it as the best foundation for geometrical teaching that has yet been published. The book has been, however, generally abandoned on the continent, though apparently with doubtful advantage to the teaching of geometry. To these arguments in its favour may be added the fact that some of the greatest mathematicians of modern times, such as Descartes, Pascal, Newton, and Lagrange, have advocated its retention as a textbook. And Lagrange said that he who did not study geometry in Euclid would be as one who should learn Latin or Greek from modern works written in those tongues. It must also be remembered that there is an immense advantage in having a single textbook in universal use in a subject like geometry. The unsatisfactory condition of the teaching of geometrical conics in schools is a standard illustration of the evils likely to arise from using different textbooks in such a subject. Some of the objections urged against Euclid do not apply to certain of the recent school editions of his Elements. I do not think that all the objections above stated can fairly be urged against Euclid himself. He published a collection of problems generally known as the Dedomena or data. This contains 95 illustrations of the kind of deductions which frequently have to be made in analysis, such as that if one of the data of the problems under consideration be that one angle of some triangle in the figure is constant, then it is legitimate to conclude that the ratio of the area of the rectangle under the sides containing the angle to the area of the triangle is known. It's proposition 66. Pappus says that the work was written for those who wish to acquire the power of solving problems. It is in fact a graduated series of exercises in analysis, and this seems a sufficient answer to the second objection. Euclid also wrote a work called Peri Division or De Divisionibus, which is known to us only through an Arabic translation, which may be itself imperfect. This is a collection of 36 problems on the division of areas into parts which bear to one another a given ratio. It is not unlikely that this was only one of several such collections of examples, possibly including the fallacies and the porisms, but even by itself it shews that the value of exercises and writers was fully recognized by Euclid. I may here add a suggestion thrown out by De Morgan, who is perhaps the most acute of all the modern critics of Euclid. He thinks it likely that the Elements were written towards the close of Euclid's life, and that their present form represents the first draft of the proposed work, which, with the exception of the 10th book, Euclid did not live to revise. If this opinion is correct, then it is probable that Euclid would in his revision have removed the 5th objection. The geometrical parts of the Elements are so well known that I do no more than to allude to them. The first 4 books and book 6 deal with plane geometry. The theory of proportion of any magnitudes is discussed in book 5, and books 11 and 12 treat of solid geometry. On the hypothesis that the Elements are the first draft of Euclid's proposed work, it is possible that book 13 is a sort of appendix containing some additional propositions which would have been put ultimately in one of the other earlier books. Thus, as mentioned above, see page 46, that the first 5 propositions which deal with a line cut in golden section might be added to the second book. The next 7 propositions are concerned with the relations between certain incommensurable lines in plane figures, such as the radius of a circle and the sides of an inscribed regular triangle, pentagon, hexagon, and decagon, which are treated by the methods of the 10th book and as an illustration of them. The 5 regular solids are discussed in the last 6 propositions. Bretschneider is inclined to think that the 13th book is a summary of part of the lost work of Aristeas, but the illustrations of the methods of the 10th book are due most probably to Theaetetus. Books 7, 8, 9, and 10 of the Elements are given up to the theory of numbers. The mere art of calculation or logistique was taught to boys when quite young. It was stigmatized by Plato as childish and never received much attention from Greek mathematicians, nor was it regarded as forming part of a course of mathematics. We do not know how it was taught, but the abacus certainly played a prominent part in it. The scientific treatment of numbers was called arithmetic, which I have here generally translated as the science of numbers. It had special reference to ratio, proportion, and the theory of numbers. It is with this alone that most of the extant Greek works deal. In discussing Euclid's arrangement of the subject, we must therefore bear in mind that those who attended his lectures were already familiar with the art of calculation. The system of numeration adopted by the Greeks is described later, see below, chapter 7, but it was so clumsy that it rendered the scientific treatment of numbers much more difficult than of geometry. Hence Euclid commenced his mathematical course with plane geometry. At the same time it must be observed that the results of the second book, though geometrical in form, are capable of expression in algebraical language, and the fact that numbers could be represented by lines was probably insisted on at an early stage and illustrated by concrete examples. This graphical method of using lines to represent numbers possessed the obvious advantage of leading to proofs which are true for all numbers rational or irrational. It will be noticed that among other propositions in the second book we get geometrical proofs of the distributive and commutative laws, of rules for multiplication, and finally geometrical solutions to the equations a multiplied by quantity a minus x equals x squared, that is, x squared plus ax minus a squared equals 0. That's Euclid 2:11. And x squared minus ab equals 0. Euclid 2:14. The solution of the first of these equations is given of the form the square root of quantity a squared plus 1/2 a squared end of square root minus half a. The solutions of the equations ax squared minus bx plus c equals 0 and ax squared plus bx minus c equals 0 are given later in Euclid 6:28 and 6:29, the cases when a equals 1 can be deduced from the identities proved in Euclid 2:5 and 6, but it is doubtful if Euclid would have detected this. The results of the 5th book, in which the theory of proportion is considered, apply to any magnitudes, and therefore are true of numbers as well as of geometrical magnitudes. In the opinion of many writers, this is the easiest way of treating the theory of proportion on a scientific basis, and was used by Euclid as the foundation on which he built the theory of numbers. The theory of proportion given in this book is believed to be due to Eudoxus. The treatment of the same subject in the 7th book is less elegant and is supposed to be a reproduction of the Pythagorean teaching. This double discussion of proportion is, as far as it goes, in favour of the conjecture that Euclid did not live to revise the work. In books 7, 8 and 9 Euclid discusses the theory of rational numbers. He commences the seventh book with some definitions founded on the Pythagorean notation. In propositions 1 to 3 he shews that if, in the usual process for finding the greatest common measure of two numbers, that the least divisor be unity, the numbers must be prime, and he thence deduces the rule for finding their GCM. Propositions 4 to 22 include the theory of fractions, which he bases on the theory of proportion. Among other results he shews that AB equals BA, proposition 16. In propositions 23 to 34 he treats of prime numbers, given many of the theorems in modern textbooks on algebra. In propositions 35 to 41 he discusses the least common multiple of numbers and some miscellaneous problems. The eighth book is chiefly devoted to numbers in continued proportion, i.e. in a geometrical progression, and the cases where one or more is a product, square, or cube are specially considered. In the ninth book Euclid continues the discussion of geometrical progressions, and in proposition 35 he enunciates the rule for the summation of a series of n terms, though the proof is given only for the case where n is equal to 4. He also develops the theory of primes, shews that the number of primes is infinite, proposition 20, and discusses the properties of odd and even numbers. He concludes by shewing how to construct a perfect number, proposition 36. In the 10th book Euclid treats of irrational magnitudes, and since Greeks possessed no symbolism for surds he was forced to adopt a geometrical representation. Propositions 1 to 21 deal generally with incommensurable magnitudes. The rest of the book, namely propositions 22 to 117, is devoted to the discussion of every possible variety of lines which can be represented, such as the square root of a plus or minus the square root of b, where a and b denote commensurable lines. There are 25 species of such lines, and that Euclid could detect and classify them all is in the opinion of so competent an authority as Nesselmann as the most striking illustration of his genius. It seems at first almost impossible that this could have been done without the aid of algebra, but it is tolerably certain that it was actually effected by abstract reasoning. No further advance in the theory of incommensurable magnitudes was made until the subject was taken up by Leonardo and Cardan after an interval of more than 1000 years. In the last proposition of the 10th book, 10.117, the side and diagonal of a square are proved to be incommensurable, and the proof is so short and easy that I may quote it. If possible, let the side be to the diagonal in a commensurable ratio, namely that of two integers a, b. Suppose this ratio is reduced to its lowest term, so that a and b have no common divisor other than unity, that is, they are prime to one another. Then, by Euclid 147, b squared equals 2a squared, and therefore b squared is an even number. Therefore b is an even number. Hence, since a is prime to b, a must be an odd number. Again, since it has been shewn that b is an even number and b may be represented by 2n, therefore 2n quantity squared equals 2 times a squared. Therefore a squared equals 2 times n squared. Therefore a squared is an even number. Therefore a is an even number. Thus the same number a must be both odd and even, which is absurd. Therefore the side and diagonal are incommensurable. Henkel believes that this proof was due to Pythagoras, and was inserted on account of its historical interest. This proposition is also proved in another way by Euclid 10.9. In addition to the elements and the last two collections of riders above mentioned, which are extant, Euclid wrote the following books on geometry. 1. An elementary treatise on conic sections in 4 books. 2. A book on curved surfaces, probably chiefly cone and cylinder. 3. A collection of geometrical fallacies, which were to be used as exercises in the detection of errors. And 4. A treatise on the porisms arranged in the 3 books. All of these are lost, but the work on porisms was discussed at such length by Pappus that some writers have thought it possible to restore it. In particular, Chasles in 1860 published what purports to be a reproduction of it, in which will be found the conceptions of cross ratios and projections, in fact those ideas of modern geometry which Chasles and other writers of this century have used so largely. This is brilliant and ingenious, and of course no one can prove that it is not exactly what Euclid wrote, but the statements of Pappus concerning this book have come to us only in mutilated form, and De Morgan frankly says that he found them unintelligible, an opinion in which most of those who read them will, I think, concur. Euclid published 2 books on optics, namely the Optics and the Catoptrica. Of these the former is extant. A work which purports to be the latter exists in the form of an Arabic translation, but there is some doubt as to whether it represents the original work written by Euclid. In any case the text is extraordinarily corrupt. The Optics commences with the assumption that the objects are seen by rays emitted from the eye in straight lines. For if light proceeded from the object we should not, as we often do, fail to perceive a needle on the floor. It contains 61 propositions founded on 12 assumptions. The Catoptrica consists of 31 propositions dealing with reflections in planes, convex and concave mirrors. The geometry of both books is ingenious. Euclid also wrote the Phenomena, a treatise on geometrical astronomy. It contains references to the work of Autolycus and to some book on spherical geometry by an unknown writer. Pappus asserts that Euclid also composed a book on the elements of music. This may refer to Sectio Canonis, which is by Euclid and deals with musical intervals. To these works I may add the following little problem, which occurs in the Palatine Anthology and is attributed by tradition to Euclid. Quote, a mule and a donkey were going to market laden with wheat. The mule said, if you give me 1 measure, I should carry twice as much as you, but if I give you 1, we should bear equal burdens. Tell me, learned geometrician, what were their burdens? Now it is impossible to say whether the question is genuine, but it is the kind of question he might have asked. It will be noticed that Euclid dealt only with magnitudes and did not concern himself with their numerical measures, but it would seem from the works of Aristarchus and Archimedes that this was not the case with all the Greek mathematicians of that time. As one of the works of the former is extant, it will serve as another illustration of Greek mathematics of this period. Aristarchus. Aristarchus of Samos, born in 310 BC and died in 250 BC, was an astronomer rather than a mathematician. He asserted at any rate, as a working hypothesis, that the sun was the centre of the universe, and that the earth revolved around the sun. This view, in spite of the simple explanation it afforded of various phenomena, was generally rejected by his contemporaries, but his propositions on the measurement of the sizes and distances of the sun and moon were accurate in principle, and his results were generally accepted, for example by Archimedes in Samitis, see below page 73, as approximately correct. There are 19 theorems, of which I select the 7th as a typical illustration, because it shews the way in which the Greeks evaded the difficulty of finding the numerical value of surds. Aristarchus observed the angular distance between the moon when dichotomized and the sun, and found it to be 29/30 of a right angle. It is actually about 89 degrees 21 minutes, but of course his instruments were of the roughest description. He then proceeded to shew that the distance of the sun is greater than 18 and less than 20 times the distance of the moon in the following manner. Let S be the sun, E be the earth, and M the moon. Then, when the moon is dichotomized, that is, when the bright part which we see is exactly a half circle, the angle between MS and ME is a right angle. With E as the center and the radii ES, EG bisecting the angle AEF as in the figure, let EM produced cut AF in H. The angle AEM is by hypothesis 1/30th of a right angle. Hence we have angle AEG to angle AEH has the ratio 1/4 right angle to 1/30th of a right angle, or the ratio 15:2. AG to AH, that is the tangent of AEG to the tangent of AEH, is also 15:2. Again, the ratio FG squared to AG squared is equal to the ratio EF squared to EA squared, Euclid 6:3, which is a ratio of 2:1, Euclid 147. Therefore, FG squared to AG squared is greater than the ratio 49:25. Therefore, FG to AG is a ratio greater than the ratio 7:5. Therefore, AF to AG, that ratio is greater than the ratio 12:5, and therefore the ratio AE to AG greater than the ratio 12:5. Now, compounding the statements in alpha was the AG to AH ratio, which would be equal to the tangent AEG to AEH being greater than 15:2, and statement beta being the statement AE to AG being greater than the ratio of 12:5. So compounding those ratios, we have the ratio AE to AH being greater than 18:1. But the triangles EMS and EAH are similar. Therefore, ES to EM is a ratio greater than 18:1. I will leave the second half of the proposition to amuse any reader who may care to prove it. The analysis is straightforward. In somewhat similar way, Aristarchus found the ratio of the radii of the sun, earth, and moon. End of chapter 4, part 1. Chapter 4, part 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 4, Part 2. The First Alexandrian School, circa 300 BC to 30 BC. Archimedes. We know very little of Conon and Dositheus, the immediate successors of Euclid at Alexandria, or of their contemporaries Zeuxippus and Nicoteles, who most likely also lectured there, except that Archimedes, who was a student at Alexandria probably shortly after Euclid's death, had a high opinion of their ability and corresponded with the three first mentioned. Their work and reputation had been overshadowed completely by that of Archimedes, whose marvellous mathematical powers have been surpassed only by those of Newton. Archimedes, who probably was related to the royal family at Syracuse, was born there in 287 BC and died in 212 BC. He went to university at Alexandria and attended the lectures of Conon, but as soon as he had finished his studies returned to Sicily, where he passed the remainder of his life. He took no part in public affairs, but his mechanical ingenuity was astonishing, and on any difficulties which could be overcome by material means arising, his advice was generally asked by the government. Archimedes, like Plato, held that it was undesirable for a philosopher to seek to apply the results of science to any practical use. But whatever might have been his view of what ought to be the case, he did actually introduce a large number of new inventions. The stories of the detection of the fraudulent goldsmith, and of the use of burning glasses to destroy the ships of the Roman blockading squadron, will recur to most readers. Perhaps it is not as well known that Hiero, who had built a ship so large that he could not launch it off the slips, applied to Archimedes. The difficulty was overcome by means of an apparatus of cogwheels worked by an endless screw, but we are not told exactly how the machine was used. It is said that it was on this occasion, and acknowledging the compliments of Hiero, that Archimedes made the well known remark that if he had but a fixed fulcrum he could move the earth. Most mathematicians are aware that the Archimedean screw was another of his inventions. It consists of a tube, open at both ends, and bent into the form of a spiral, like a corkscrew. If one end be immersed in water, and the axis of the instrument, i.e. the axis of the cylinder on the surface of which the tube lies, be inclined to the vertical at a sufficiently big angle, and the instrument turned round it, the water will flow along the tube and out the other end. In order that it may work, the inclination of the axis of the instrument to the vertical must be greater than the pitch of the screw. It was used in Egypt to drain the fields after an inundation of the Nile, and was also frequently applied to pump water out of the hold of a ship. The story that Archimedes set fire to the Roman ships by means of burning glasses and concave mirrors is not mentioned till some centuries after his death, and is generally rejected, but it is not so incredible as is commonly supposed. The mirror of Archimedes is said to have been made of a hexagon surrounded by several polygons, each of 24 sides, and Buffon in 1747 contrived, with the aid of a single composite mirror made on this model with 168 small mirrors, to set fire to wood at a distance of 150 feet, and to melt lead at a distance of 140 feet. This was in April, and in Paris, so in a Sicilian summer, with several mirrors the deed would be possible, and if the ships were anchored near the town would not be difficult. It is perhaps worth mentioning that a similar device is said to have been used in the defence of Constantinople in 514 AD, and is alluded to by writers who either were present at the siege or obtained their information from those who were engaged in it. But whatever be the truth as to this story, there is no doubt that Archimedes devised the catapults which kept the Romans, who were then besieging Syracuse, at bay for a considerable time. These were constructed so that the range could be made either short or long at pleasure, and so that they could be discharged through a small loophole without exposing the artillerymen to the fire of the enemy. So effective did they prove that the siege was turned into a blockade, and 3 years elapsed before the town was taken, that is in 212 BC. Archimedes was killed during the sack of the city which followed its capture, in spite of the orders given by the consul Marcellus, who was in command of the Romans, that his house and life should be spared. It is said that a soldier entered his study while he was regarding a geometrical diagram drawn in the sand on the floor, which was the usual way of drawing figures in classical times. Archimedes told him to get off the diagram and not spoil it. The soldier, feeling insulted at having orders given to him by and ignorant of whom the old man was, killed him. According to another and more probable account, the cupidity of the troops was excited by seeing his instruments and constructed of polished brass which they supposed to be made of gold. The Romans erected a splendid tomb to Archimedes, on which was engraved, in accordance with a wish he had expressed, the figure of a sphere inscribed in a cylinder, in commemoration of the proof he had given to a volume of a sphere which was equal to 2/3 that of the circumscribing right cylinder, and its surface to 4 times the area of a great circle. Cicero gives a charming account of his efforts, which were successful, to rediscover the tomb in 75 BC. It is difficult to explain in a concise form the works or discoveries of Archimedes, partly because he wrote on nearly all the mathematical subjects then known, and partly because his writings are contained in a series of disconnected monographs. Thus, while Euclid aimed at producing systematic treatises which could be understood by all students who had attained a certain level of education, Archimedes wrote a number of brilliant essays addressed chiefly to the most educated mathematicians of the day. The work for which he is perhaps now best known is his treatment of the mechanics of solids and fluids, but he and his contemporaries esteemed his geometrical discoveries of the quadrature of a parabolic area and of a spherical surface, and his rule for finding the volume of a sphere as more remarkable, while at somewhat later time his numerous mechanical inventions excited most attention. On plane geometry the extant work of Archimedes are three in number, namely (a) the measure of the circle, (b) the quadrature of the parabola, and (c) one on spirals. The measure of the circle contains three propositions. In the first proposition Archimedes proves that the area is the same as that of a right angled triangle whose sides are equal respectively to the radius and the circumference of the circle, i.e. the area is equal to 1/2 a multiplied by 2 pi a. In the second proposition he shews that the ratio pi a squared to 2 times a all squared equals 11 to 14 very nearly. And next, the third proposition, that pi is less than 3 1/7 and greater than 3 and 10/71. These theorems are of course proved geometrically. To demonstrate the two latter propositions he inscribes and circumscribes about a circle regular polygons of 96 sides, calculates their perimeters, and then assumes the circumference of the circle to lie between them. It would seem from the proof that he had some at present unknown method of extracting the square roots of numbers approximately. (b) The quadrature of the parabola contains 24 propositions. Archimedes begins his work, which was sent to Dositheus, by establishing some properties of conics (propositions 1 through 5). He then states correctly the area cut off from a parabola by any chord, and gives proof which rests on a preliminary mechanical experiment of the ratio of areas which balance when suspended from the arms of a lever (propositions 6 through 17). And lastly he gives a geometrical demonstration of this result (propositions 18 through 24). The latter is of course based on the method of exhaustions, but for brevity I will, in quoting it, use the method of limits. Let the area of the parabola, see figure on next page, be bounded by the chord PQ. Draw VM, the diameter to the chord PQ by a previous proposition. V is more remote from PQ than any other point on the arc PVQ. Let the area of the triangle PVQ be denoted by delta. In the segments bounded by VP and VQ, inscribe triangles in the same way as the triangle PVQ was inscribed in the given segment. Each of these triangles is, by a previous proposition of his, equal to 1/8 delta, and their sum is therefore 1/4 delta. Similarly, in the four segments left inscribed triangles, their sum will be 1/16 delta. Proceeding in this way, the area of the given segment is shewn to be equal to the limit delta plus delta over 4 plus delta over 16 plus ... plus delta over 4 to the power n plus ... when n is indefinitely large. The problem is therefore reduced to finding the sum of a geometrical series. This he effects as follows. Let a, b, c, d, e, f, g, h, i, j, and k be a series of magnitudes such that each is 1/4 of that which precedes it. Take magnitudes lowercase b, lowercase c up to lowercase k equal respectively to 1/3 capital B, 1/3 capital C, all the way to 1/3 capital K. Then big B plus little b equals 1/3 big A. Big C plus little c equals 1/3 big B, all the way to big K plus little k equals 1/3 big J. Hence the sum big B plus big C all the way to big K plus little b plus little c all the way to little k equals 1/3 of big A plus big B all the way to big J. But by hypothesis, little b plus little c dot 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 plus little j plus little k equals 1/3 of big B plus big C all the way to big J plus 1/3 k. Therefore, big B plus big C all the way to big K plus 1/3 of big K equals 1/3 A. Therefore, big A plus big B plus big C all the way to K equals 4/3 big A minus 1/3 big K. Hence, the sum of these magnitudes exceeds 4 times the third of the largest of them by 1/3 of the smallest of them. Returning now to the problem of the quadrature of the parabola, big A stands for delta, and ultimately big K is indefinitely small. Therefore the area of the parabolic segment is 4/3 that of the triangle PVQ, or 2/3 that of the rectangle whose base is PQ and altitude of the distance V from PQ. While discussing the question of quadratures, it may be added that in the fifth and sixth propositions of his work on conoids and spheroids he determined the area of an ellipse. C. The work on spirals contains 28 propositions on the properties of the curve now known as the spiral of Archimedes. It was sent to Dositheus at Alexandria accompanied by a letter, from which it appears that Archimedes had previously sent a note of his results to Conon, who had died before he had been able to prove them. The spiral is defined by saying that the vectorial angle and the radius vector both increase uniformly, hence its equation is r equals c theta. Archimedes finds most of its properties and determines the area enclosed between the curve and the two radii vectors. This he does by, in effect, saying, in the language of the infinitesimal calculus, that the element of area is greater than 1/2 r squared d theta and less than 1/2 quantity r plus dr squared d theta. To effect the sum of the elementary areas, he gives the two lemmas in which he sums geometrically the series a squared plus 2a all squared plus 3a all squared dot 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 plus na all squared proposition 10 and a plus 2a plus 3a plus dot 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 plus na proposition 11. D. In addition to these he wrote a small treatise on the geometrical methods and works on parallel lines, triangles, the properties of a right angle triangle, data, the heptagon inscribed in a circle, and systems of circles touching one another. Possibly he wrote others too. These are all lost, but it is probable that fragments of 4 of the propositions in the last mentioned work are preserved in a Latin translation from an Arabic manuscript entitled Lemmas of Archimedes. 2. On geometry of 3 dimensions, the extant works of Archimedes are 2 in number, namely A. the sphere and cylinder, and B. conoids and spheroids. A. The sphere and cylinder contains 60 propositions arranged in 2 books. Archimedes sent this, like so many of his works, to Dositheus at Alexandria, but he seems to have played a practical joke on his friends there, for he purposely misstated some of his results to deceive those vain geometricians who say they have found everything but never give their proofs, and sometimes claim they have discovered what is impossible. He regarded this work as his masterpiece. It is too long for me to give an analysis of its contents, but I remark in passing that in it he finds expressions for the surface and volume of a pyramid, of a cone, and of a sphere, as well as that of the figures produced by the revolution of polygons inscribed in a circle about the diameter of the circle. There are several other propositions on areas and volumes, which perhaps the most striking is the 10th proposition of the second book, namely, that of all spherical segments whose surfaces are equal to the hemisphere has the greatest volume. In the second proposition of the second book he enunciates the remarkable theorem that a line of length a can be divided so that the ratio a minus x to b equals the ratio 4a squared to 9x squared, where b is a given length, only if b be less than 1/3 a, that is to say, the cubic equation x cubed minus ax squared plus 4/9 a squared b equals 0 can have a real and positive root only if a be greater than 3b. This proposition was required to complete his solution of the problem to divide a given sphere by a plane so that the volumes of the segments should be in a given ratio. One very simple cubic equation occurs in the arithmetic of Diophantus, but with that exception no such equation appears again in the history of European mathematics for more than 1000 years. B. The conoids and spheroids contain 40 propositions on quadrics of revolution sent to Dositheus in Alexandria, mostly concerned with an investigation of their volumes. C. Archimedes also wrote a treatise on the 13 semi-regular polyhedrons, that is, solids contained by irregular but dissimilar polygons. This work is lost. 3. On arithmetic, Archimedes wrote 2 papers. One, addressed to Zeuxippus, was on the principle of numeration. This is now lost. The other, addressed to Gilon, was called Tamiz, the sand reckoner, and in this he meets an objection which has been urged against his first paper. The object of the first paper had been to suggest a convenient system by which numbers of any magnitude could be represented, and it would seem that some philosophers at Syracuse had doubted whether the system was practicable. Archimedes said people talk of the sand on the Sicilian shore as something beyond the power of calculation, but he can estimate it, and further he will illustrate the power of his method by finding a superior limit to the number of grains of sand which would fill the whole universe, i.e. a sphere whose centre is the earth and whose radius is the distance to the sun. He begins by saying that in ordinary Greek nomenclature it was only possible to express the numbers from 1 up to 10 to the power 8. These are expressed in what he says he may call units of the first order. If 10 to the power 8 be termed a unit of the second order, any number from 10 to the power 8 to 10 to the power 16 can be expressed as so many units of the second order plus so many units of the first order. If 10 to the 16 be a unit of the third order, any number up to 10 to the power 24 can then be expressed, and so on. Assuming that 10,000 grains of sand occupy a sphere whose radius is not less than 1/80th of a finger breadth, and that the diameter of the universe is not greater than 10 to the power 10 stadia, he finds that the number of grains of sand required to fill the universe is less than 10 to the power of 63. Probably this system of numeration was suggested merely as a scientific curiosity. The Greek system of numeration with which we are acquainted has only recently been introduced, most likely at Alexandria, and was sufficient for all the purposes for which the Greeks then required numbers, and Archimedes used that system in all his papers. On the other hand, it has been conjectured that Archimedes and Apollonius had some symbolism based on the decimal system for their own investigations, and it is possible that it was the one here sketched out. The units suggested by Archimedes form a geometrical progression, having 10 to the 8th for the radix. He incidentally adds that it will be convenient to remember that the product of the mth and nth terms of a geometrical progression whose first term is unity is equal to the m plus nth term of the series, i.e. that r to the m times r to the n equals r to the m plus n. To these two arithmetical papers I may add the following celebrated problem with which he sent to the Alexandrian mathematicians. The sun had a herd of bulls and cows, all of which were either white, grey, dun, or piebald. The number of piebald bulls was less than the number of white bulls by 5/6 of the number of grey bulls, but it was less than the number of grey bulls by 9/20 of the number of dun bulls, and it was less than the number of dun bulls by 13/42 of the number of white bulls. The number of white cows was 7/12 of the number of grey cattle, bulls and cows. The number of grey cows was 9/20 of the number of dun cattle, and the number of dun cows was 11/30 of the number of piebald cattle, and the number of piebald cows was 13/42 of the number of white cattle. The problem was to find the composition of the herd. The problem is intermediate, but the solution in lowest integers is number of white bulls 10,366,482, grey bulls 7,460,514, dun bulls 7,358,060, piebald bulls 4,149,387, white cows 7,206,360, grey cows 4,893,246, dun cows 3,515,820, piebald cows 5,439,213. In the classical solution attributed to Archimedes, these numbers are multiplied by 80. Nesselmann believes, from internal evidence, that the problem has been falsely attributed to Archimedes. It certainly is unlike his extant work, but it was attributed to him among the ancients, and is generally thought to be genuine, though possibly it has come down to us in a modified form. It is in verse, and a later copyist has added the additional conditions that the sum of the white and grey bulls shall be a square number, and the sum of the piebald and dun bulls be a triangular number. It is perhaps worthy of note that in the enunciation the fractions are represented as a sum of fractions whose numerators are unity. Thus Archimedes wrote 1/7 plus 1/6 instead of 13/42, in the same way as Ahmes would have done. See above, page 4. 4. On mechanics, the extant work of Archimedes are two in number, namely A. his mechanics, and B. his hydrostatics. A. The Mechanics is a work on statics with a spherical reference to the equilibrium of plane laminas and to properties of their centers of gravity. It consists of 25 propositions in 2 books. In the first part of book 1, most of the elementary properties of the center of gravity are proved, propositions 1 through 8. And in the remainder of book 1, propositions 9 through 15, and in book 2, the centers of gravity of a variety of plane areas such as parallelograms, triangles, trapeziums, and parabolic areas are determined. B. Archimedes also wrote a treatise on levers, and perhaps on all the mechanical machines. The book is lost, but we know from Pappus that it contained a discussion on how a given weight could be moved with a given power. It was this work probably that Archimedes discussed the theory of a certain compound pulley consisting of 3 or more simple pulleys which he had invented and which was used in some public works in Syracuse. It is well known that he boasted that if he had but a fixed fulcrum he could move the whole earth, see above, page 66, and a commentator of later date said that he added he would do it by using a compound pulley. C. His works on floating bodies contain 19 propositions in 2 books, and was the first attempt to apply mathematical reasoning to hydrostatics. The story of the manner in which his attention was directed to the subject is told by Vitruvius. Hiero, the king of Syracuse, had given some gold to a goldsmith to make into a crown. The crown was delivered made up and of the proper weight, but it was suspected that the workman had appropriated a considerable proportion of the gold, replacing it by an equal weight of silver. Archimedes was thereupon consulted. Shortly afterwards, when in the public baths, he noticed that his body was pressured upwards by a force which increased the more completely he was immersed in the water. Recognizing the value of the observation, he rushed out just as he was, and ran home through the streets, shouting, "Eureka! Eureka! I have found it! I have found it!" There to follow a later account on making accurate experiments, he found that when equal weights of gold and silver were weighed in water they no longer appeared equal. Each seemed lighter than before by the weight of the water it displaced, and as the silver was more bulky than the gold, its weight was more diminished. Hence, if on a balance he weighed the crown against an equal weight of gold then immersed the whole in water, the gold would outweigh the crown if any silver had been used in its construction. Tradition says that the goldsmith was found to be fraudulent. Archimedes began the work by proving that the surface of a fluid at rest is spherical, the centre of the sphere being at the centre of the earth. He then proved that the pressure of the fluid on a body wholly or partially immersed is equal to the weight of the fluid displaced, and thence found the position of the equilibrium of a floating body, which he illustrated by spherical segments and paraboloids of revolution floating on a fluid. Some of the latter problems involve geometrical reasoning of great complexity. The following is a fair specimen of the questions considered. A solid in the shape of a paraboloid of revolution of height h and latus rectum 4a floats in water, with its vertex immersed and its base wholly above the surface. If the equilibrium be possible when the axis is not vertical, then the density of the body must be less than h minus 3a squared divided by h squared. Book 2, proposition 4. When it is recollected that Archimedes was unacquainted with trigonometry or analytical geometry, the fact that he could discover and prove a proposition such as that just quoted will serve as an illustration of his powers of analysis. As an illustration of the influence of Archimedes on the history of mathematics, I may mention that the science of statics rested on his theory of the lever until 1586, when Stevinus published his treatise on statics, and no distinct advance was made in the theory of hydrostatics until Stevinus in the same work investigated the laws which regulate the pressure of fluids. See below, page 248. 5. We know both from occasional references in his works and from remarks by other writers that Archimedes was largely occupied in astronomical observations. He wrote a book, Peris Feriopis, on the construction of a celestial sphere, which is lost, and he constructed a sphere of the stars and an orrery. These, after the capture of Syracuse, were taken by Marcellus to Rome, and were preserved as curiosities for at least 200 or 300 years. This mere catalogue of his works will shew how wonderful were his achievements, but no one who has not actually read some of his writings can form a just appreciation of his extraordinary ability. This will be still further increased if we recollect that the only principles used by Archimedes, in addition to those contained in Euclid's Elements and Conic sections, are that all lines like ACB, ADB connecting 2 points A and B, the straight line is the shortest, and that of the curved lines the inner one ADB is shorter than the outer one ACB, together with 2 similar statements for space of 3 dimensions. In the old and medieval world Archimedes was unanimously reckoned as the first of mathematicians, and in the modern world there is no one but Newton who can be compared with him. Perhaps the best tribute to his fame is the fact that those writers who have spoken most highly of his work and ability are those who have been themselves the most distinguished men of their generation. End of chapter 4, part 2. Chapter 4, Part 3 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball. Chapter 4. The First Alexandrian School, circa 300 BC to 30 BC. Part 3. Apollonius. The third great mathematician of this century was Apollonius of Perga, who is chiefly celebrated for having produced a systematic treatise on the conic sections which not only included all that was previously known about them, but immensely extended the knowledge of these curves. This work was accepted at once as the standard textbook on the subject and completely superseded the previous treatises on Menaechmus, Aristeas, and Euclid, which until that time had been in general use. We know very little about Apollonius himself. He was born about 260 BC and died about 200 BC. He studied in Alexandria for many years, and probably lectured there. He is represented by Pappus as vain, jealous of the reputation of others, and ready to seize every opportunity to depreciate them. It is curious that while we know next to nothing of his life or that of his contemporary Eratosthenes, yet their nicknames, which were respectively Epsilon and Beta, have come down to us. Dr. Gow has ingeniously suggested that the lecture rooms at Alexandria were numbered, and that they always used the rooms numbered 5 and 2 respectively. Apollonius spent some years at Pergamum in Pamphylia, where a university had recently established and endowed in imitation of that at Alexandria. There he met Eudemus and Attalus, who he subsequently sent each book of his conics as it came out with an explanatory note. He returned to Alexandria and lived out there until his death, which was nearly contemporaneous with that of Archimedes. In his great work on conic sections he so thoroughly investigated the properties of these curves that he left but little for his successors to add. But his proofs are long and involved, and I think that most readers will be content to accept a short analysis of his work and the assurance that his demonstrations are valid. Dr. Zeuthen believes that many of the properties enunciated were obtained in the first instance by the use of coordinate geometry, and that the demonstrations were translated subsequently into a geometrical form. If this be so, we must suppose that from the classical writers were familiar with some branches of analytical geometry. Dr. Zeuthen says the use of orthogonal and oblique coordinates and of transformations depending on abridged notation, that this knowledge was confined to a limited school and was finally lost. This is a mere conjecture and is unsupported by any direct evidence, but it has been accepted by many critics as affording an explanation of the extent and arrangement of the work. The treatise contained about 400 propositions and was divided into 8 books. We have the Greek text of the first 4 of these, and we also possess copies of the commentaries by Pappus and Eutychius on the whole work. In the 9th century, an Arabic translation was made of the first 7 books, which were the only ones then extant. We have 2 manuscripts of this version. The 8th book is lost. In the letter to Eudemus which accompanied the first book, Apollonius says that he undertook the work at the request of Naucrates, a geometrician who had been staying with him at Alexandria, and, though he had been given some of his friends a rough draft of it, he preferred to revise it carefully before sending it to Pergamum. In the note which accompanied the next book, he asked Eudemus to read it and communicate it to others who can understand it, and in particular to Philonides, a certain geometrician whom the author had met at Ephesus. The first four books deal with the elements of the subject, and of these the first three are founded on Euclid's previous work, which was itself based on the earlier treatises by Menaechmus and Aristeas. Heraclides asserts that much of the matter in these books was stolen from an unpublished work of Archimedes, but a critical examination by Heiberg has shewn that this is improbable. Apollonius begins by defining a cone and a circular base. He then investigates the different plane sections of it and shews that they are divisible into three kinds of curves which he calls ellipses, parabolas, and hyperbolas. He proves the proposition that if A prime be the vertices of a conic, and if P be any point and PM the perpendicular drawn from P on A prime, then in the usual notation the ratio MP squared to AM times MA prime is constant in an ellipse or hyperbola, and the ratio MP squared to AM is constant in a parabola. These are the characteristic properties on which almost all of the rest of the work is based. He next shews that if A be the vertex, L be the latus rectum, and if AM and MP be the abscissa and ordinate of any point on a conic, then MP squared is less than, equal to, or greater than L. AM, according as the conic is an ellipse, parabola, or hyperbola, hence the names which he gave to the curves by which they are still known. He had no idea of the directrix, and was not aware that the parabola had a focus. But with the exception of the propositions which involve these, his first three books contain most of the propositions which are found in modern textbooks. In the fourth book he develops the theory of lines cut harmonically and treats the points of intersection of systems of conics. In the fifth book he commences with the theory of maxima and minima, applies it to find the center of curvature at any point of a conic and the evolute of a curve, and discusses the number of normals which can be drawn from a point to a conic. In the sixth book he treats of similar conics. The seventh and eighth books were given up to a discussion of conjugate diameters, and the latter of these was conjecturally restored by E. Halley in 1710. The verbose and tedious explanations make the book repulsive to most modern readers, but the logical arrangement and reasoning are unexceptionable, and it has not been unfitly described as the crown of Greek geometry. It is the work on which the reputation of Apollonius rests, and it earned for him the name the Great Geometrician. Besides this immense treatise he wrote a number of shorter works. Of course the books were written in Greek, but they are usually referred to by their Latin titles. Those about which we know anything are enumerated below. He was the author of a work on the problem: given two coplanar straight lines a and b drawn through fixed points A and B, to draw a line OA b from a given point O outside of them, cutting them in a and b, so that a shall be to b in a given ratio. He reduced the question to 77 separate cases, and gave an appropriate solution with the aid of conics for each case. This was published by E. Halley, translated from Arabic copy, in 1706. He also wrote a treatise on Dissectione Spatii, restored by E. Halley in 1706, on the same problem under the condition that the rectangle big B dot big B was given. He wrote another entitled Dissectione Determinata, restored by R. Simpson, Glasgow, 1749, dealing with problems such as to find a point P in a given straight line AB so that PA squared shall be to PB in a given ratio. He wrote another De Tactionibus, restored by Vieta in 1600, see below, page 238, on the construction of a circle which shall touch three given circles. Another work was his De Inclinationibus, restored by M. Getaldi, Venice, 1607, on the problem to draw a line so that the intercept between two given lines or the circumference of two given circles shall be of a given length. He was also the author of a treatise in 3 books on plane loci, De Locis Planis, restored by Fermat in 1637 and by R. Simpson in 1746, and of another on the regular solids. And lastly he wrote a treatise on unclassed incommensurables, being a commentary on the 10th book of Euclid. It is believed that in one or more of the lost books he used the method of conical projections. Besides these geometrical works, he wrote on the methods of arithmetical calculation. All that we know of this is derived from some remarks of Pappus. Fridolin thinks that it was merely a sort of ready reckoner. It would, however, seem that Apollonius here suggested a system of numeration similar to that proposed by Archimedes, see above, but proceeding by tetrads instead of octads, and described a notation for it. It will be noticed that our modern notation goes by hexads. A million is 10 to the 6th, a billion, that is, a million, is 10 to the 12th, and a trillion, that is, a million billion, is 10 to the 18, etc. It is not impossible that Apollonius also pointed out that a decimal system of notation involving only 9 symbols would facilitate numerical multiplications. Apollonius was interested in astronomy and wrote a book on the stations and regressions of the planets, of which Ptolemy made some use in writing in the Almagest. He also wrote a treatise on the use and theory of the screw in statics. This is a long list, but I should propose that most of these works were short tracts on special points. Like so many of his predecessors, he too gave a construction for finding two mean proportionals between two given lines and thereby duplicating the cube. It was as follows. Let OA and OB be the given lines. Construct a rectangle OADB of which they are adjacent sides. Draw a diagonal from A to B of center point C. Then, if with C as the center, we can describe a circle cutting OA produced in little a and cutting OB produced in little b, so that little a, big D, little b shall be a straight line, the problem is effected. For it is easily shewn that O little a times A little a plus CA squared equals C little a squared. Similarly, O little b times B little b plus CB squared equals C little b squared. Hence, O little a times A little a equals O little b times B little b. That is, the ratio O little a to O little b equals the ratio B little b to A little a. But by similar triangles, BD to B little b equals the ratio O little a to O little b, which is also equal to the ratio A little a to AD. Therefore, OA to B little b equals B little b to A little a, which is also equal to A little a to OB. That is, B little b and O little a are the two mean proportionals between OA and OB. It is impossible to construct the circle whose center is C by Euclidean geometry, but Apollonius gave a mechanical way of describing it. This construction is quoted by several Arabic writers. In one of the most brilliant passages of his Aperçu historique, Chasles remarks that while Archimedes and Apollonius were the most able geometricians of the Old World, their works are distinguished by a contrast which runs through the whole subsequent history of geometry. Archimedes, in attacking the problem of the quadrature of curved linear areas, laid the foundation of the geometry which rests on measurements. This naturally gave rise to the infinitesimal calculus, and in fact the method of exhaustions as used by Archimedes does not differ in principle from the method of limits used by Newton. Apollonius, on the other hand, in investigating the properties of conic sections by means of transversals involving the ratio of rectilineal distances and of perspective, laid the foundations of the geometry of form and position. Eratosthenes. Among the contemporaries of Archimedes and Apollonius I may mention Eratosthenes. Born at Cyrene in 275 BC, he was educated at Alexandria, perhaps at the same time as Archimedes, of whom he was a personal friend, and Athens, and was at an early age entrusted with the care of the university library at Alexandria, a post which probably he occupied till his death. He was the admirable Christian of his age, and distinguished for his athletic achievements not less than for his literary and scientific attainments. He was also something of a poet. He lost sight by ophthalmia, then as now, a curse of the valley of the Nile, and refusing to live when he was no longer able to read, he committed suicide by starvation in 194 BC. In science he was chiefly interested in astronomy and geodesy, and he constructed various astronomical instruments which were used for some centuries at the university. He introduced the calendar, now known as Julian, in which every fourth year contains 366 days, and he determined the obliquity of the ecliptic as 23 degrees 51 minutes and 20 seconds. He measured the length of a degree on the earth's surface, making it to be about 79 miles, which is actually too long by nearly 10 miles, and thence calculated the circumference of the earth to be 252,000 stadia, which, if we take the Olympic stadium of 202 1/4 yards, is equivalent to saying that the radius is about 4,600 miles. The principle used in the determination is correct. Of Eratosthenes' work in mathematics we have two extant illustrations, one in a description of an instrument to duplicate a cube, and the other in the rule he gave for constructing a table of prime numbers. The former is given in many books. The latter, called the Sieve of Eratosthenes, was as follows. Write down all the numbers from 1 upwards. Then every second number from 2 is a multiple of 2 and may be cancelled. Every third number from 3 is a multiple of 3 and may be cancelled. Every fifth number from 5 is a multiple of 5 and may be cancelled, and so on. It has been estimated that it would involve working for about 300 hours to thus find the primes in the numbers from 1 to 1,000,000. The labour of determining whether any particular number is prime may be however much shortened by observing that if a number can be expressed as the product of two factors, one must be less and the other greater than the square root of the number, unless the number is the square of a prime, in which case the two factors are equal. Hence every composite number must be divisible by a prime number which is not greater than its square root. The 2nd century before Christ. The 3rd century before Christ, which opens with the career of Euclid and closes with the death of Apollonius, is the most brilliant era in the history of Greek mathematics. But the great mathematicians of that century were geometricians, and under their influence attention was directed almost solely to that branch of mathematics. With the methods they used, and to which their successors were by tradition confined, it was hardly possible to make any further great advance. To fill up a few details in a work that was completed in its essential parts was all that could be effected. It was not till after the lapse of nearly 1800 years that the genius of Descartes open the way to any further progress in geometry, and I therefore pass over the numerous writers who followed Apollonius but with slight mention. Indeed, it may be said roughly that during the next 1000 years Pappus was the sole geometrician of any great ability, and during this long period almost the only other pure mathematician of exceptional genius was Hipparchus and Ptolemy, who laid the foundations of trigonometry, and Diophantus, who laid those of algebra. Early in the 2nd century, circa 180 BC, we find the names of 3 mathematicians, Hypsicles, Nicomedes, and Diocles, who were in their own day famous. Hypsicles. The first of these was Hypsicles, who added a 14th book to Euclid's Elements in which the regular solids were discussed. In another small work entitled Risings, Hypsicles developed the theory of arithmetical progressions which had been so strangely neglected by the earlier mathematicians, and here for the first time in Greek mathematics we find a right angle divided in the Babylonian manner into 90 degrees. Possibly Eratosthenes may have previously estimated angles by the number of degrees they contain, but this is only a matter of conjecture. Nicomedes. The second was Nicomedes, who invented the curve known as the conchoid, or the shell-shaped curve. If from a fixed point S a line be drawn cutting a given fixed straight line in Q, and if P be taken on SQ so that the length QP is constant, say D, then the locus of P is the conchoid. Its equation may be put in the form of R equals A multiplied by secant theta plus or minus D. It is easy with its aid to trisect a given angle or to duplicate a cube, and this no doubt was the cause of its invention. Diocles. The third of these mathematicians was Diocles, the inventor of the curve known as the cissoid, or the ivy-shaped curve, which, like the conchoid, was used to give a solution of the duplication problem. He defined it thus: let AOA prime and BOB prime be 2 fixed diameters of a circle at right angles to one another. Draw 2 chords QQ prime and RR prime parallel to BOB prime and equidistant from it. Then the locus of the intersection of AR and QQ prime will be the cissoid. Its equation can be expressed in the form of y squared multiplied by the quantity 2a minus x close bracket equals x cubed. Diocles also solved by the aid of conic sections a problem which had been proposed by Archimedes, namely to draw a plane which will divide a sphere into 2 parts whose volumes shall bear to one another a given ratio. Perseus, Zenodorus. About a quarter of a century later, say about 150 BC, Perseus investigated the various plane sections of the anchor ring, see above, and Zenodorus wrote a treatise on isoperimetrical figures. Part of the latter work has been preserved. One proposition which will serve to shew the nature of the problems discussed is that of segments of circles having equal arcs, the semicircle is the greatest. Toward the close of this century we find 2 mathematicians who, by turning their attention to new subjects, gave a fresh stimulus to the study of mathematics. These were Hipparchus and Hero. Hipparchus. Hipparchus was the most eminent of Greek astronomers, his chief predecessors being Eudoxus, Aristarchus, Archimedes, and Eratosthenes. Hipparchus is said to have been born about 160 BC at Nicaea in Bithynia. It is probable that he spent some years at Alexandria, but he finally took up his abode at Rhodes, where he made most of his observations. Delambre has obtained an ingenious confirmation of the tradition which asserted that Hipparchus lived in the 2nd century before Christ. Hipparchus in one place says that the longitude of a certain star Nu Canis observed by him was exactly 90 degrees, and it should be noted that he was an extremely careful observer. Now in 1750 it was 116 degrees 4 minutes 10 seconds, and as the first point of Aries regredes at the rate of 50.2 seconds a year, the observation was made at about 120 BC. Except for a short commentary on a poem of Aratus dealing with astronomy, all his works are lost. But Ptolemy's great treatise, the Almagest, was founded on the observation and writings of Hipparchus, and from the notes there given we infer that the chief discoveries of Hipparchus were as follows. He determined the duration of the year to within 6 minutes of its true value. He calculated the inclination of the ecliptic and equator as 23 degrees 51 minutes, and it was actually at that time 23 degrees 46 minutes. He estimated the annual precession of the equinoxes as 59 seconds, and it is 50.2 seconds. He stated the lunar parallax as 57 minutes, which is nearly correct. He worked out the eccentricity of the solar orbit as 1 over 24. It is very approximately 1 over 30. He determined the perigee and mean motion of the sun and of the moon, and he calculated the extent of the shifting of the plane of the moon's motion. Finally, he obtained the synodic periods of the 5 planets then known. I leave the details of his observations and calculations to writers who deal specially with astronomy such as Delambre, but it may be fairly said that this work placed the subject for the first time on a scientific basis. To account for the lunar motion, Hipparchus supposed that the moon to move with uniform velocity in a circle, the earth occupying a position near but not at the centre of this circle. This is equivalent to saying that the orbit is an epicycle of the first order. The longitude of the moon obtained on this hypothesis is correct to the first order of small quantities for a few revolutions. To make it correct for any length of time, Hipparchus further supposed that the apse line moved forward about 3 degrees per month, thus giving it a correction for evection. He explained the motion of the sun in a similar manner. This theory accounted for all of the facts which could be determined with the instruments then in use, and in particular enabled him to calculate the details of eclipses with considerable accuracy. He commenced a series of planetary observations to enable his successors to frame a theory to account for their motions, and with this great perspicacity he predicted that to do this it would be necessary to introduce epicycles of a higher order, that is, to introduce 3 or more circles, the centre of each successive one moving uniformly on the circumference of the preceding one. He also formed the list of the fixed stars. It is said that the sudden appearance in the heavens of a new and brilliant star called his attention to the need of such a catalogue, and the appearance of such a star during his lifetime is confirmed by Chinese records. No further advance in the theory of astronomy was made until the time of Copernicus, though the principles laid down by Hipparchus were extended and worked out in detail by Ptolemy. Investigations such as these naturally led to trigonometry, and Hipparchus must be credited with the invention of that subject. It is known that in plane trigonometry he constructed a table of chords and arcs, which is practically the same as one of natural sines, and that in spherical trigonometry he had some method of solving triangles, but his works are lost and we can give no details. It is believed, however, that the elegant theorem printed as Euclid's 6d and generally known as Ptolemy's theorem is due to Hipparchus and was copied from him by Ptolemy. It contains implicitly the addition formulae for sine of a plus b or sine of a minus b, and cosine a plus b and cosine a minus b. And Carnot shewed how the whole of elementary plane trigonometry could be deduced from it. I ought also to add that Hipparchus was the first to indicate the position of a place on the earth by means of its latitude and longitude. Hero. The second of these mathematicians was Hero of Alexandria, circa 125 BC, who placed engineering and land surveying on a scientific basis. He was a pupil of Ctesibus, who invented several ingenious machines, and is alluded to as if he were a mathematician of note. In pure mathematics, Hero's principal and most characteristic work consists of 1. Some elementary geometry with applications to the determination of the areas of fields of given shapes. 2. Propositions on finding the volumes of certain solids, with applications to theatres, baths, banquet halls, and so on. 3. A rule to find the height of an inaccessible object, and 4. Tables of weights and measures. He invented a solution of the duplication problem, which is practically the same as that which Apollonius had already discovered. See above. Some commentators think that he knew how to solve a quadratic equation even when the coefficients were not numerical, but this is doubtful. He proved the formula that the area of a triangle is equal to the square root of the expression s times the quantity s minus a times the quantity s minus b times the quantity s minus c, where s is the semi-perimeter and abc the lengths of the sides, and gave as an illustration the triangle whose sides were 13, 14, and 15. He was evidently acquainted with the trigonometry of Hipparchus, but he nowhere quotes a formula or expressly uses the value of the sine, and it is probable that like the later Greeks he regarded trigonometry as forming an introduction to and being an integral part of astronomy. The following is the manner in which he solved the problem to find the area of the triangle ABC, the lengths whose sides are a, b, c. Let s be the semi-perimeter of the triangle. Let the inscribed circle touch the sides in points D, E, F, and let O be its center. On BC produced, take H, so that CH equals AF, and therefore BH equals s. Draw OK at right angles to OB and CK at right angles to BC. Let them meet in K. The area ABC, or the triangle, is equal to the sum of the areas OBC, OCA, and OAB, which is equal to 1/2 a r plus 1/2 b r plus 1/2 c r equals s r. That is equal to BH times OD. He then shews that the angle OAF equals the angle CBK, hence the triangles OAF and CBK are similar. Therefore, the ratio BC to CK equals the ratio AF to OF, which equals the ratio CH to OD. Therefore, the ratio BC to CH equals the ratio CK to OD, which equals the ratio CL to LD. Therefore, BH to CH equals CD to LD. Therefore, the ratio BH squared to CH times BH equals the ratio CD times BD to LD times BD equals the ratio CD times BD to OD squared. Hence the triangle BH times OD equals the square root CH times BH times CD times BD, which also is equal to the square root of the expression s times the quantity s minus a times the quantity s minus c times the quantity s minus b. In applied mathematics, Hero discussed the center of gravity, the 5 simple machines, and the problem of moving a given weight with a given power, and in one place he suggested a way in which the power of a catapult could be tripled. He also wrote on the theory of hydraulic machines. He described a theodolite and cyclometer and pointed out various problems in surveying for which they would be useful. But the most interesting of his smaller works are his Pneumatik and Automata, containing descriptions of about 100 small machines and mechanical toys, many of which are very ingenious. In the former there is an account of a small stationary steam engine, which is of the form now known as Avery's patent. It was in common use in Scotland at the beginning of this century, but is not so economical as the form introduced by Watt. There is also an account of a double forcing pump to be used as a fire engine. It is probable that in the hands of Hero these instruments never got beyond models. It is only recently that general attention has been directed to his discoveries, though Arago had alluded to them in his Eloge on Watt. All this is very different from the classical geometry and arithmetic of Euclid or the mechanics of Archimedes. Hero did nothing to extend a knowledge of abstract mathematics. He learned all that the textbooks of the day could teach him, but he was interested in science only on account of its practical applications, and so long as his results were true he cared nothing for the logical accuracy of the process by which he arrived at them. Thus in finding the area of a triangle he took the square root of the product of four lines. The classical Greek geometricians permitted the use of the square and the cube of a line because these could be represented geometrically, but a figure of four dimensions is inconceivable, and certainly they would have rejected a proof which involves such a conception. It is questionable if Hero or his contemporaries were aware of the existence of the Rhind papyrus, but it would seem that treatises found on it and of a similar character were then current in Egypt, and while I am passing these sheets through the press the manuscript of a textbook of this kind, though most likely some 8 centuries or so later in date, has been discovered and reproduced. Doubtless it was from some such source that Hero drew his inspiration. 2 or 3 reasons have led modern commentators to think that Hero, who was born in Alexandria, was a native Egyptian. If this be so, it affords an interesting illustration of the permanence of racial characteristics and traditions. Hero spoke and wrote Greek, and it is believed that he was brought up under Greek influence, yet the rules he gives, his methods of proof, the figures he draws, the questions he attacks, and even the phrases of which he makes use, recall the earlier work of Ahmes. The 1st century before Christ. The successors of Hipparchus and Hero did not avail of themselves of the opportunity thus opened of investigating new subjects, but fell back on the well-worn subject of geometry. Among the more eminent of these later geometricians were Theodosius and Dionysodorus, both of whom flourished about 50 BC. Theodosius was the author of a complete treatise on the geometry of the sphere, which was edited by Barrow, Cambridge, 1675, and Nizza, Berlin, 1852. He also wrote 2 works on astronomy, which were then published by Dasypodius in 1572. Dionysodorus is known to us only by his solution of the problem to divide a hemisphere by a plane parallel to its base into 2 parts, whose volumes shall be in a given ratio. Like the solution by Diocles of the similar problem for a sphere above alluded to, it was effected by the aid of conic sections. It is reproduced in Suter's Geschichte der mathematischen Wissenschaften, page 101. Pliny says that Dionysodorus determined the length of the radius of the earth approximately as 42,000 stadia, which, if we take the Olympic stadium of 202 1/4 yards, it is a little less than 5,000 miles. We do not know how it was obtained. This may be compared with the result given by Eratosthenes, see above. End of the first Alexandrian school. The administration of Egypt was definitely undertaken by Rome in 30 BC. The closing years of the dynasty of the Ptolemies and the earlier years of the Roman occupation of the country were marked by much disorder, civil and political. The studies of the university were naturally interrupted, and it is customary to take this time as the close of the first Alexandrian school. End of chapter 4. Read by Paul King, pjk.scripps.mit.edu/pkj. Chapter 5 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse-Ball. Chapter 5. The Second Alexandrian School, 30 BC to 641 AD. I concluded the last chapter by stating that the first school of Alexandria may be said to have come to an end at about the same time as the country lost its nominal independence. But although the schools of Alexandria suffered from the disturbances which affected the whole Roman world in the transition, in fact, if not in name, from a republic to empire, there was no break of continuity. The teaching in the university was never abandoned, and as soon as order was again established, students began once more to flock to Alexandria. This time of confusion was however contemporaneous with a change in the prevalent attitudes of philosophy, which thenceforward were mostly Neoplatonic and Neo-Pythagorean, and it therefore fitly marks the commencement of a new period. These mystical opinions reacted on the mathematical school, and this may partially account for the paucity of good work. Though Greek influence was still predominant and the Greek language was always used, Alexandria now became the intellectual centre for most of the Mediterranean nations which were subject to Rome. It should be added, however, that the direct connection with it of many of the mathematicians of this time is at least doubtful, but their knowledge was ultimately obtained from the Alexandrian teachers, and they are usually described as of the Second Alexandrian School. Such mathematics as were taught at Rome were derived from Greek sources, and we may therefore consider their extent in connection with this chapter. The first century after Christ. There is no doubt that throughout the first century after Christ geometry continued to be that subject in science to which most attention was devoted. But by this time it was evident that the geometry of Archimedes and Apollonius was not capable of much further extension, and such geometrical treatises as were produced consisted mostly of commentaries on the writings of the great mathematicians of a preceding age. In this century the only original works of any ability were two, by Cyrenius and one by Menelaus. Menelaus. Those by Cyrenius of Antissa, circa 70, were on the plane sections of the cone and cylinder. These were edited by Edmund Halley, Oxford, 1710. That by Menelaus of Alexandria, circa 98, was on spherical trigonometry, investigated in the Euclidean method. This was translated by E. Halley, Oxford, 1758. The fundamental theorem on which the subject is based is the relation between the six segments of the sides of a spherical triangle formed by the arc of a great circle which cuts them. Book 3, Proposition 1. Menelaus, who also wrote on the calculation of chords, i.e. on plane trigonometry, this is lost. Nicomachus, a Jew, who was born at Gerasa in 50 and died circa 110, published an arithmetic, which, the Latin translation of it, remained for 1,000 years a standard authority on the subject. The work has been edited by R. Hosch Leipzig, 1866. Geometrical demonstrations are here abandoned, and the work is a mere classification of the results then known, with numerical illustrations, the evidence of the truth of the propositions enunciated, for I cannot call them proofs, being in general an introduction from numerical instances. The object of the book is the study of the properties of numbers, and particularly of their ratios. Nicomachus commences with the usual distinctions between even, odd, prime, and perfect numbers. He next discusses fractions in a somewhat clumsy manner, and then turns to polygonal and to solid numbers, and finally treats of ratio, proportion, and the progressions. Arithmetic of this kind is usually termed Boethian, and the work of Boethius on it was a recognized textbook in the Middle Ages. The 2nd century after Christ. Theon. Another arithmetic on much the same lines as that of Nicomachus was produced by Theon of Smyrna circa 130, but it was even less scientific than that of Nicomachus. It was edited by J. de Gelder, Leyden, 1827, and by E. Hiller, Leipzig, 1878. Theon also wrote a work on astronomy which was edited by Th. Martin, Paris, 1849. Thymaridas. Another mathematician of about the same date was Thymaridas, who is worthy of notice from the fact that he is the earliest known writer who explicitly enunciated an algebraical theorem. He stated that if the sum of any number of quantities be given, and also the sum of every pair which contains one of them, then this quantity is equal to 1 n-2th part of the difference between the sum of these pairs and the first given sum. Thus if x1 plus x2 plus x3 and so on plus x sub n equals s, and if x1 plus x2 equals x2, x1 plus x3 equals s3, and x1 plus xn equals sn, then x1 equals s2 plus s3 plus and so on to sn minus big S divided by n minus 2. He does not seem to have used a symbol to denote the unknown quantity, but he always represented it by the same word, which is an approximation to symbolism. Ptolemy. About the same time as these writers, Ptolemy of Alexandria, who died in 168, produced his great work on astronomy, which will preserve his name as long as the history of science endures. This treatise is usually known as the Almagest. The name is derived from the Arabic title of al-Michisti, which is said to be a corruption of Metis Syntaxis. The work is found on the writings of Hipparchus, and though it did not sensibly advance the history of the subject, it presents the views of the older writer with a completeness and elegance which will always make it a standard treatise. We gather from it that Ptolemy made observations at Alexandria from the years 125 to 150. He, however, was but an indifferent practical astronomer, and the observations of Hipparchus are generally more accurate than those of his expounder. The work is divided into 13 books. In the first book, Ptolemy discusses the various preliminary matters, treats of trigonometry, plane and spherical, gives a table of chords, i.e. the natural signs, which is substantially correct and is probably taken from the lost work of Hipparchus, and explains the obliquity of the ecliptic. In this book he uses degrees, minutes, and seconds as measures of angles. The second book is devoted chiefly to phenomena depending on the spherical form of the Earth. He remarks that the explanations would be much simplified if the Earth was supposed to rotate on its axis once a day, but points out that this hypothesis is inconsistent with known facts. In the third book he explains the motion of the sun round the earth by means of eccentrics and epicycles. In the fourth and fifth books he treats the motion of the moon in a similar way. The sixth book is devoted to the theory of eclipses, and in it he gives 3 degrees 8 minutes and 30 seconds, that is 3 and 17 120ths, as the approximate value of pi, which is equivalent to taking it equal to 3.1416. The seventh and eighth books contain a catalogue of 1022 fixed stars determined by indicating those 3 or more that are in the same straight line. This is probably copied from Hipparchus. And another work Ptolemy added a list of annual sidereal phenomena. The remaining books are given up to the theory of the planets. This work is a splendid testimony to the ability of its author. It became at once the standard authority on astronomy, and remained so till Copernicus and Kepler shewed that the sun and not the earth must be regarded as the centre of the solar system. The idea of eccentrics and epicycles on which the theories of Hipparchus and Ptolemy are based have been often ridiculed in modern times. No doubt at a later time, when more accurate observations have been made, the necessity of introducing epicycle on epicycle in order to bring the theory into accordance with the facts made it very complicated. But De Morgan has acutely observed that in so far as the ancient astronomers supposed that it was necessary to resolve every celestial motion into a series of uniform circular motions, and they erred greatly, but that if the hypothesis be regarded as a convenient way of expressing known facts, it is not only legitimate but convenient. It was as good a theory as with their instruments and knowledge it was possible to frame, and in fact it exactly corresponds to the expression of a given function as a sum of sines or cosines, a method which is of frequent use in modern analysis. In spite of the trouble taken by Delambre, it is almost impossible to separate the results due to Hipparchus from those due to Ptolemy. But Delambre and De Morgan agree in thinking that the observations quoted, the fundamental ideas, and the explanation of the apparent solar motion are due to Hipparchus, while all the detailed explanations and calculations of the lunar planetary motions are wholly due to Ptolemy. The Almagest shews that Ptolemy was a geometrician of the first rank, though it was with the application of geometry to astronomy that he is chiefly concerned. He was, however, the author of numerous other treatises, most of which were on pure mathematics. Amongst these treatises is one on pure geometry, in which he proposed to cancel the 12th axiom of Euclid on parallel lines, and to prove it in the following manner. Let the straight line EFGH meet the two straight lines AB and CD so as to make the sum of the angles BFG and FGD equal to two right angles. It is required to prove that AB and CD are parallel. If possible, let them not be parallel, then they will meet when produced, say, at M or N. But the angle AFG is the supplement of BFG and therefore equal to FGD. Similarly, the angle FGC is equal to the angle BFG. Hence the sum of the angles AFG and FGC is equal to two right angles, and the lines BA and DC will therefore, if produced, meet at N or M. But two straight lines cannot enclose a space, and therefore AB and CD cannot meet when produced, that is, they are parallel. Conversely, if AB and CD be parallel, then AF and CG are not less parallel than FB and GD, and therefore whatever be the sum of the angles AFG and FGC, such also must be the sum of the angles FGD and BFG. But the sum of the four angles is equal to four right angles, and therefore the sum of the angles BFG and FGD must be equal to two right angles. Ptolemy wrote another work to shew that there could not be more than three dimensions in space. He also discussed orthographic and stereographic projections with special reference to the construction of sundials. He wrote on geography and stated that the length of 1 degree of latitude is 500 stadia. A book on optics and another on sound are sometimes attributed to him, but their authenticity is doubtful. The 3rd century after Christ. Pappus. Ptolemy had shewn not only that geometry could be applied to astronomy, but had indicated how new methods of analysis like trigonometry might thence be developed. He found, however, no successors to take up the work he had commenced so brilliantly, and we must look forward 150 years before we find another geometrician of any eminence. That geometrician was Pappus, who lived and taught at Alexandria about the end of the 3rd century. We know that he had numerous pupils, and it is probable that he temporarily revived an interest in the study of geometry. Pappus wrote several books, but the only one which has come down to us is his Synagogy, a collection of mathematical papers arranged in 8 books, which the first and part of the second have been lost. It has been published by F. Hulch, Berlin, 1876 to 1878. This collection was intended to be a synopsis of Greek mathematics together with comments on additional propositions by the editor. A careful comparison of various extant works with the account given of them in this book shews that it is trustworthy, and we rely largely on it for our knowledge of other work now lost. It is not arranged chronologically, but all the treatises on the same subject are grouped together, and it is most likely that it gives roughly the order in which the classical authors were read at Alexandria. Probably the first book, which is now lost, was on arithmetic. The next 4 books deal with geometry exclusive of conic sections, the 6th with astronomy including as subsidiary subjects optics and trigonometry, the 7th with analysis, conics and porisms, and the 8th with mechanics. The last 2 books contain a good deal of original work by Pappus. At the same time it should be remarked that in 2 or 3 cases he has been detected in appropriating proofs from earlier authors, and it is possible he may have done this in other cases. Subject to this suspicion, we may say that he discovered the focus in the parabola and the directrix in the conic sections, but in both cases he investigated only a few isolated properties. The earliest comprehensive account of the foci was given by Kepler, and of the directrix by Newton and Boscovich. In mechanics he shewed that the centre of mass of a triangular lamina is the same as that of an inscribed triangular lamina whose vertices divide each of the sides of the original triangle in the same ratio. He also discovered the 2 theorems on the surface and volume of a solid of revolution, which are still quoted in textbooks under his name. These are that the volume generated by the revolution of a curve about an axis is equal to the product of the area of the curve and the length of the path described by its centre of mass, and the surface is equal to the product of the perimeter of the curve and the length of the path described by its centre of mass. Pappus's best work is geometry. As an illustration of his power, I may mention that he solved, book 7, proposition 107, the problem to inscribe in a given circle a triangle whose sides produced shall pass through 3 collinear points. This question was in the 18th century generalized by Kramer, by supposing that the 3 given points to be anywhere, and was considered a difficult problem. It was sent in 1742 as a challenge to Castillon, and in 1776 he published a solution. Lagrange, Euler, L'Huillier, Fuss, and Lexell also gave solutions in 1780. A few years later the problem was set to a Neapolitan lad, Ottaviano, who was only 16 but had shewn marked mathematical ability, and he extended it to the case of a polygon of n sides which passed through n given points, and gave a solution both simple and elegant. Poncelet extended it to conics of any species and subject to other restrictions. The problem just mentioned is but a sample of many brilliant but isolated theorems which were enunciated by Pappus. His work as a whole and his comments shew that he was a geometrician of great power, but it was his misfortune to live at a time when but little interest was taken in geometry, and when the subject as then treated had been practically exhausted. Possibly a small tract on multiplication and division of sexagesimal fractions, which would seem to have been written about this time, is due to Pappus. It was edited by C. Henry, Halle, 1879, and is valuable as an illustration of practical Greek arithmetic. The 4th century after Christ. Throughout the 2nd and 3rd centuries, that is, from the time of Nicomachus, interest in geometry had steadily decreased, and more attention had been paid to the theory of numbers, though the results were in no way commensurate with the time devoted to the subject. It will be remembered that Euclid used lines as symbols for any magnitudes and investigated a number of theorems about numbers in a strictly scientific manner, but he confined himself to cases where a geometrical representation was possible. There are indications in the works of Archimedes that he was prepared to carry the subject much further. He introduced numbers into his geometrical discussions and divided lines by lines, but he was fully occupied by other researches and had no time to devote to arithmetic. Hero abandoned the geometrical representation of numbers, but he, Nicomachus, and other later writers on arithmetic did not succeed in creating any other symbolism for numbers in general, and thus when they enunciated a theorem they were content to verify it by a large number of numerical examples. They doubtless knew how to solve a quadratic equation with numerical coefficients, for, as pointed out above, geometrical solutions of the equation ax squared minus bx plus c equals 0 and ax squared plus bx minus c equals 0 are given in Euclid 6, 28, and 29, but probably this represented their highest attainment. It would seem then that in spite of the time given to its study, arithmetic and algebra had not made any sensible advance since the time of Archimedes. The problem of this kind which excited most interest in the 3rd century may be illustrated from a collection of questions printed in the Palatine Anthology, which was made by Metrodorus at the beginning of the next century, about 310. Some of them are due to the editor, but some are an anterior date, and they fairly illustrate the way in which arithmetic was leading up to algebraical methods. The following are typical examples. 4 pipes discharge into a cistern. One fills it in 1 day, another in 2 days, the third in 3 days, the fourth in 4 days. If all run together, how soon will they fill the cistern? Demochares has lived a fourth of his life as a boy, a fifth as a youth, a third as a man, and has spent 13 years in his dotage. How old is he? Make a crown of gold, copper, tin, and iron weighing 60 minae. Gold and copper shall be 2/3 of it, and gold and tin 3/4 of it, and gold and iron 3/5 of it. Find the weights of the gold, copper, and tin and iron which are required. The last problem is a numerical illustration of Thamyrides's theorem as quoted above. The German commentators have pointed out that though these problems lead to simple equations, they can be solved by geometrical methods, the unknown quantity being represented by a line. Dean Peacock has also remarked that they can be solved by the method used in similar cases by the Arabians and many by medieval writers. This method, usually known as the rule of false assumption, consists in assuming any number for the unknown quantity, and if on trial the given conditions be not satisfied, altering the number by a simple proportion as in the rule of 3. For example, in the second problem, suppose we assume that the age of Demochares is 40, and then by given conditions he would have spent 8 2/3, not 13 years in his dotage, and therefore we have the ratio of 8 2/3 to 13 equal to the ratio of 40 to his actual age, hence his actual age is 60. But the most recent writers on the subject think that the problems were solved by rhetorical algebra, that is, by a process of algebraical reasoning expressed in words and without the use of symbols. This, according to Nesselmann, is the first stage in the development of algebra, and we find it used both by Ahmes and by the earliest Arabian, Persian, and Italian algebraists. Examples of its use in the solution of a geometrical problem and in the rule for the solution of a quadratic equation are given later. See below, pages 207 and 214. On this view, then, a rhetorical algebra has been gradually evolved by the Greeks, or was then in process of evolution. Its development was, however, very imperfect. Hankel, who is no unfriendly critic, says the results attained as the net outcome of the work of 600 years on the theory of numbers are, whether we look at the form or the substance, unimportant or even childish. and not in any way the commencement of a science. In the midst of this decaying interest in geometry and these feeble attempts at algebraic arithmetic, a single algebraist of marked originality suddenly appeared, who created what was practically a new science. This was Diophantus, who introduced a system of abbreviation for those operations and quantities which constantly recur. Though using them, he observed all the rules of grammatical syntax. The resulting science is called by Nesselmann a syncopated algebra. It is a sort of shorthand. Broadly speaking, it may be said that European algebra did not advance beyond this stage until the close of the 16th century. Modern algebra has progressed one stage further and is entirely symbolic. That is, it has a language of its own, and a system of notation which has no obvious connection with the things represented, while the operations are performed according to certain rules which are distinct from the laws of grammatical construction. Diophantus. All that we know of Diophantus is that he lived in Alexandria, and that most likely he was not a Greek. Even the date of his career is uncertain, but probably he flourished in the early half of the 4th century, that is, shortly after the death of Pappus. He was 84 when he died. In the above sketch, the lines on which algebra has developed, I credited Diophantus with the invention of syncopated algebra. This is a point on which opinions differ, and some writers believe that he only systematized the knowledge which was familiar to his contemporaries. In support of this latter opinion, it may be stated that Cantor thinks that there are traces of the use of algebraic symbolism in Pappus, and that Frédélin mentions a Greek papyrus with the signs / and curve symbol, and are used for addition and subtraction respectively, but no other direct evidence for the non-originality of Diophantus has been produced, and no ancient author gives any sanction to this view. Diophantus wrote a short essay on polygonal numbers, a treatise on algebra which has come down to us in a mutilated condition, and a work on porisms which is lost. The polygonal numbers contains 10 propositions, and was probably his earliest work. In this he abandons the empirical method of Nicomachus, and reverts to the old and classical system by which numbers are represented by lines. A construction is, if necessary, made, and a strictly deductive proof follows. It may be noticed that in it he quotes propositions such as Euclid 2:3 and 2:8, referring to numbers and not to any magnitudes. His chief work is Arithmetic. This is really a treatise on algebra. Algebraic symbols are used and the problems are treated analytically. Diophantus tacitly assumes, as is done in nearly all modern algebra, that the steps are reversible. He applies this algebra to find solutions, though frequently only particular ones, of several problems involving numbers. I propose to consider successively the notation, the methods of analysis employed, and the subject matter of this work. First, as to the notation, Diophantus always employed a symbol to represent the unknown quantity in his equations. But as he had only one symbol, he could never use more than one unknown at a time. See however below, page 109. The unknown quantity is called oarthmos and is represented by sigma prime, sigma omicron superscript prime. It is usually printed as lowercase sigma. In the plural it is denoted by sigma sigma, both lowercase, or sigma sigma superscript omicron iota. This symbol may be a corruption of alpha superscript omicron, or possibly it is an old hieratic symbol for the word heap. See above, page 4. Or it may stand for the final sigma of the word. The square of the unknown is called zinamis and denoted by lowercase delta superscript upsilon, the cube cubos, and denoted by kappa, and so on up to the 6th power. The coefficients of the unknown quantity and its powers are numbers, and a numerical coefficient is written immediately after the quantity it multiplies. An absolute term is regarded as a certain number of units or monaves which are represented by mu superscript omicron. There is no sign for addition beyond mere juxtaposition. Subtraction is represented by an upside down psi, and this symbol affects all the symbols that follow it. Equality is represented by iota. Thus you can represent an equation such as x cubed plus 8x minus 5x squared plus 1 equals x. Diophantus also introduced a somewhat similar notation for fractions involving the unknown quantity, but into the details of this I need not here enter. It will be noticed that all these symbols are mere abbreviations for words, and Diophantus reasons out his proof, writing these abbreviations in the middle of his text. In most manuscripts there is a marginal summary in which the symbols alone are used and which is really symbolic algebra, but probably this is the addition of some scribe of later times. This introduction of a contraction or a symbol instead of a word to represent an unknown quantity marks a greater advance than anyone not acquainted with the subject would imagine, and those who have never had the aid of some such abbreviated symbolism find it almost impossible to understand complicated algebraical processes. It is likely enough that it might have been introduced earlier, but for the unlucky system of numeration adopted by the Greeks, which they used all the letters of the alphabet to denote particular numbers and thus make it impossible to employ them to represent any number. Next, as to the knowledge of algebraic methods shewn in the book. Diophantus commences with some definitions which include an explanation of his notation, and in giving the symbols for minus he states that a subtraction multiplied by a subtraction gives an addition. By this he means that the product of negative b and negative d in the expansion of a minus b multiplied by c minus d is positive bd, but in applying the rule he always takes care that the numbers a, b, c, d are so chosen that a is greater than b and c is greater than d. The whole of the work itself, or at least as much as is now extant, is devoted to solving problems which lead to equations. It contains the rules for solving a simple equation of the first degree and a binomial quadratic. The rule for solving any quadratic equation is probably in one of the lost books, but where the equation is of the form ax squared plus bx plus c equals 0, he seems to have multiplied by a and then completed the square, in much the same way as is now done. When the roots are negative or irrational, the equation is rejected as impossible, and even when both roots are positive, he never gives more than one, always taking the positive value of the square root. Diophantus solves one cubic equation, namely x cubed plus x equals 4x squared plus 4. Book 6, problem 19. The greater part of the work is however given up to the indeterminate equations between two or three variables. When the equation is between two variables, then, if it be of the first degree, he assumes a suitable value for one variable and solves the equation for the other. Most of his equations are of the form of y squared equals ax squared plus bx plus c, a, b, and c being capitalized. Whenever capital A or capital C is present, he is able to solve them completely. When this is not the case, then if capital A equals little a squared, he assumes that y equals little ax plus m. If big C equals little c squared, he assumes y equals mx plus little c. And lastly, if the equation can be put into the form y squared equals ax plus or minus little b quantity squared plus little c, he assumes that y equals mx, where in each case he has some particular numerical value suitable to the problem under consideration. A few particular equations of a higher order occur, but in those he generally alters the problem so as to enable him to reduce the equations to one of the above forms. The simultaneous indeterminate equations involving three variables, or double equations as he calls them, which he considers are of the forms y squared equals capital AX squared plus capital BX plus capital C, and z squared equals little a times x squared plus little b times x plus little c. If big A and little a both vanish, he solves them in one or two ways. It will be enough to give one of his methods, which is as follows. He subtracts and thus gets an equation of the form y squared minus z squared equals mx plus n. Hence, if y plus or minus z equals lambda, then y minus or plus z equals the quantity mx plus n, close bracket, divided by lambda. And solving, he finds y and z. His treatment of the double equations of a higher order lacks generality and depends on the particular numerical conditions of the problem. Lastly, as to the matter of the book. The problems he attacks and the analysis he uses are so various that they cannot be described concisely, and I have therefore selected 5 typical problems to illustrate his methods. What seems to strike his critics most is the ingenuity with which he selects as his unknown some quantity which leads to equations such as he can solve, and the artifices by which he finds numerical solutions of his equations. I select the following as characteristic examples. 1. Find 4 numbers, the sum of every arrangement 3 at a time being given, say 22, 24, 27, and 20. Book 1, Problem 17. Let x be the sum of all 4 numbers, hence the numbers are x minus 22, x minus 24, x minus 27, and x minus 20. Therefore x equals x minus 22 plus quantity x minus 24 plus quantity x minus 27 plus quantity x minus 20. Therefore x equals 31. The numbers are 9, 7, 4, and 11. 2. Divide a number such as 13, which is the sum of 2 squares 4 and 9, into 2 other squares. That's book 2, problem 10. He says that since the given squares are 2 squared and 3 squared, he will take x plus 2 quantity squared and mx minus 3 quantity squared as the required squares, and will assume m equals 2. Therefore, x plus 2 quantity squared plus 2x minus 3 quantity squared equals 13. Therefore, x equals 8/5. Therefore, the required squares are 324 over 25 and 1/25. 3. Find 2 squares such as the sum of the product and either is a square. Book 2, problem 29. Let x squared and y squared be the numbers. Then x squared y squared plus y squared and x squared y squared plus x squared are squares. The first will be a square if x squared plus 1 be a square, which he assumes may be taken equal to x minus 2 all squared, hence x equals 3/4. He has now to make 9/16 multiplied by the quantity y squared plus 1 a square. To do this he assumes that 9y squared plus 9 equals the quantity 3y minus 4 all squared, hence y equals 7 over 24. Therefore, the squares required are 9/16 and 49 over 576. It will be recollected that Diophantus had only one symbol for an unknown quantity, and in this example he begins by calling the unknowns x squared and 1. But as soon as he had found x, he then replaces the 1 by the symbol for the unknown quantity, and it finds it in its turn. 4. To find a rational right-angled triangle such that the line bisecting an acute angle is rational. Book 6, problem 18. His solution is as follows. Let ABC be the triangle of which C is a right angle. Let the bisector AD equals 5x and let DC equal 3x. hence AC equals 4x. Now let BC be a multiple of 3, say 3, therefore BD equals 3 minus 3x, hence AB equals 4 minus 4x by Euclid 6.3, hence 4 minus 4x quantity squared equals 3 squared plus 4x all squared, Euclid 1.47, therefore x equals 7 over 32. Multiplying by 32 we get for the sides of the triangle 28, 96 and 100, and for the bisector 35. Number 5. A man buys X measures of wine, some at 8 drachmae a measure, the rest at 5. He pays for them a square number of drachmae such that if 60 be added to it the resulting number is x squared. Find the number he bought at each price. That's book 5, problem 33. Well, the price paid was x squared minus 60, hence 8x is greater than x squared minus 60 and 5x is less than x squared minus 60. From this it follows that x must be greater than 11 and less than 12. Again, x squared minus 60 is to be a square. Suppose it is equal to x minus m quantity squared, then x equals m squared plus 60 in brackets divided by 2m. We have therefore 11 is less than the quantity m squared plus 60 divided by 2m is less than 12. Therefore m is a number between 19 and 21. Diophantus therefore assumes that m is equal to 20, which gives him x equals 11 and a half, and makes the total cost, i.e. x squared minus 60, equal to 72 and 1/4 drachmae. He has next to divide the cost into two parts, which shall give the cost of the 8 drachmae measures and the 5 drachmae measures respectively. Let the parts be y and z. Therefore 1/5 z plus 1/8 multiplied by the quantity 72 and 1/4 minus z equals 11 and a half. Therefore z equals 5 times 79 divided by 12, and y equals 8 times 59 divided by 12. Therefore the number of 5 drachmae measures was 79 twelfths, and of 8 drachmae measures was 59 twelfths. From the enunciation of this problem it would seem that the wine was of poor quality, and M. Tannery has ingeniously suggested that the prices mentioned for such a wine are higher than were usual until after the end of the 2nd century. He therefore rejects the view which was formerly held that Diophantus lived in that century, but he does not seem to be aware that De Morgan had previously shewn that this opinion was untenable. M. Tannery inclines to think that Diophantus lived half a century earlier than I had supposed. I mentioned that Diophantus wrote a third work entitled Porisms. The book is lost, but we have the enunciations of some of the propositions, and though we cannot tell whether they were rigorously proven by Diophantus, they confirm our opinion of his ability and sagacity. It has been suggested that some of the theorems which he assumes in his arithmetic were proved in the Porisms. Among the more striking of these results are the statements that the difference of two cubes can always be expressed as a sum of two cubes, that no number of the form 4n-1 can be expressed as the sum of two squares, and that no number of the form 8n-1 or possibly 24n plus 7 can be expressed as the sum of three squares. To these we may perhaps add the proposition that any number can be expressed as a square or as a sum of 2 or 3 or 4 squares. The writings of Diophantus exercised no perceptible influence on Greek mathematics, but his arithmetic, when translated into Arabic in the 10th century, influenced the Arabian school, and so indirectly affected the progress of European mathematics. A copy of the work was discovered in 1462. It was translated into Latin and published by Xylander in 1575. The translation excited general interest, but by that time the European algebraists had on the whole advanced beyond the point at which Diophantus had left off. The names of two commentators will practically conclude the long roll of Alexandrian mathematicians. Theon. The first of these is Theon of Alexandria, who flourished about 370. He was not a mathematician of special note, but we are indebted to him for an edition of Euclid's Elements and a commentary on the Almagest. The latter gives a great deal of miscellaneous information about the numerical methods used by the Greeks. It was translated with comments by M. Helma and published at Paris in 1821. Hypatia. The other was Hypatia, the daughter of Theon. She was more distinguished than her father and was the last Alexandrian mathematician of any general reputation. She wrote a commentary on the Conics of Apollonius and possibly some other works, but nothing of hers is now extant. She was murdered at the instigation of the Christians in 415. The fate of Hypatia may serve to remind us that the Christians, as soon as they became the dominant party in the state, shewed themselves bitterly hostile to all forms of learning. The very singleness of purpose which had at first so materially aided their progress developed into a one-sidedness which refused to see any good outside their own body. Those who did not actively assist them were persecuted, and the manner in which they carried out on their war against the old schools of learning is pictured on the pages of Kingsley's novel. The final establishment of Christianity in the East marks the end of the Greek scientific schools, though nominally they continued to exist for 200 years more. The Athenian school in the 5th century. The hostility of the Eastern Church to Greek science is further illustrated by the fall of the later Athenian school. This school occupies but a small space in our history. Ever since Plato's time, a certain number of professional mathematicians have lived at Athens, and about the year 420 this school again acquired considerable reputation, largely in consequence of the numerous students who after the murder of Hypatia migrated there from Alexandria. Its most celebrated members were Proclus, Damascius, and Eutychius. Proclus was born at Constantinople in February 412 and died at Athens on April 17, 485. He wrote a commentary on Euclid's Elements, of which that part which deals with the first book is extant and contains a great deal of valuable information on the history of Greek mathematics. He is verbose and dull, but luckily he has preserved for us quotations from other and better authorities. His commentary has been edited by G. Fridolin Leipzig, 1873. Proclus has succeeded as the head of the school by Marinus, and Marinus by Isidorus. Damascius, Eutychius. Two pupils of Isidorus, who in their turn subsequently lectured at Athens, may be mentioned in passing. Damascius of Damascus, circa 490, added to Euclid's Elements a 15th book on the inscription of one regular solid in another. Eutychius, circa 510, wrote commentaries on the first 4 books of the Conics of Apollonius and on various works of Archimedes. He also published some examples of practical Greek arithmetic. His works have never been edited, though they would seem to deserve it. This later Athenian school was carried on under great difficulties owing to the opposition of the Christians. Proclus, for example, was repeatedly threatened with death because he was a philosopher. His remark, "After all, my body does not matter, it is the spirit that I shall take with me when I die," which he made to some students who had offered to defend him, has often been quoted. The Christians, after several ineffectual attempts, at last got a decree from Justinian in 529 that heathen learning should no longer be studied at Athens. That date therefore marks the end of the Athenian school. The church at Alexandria was less influential, and the city was more remote from the centre of civil power. The schools there were thus suffered to continue, though their existence was of a precarious character. Under these conditions mathematics continued to be read there for another 100 years, but all interest in the study had gone. Roman mathematics. I ought not to conclude this part of the history without any mention of Roman mathematics, for it was through Rome that mathematics first passed into the curriculum of medieval Europe, and in Rome all modern history has its origin. There is, however, very little to say on the subject. The chief study of the place was in fact the art of government, whether by law, by persuasion, or by those material means on which all government ultimately rests. There was no doubt professors who could teach the results of Greek science, but there was no demand for a school of mathematics. Italians who wished to learn more than the elements of the science went to Alexandria or to places which drew their inspiration from Alexandria. The subject as taught in the mathematical schools at Rome seemed to have been confined in arithmetic to the art of calculation, no doubt by the aid of the abacus, and perhaps some of the easier parts of the work of Nicomachus, and in geometry to a few practical rules, though some of the arts founded on a knowledge of mathematics, especially that of surveying, were carried to a high pitch of excellence. It would seem also that special attention was paid to the representation of numbers by signs. The manner of indicating numbers up to 10 by the use of the fingers must have been in practice from quite early times, but about the first century it had been developed by the Romans into a finger symbolism by which numbers up to 10,000 or perhaps more could be represented. This would seem to have been taught in the Roman schools. The system would hardly be worth notice, but that its use has still survived in the Persian bazaars. I am not aware of any Latin work on the principles of mechanics, but there was numerous books on the practical side of the subject which dealt elaborately with architectural and engineering problems. We may judge what they were like by the Mathematici Veteris, which is a collection of very short treatises on catapults, engines of war, etc. An edition was published in Paris in 1693. And by the Cateris, written by Sextus Julius Africanus about the end of the second century, which contains, amongst other things, rules for finding the breadth of a river when the opposite bank is occupied by an enemy, or how to signal with a semaphore, etc. In the 6th century, Boethius published a geometry containing a few propositions from Euclid and an arithmetic founded on that of Nicomachus. And about the same time Cassiodorus discussed the foundation of a liberal education which, after the preliminary trivium of grammar, logic, and rhetoric, meant the quadrivium of arithmetic, geometry, music, and astronomy. These works were written at Rome in the closing years of the Athenian and Alexandrian schools, and I therefore mention them here, but as their only value lies in the fact that they have become recognized textbooks in medieval education, I postpone their consideration to chapter 8. Theoretical mathematics was in fact an exotic study at Rome. Not only was the genius of the people essentially practical, but alike during the building of their empire, while it lasted, and under the Goths, all the conditions were unfavourable to abstract science. On the other hand, Alexandria was exceptionally well placed to be a centre of science. From the foundation of the city to its capture by the Mohammedans, it was disturbed neither by foreign nor by civil war, save for a few years when the rule of the Ptolemies gave way to that of Rome. It was wealthy, and its rulers took pride in endowing the university. And lastly, just as in commerce it became the meeting place of the East and the West, so it had the good fortune to be the dwelling place alike of the Greeks and of various Semitic people. The one race shewed a peculiar attitude for geometry, the other for all science which rests on measurement. Here too, however, as time went on, the conditions gradually became more unfavourable, the endless discussions by the Christians on theological dogmas and the increasing insecurity of the empire tending to divert men's thoughts into other channels. End of the Second Alexandrian School. The precarious existence and unfruitful history of the last 2 centuries of the Second Alexandrian School need no record. In 632 Muhammad died, and within 10 years his successors had subdued Syria, Palestine, Mesopotamia, Persia, and Egypt. The precise date on which Alexandria fell is doubtful, but the most reliable Arab historians give December 10th, 641, a date which at any rate is correct within 18 months. With the fall of Alexandria, the long history of Greek mathematics came to a conclusion. It seems probable that the greater part of the famous university library and museum had been destroyed by Christians 100 or 200 years previously, and what remained was unvalued and neglected. Some 2 or 3 years after the first capture of Alexandria, a serious revolt occurred in Egypt, which was ultimately put down with great severity. I see no reason to doubt the truth of the account that after the capture of the city the Mohammedans destroyed such university buildings and collections as were still left. It is said that when Arab commander ordered the library to be burnt, the Greeks made such energetic protests that he consented to refer the matter to the Caliph Omar. The Caliph returned the answer, "As to the books you have mentioned, if they contain what is agreeable with the book of God, the book of God is sufficient without them. And if they contain what is contrary to the book of God, there is no need for them. So give the orders for their destruction." The account goes on to say that they were burnt in the public baths of the city, and that it took 6 months to consume them all. End of chapter 5. This is Paul King, pjk.scripts.mit.edu. Chapter 6 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 6. The Byzantine School, 641 to 1453. It will be convenient to consider the Byzantine school in connection with the history of Greek mathematics. After the capture of Alexandria by the Mohammedans, the majority of the philosophers who previously had been teaching there migrated to Constantinople, which then became the centre of Greek learning in the East, and remained so for 800 years. But though the history of the Byzantine school stretches over so many years, a period about as long as that from the Norman conquest to the present day, it is utterly barren of scientific interest, and its chief merit is that it preserved for us the works of the different Greek schools. The revelation of these works to the West in the 15th century was one of the most important sources of the stream of modern European thought, and the history of the Byzantine school may be summed up by saying that it played the part of a conduit pipe in conveying to us the results of an earlier and brighter age. The time was one of constant war, and men's minds during the short intervals of peace were mainly occupied with the theological subtleties and pedantic scholarship. I should not have mentioned any of the following writers had they lived in the Alexandrian period, but in default of any others may be noticed as illustrating the character of the school. I ought also perhaps to call the attention of the reader explicitly to the fact that I am here departing from chronological order, and that the mathematicians mentioned in this chapter were contemporaries of those discussed in the chapters devoted to the mathematics of the Middle Ages. The Byzantine school was so isolated that I deem this is the best arrangement of the subject. Hero. One of the earliest members of the Byzantine school was Hero of Constantinople circa 900, sometimes called the Younger, to distinguish him from Hero of Alexandria. There is some difficulty in separating the works of these two writers. Hero would seem to have written on geodesy and mechanics as applied to the engines of war. During the 10th century, two emperors, Leo VI and Constantine VII, shewed considerable interest in astronomy and mathematics, but the stimulus thus given to the study of these subjects was only temporary. Psellus. In the 11th century, Michael Psellus, born in 1020, wrote a pamphlet on the quadrivium. It is now in the National Library at Paris. It was printed at Bâle in 1556. He also wrote Compendium Mathematicum, which was printed at Leyden in 1647. In the 14th century we find the names of three monks who paid attention to mathematics. Planudes. The first of three was Maximus Planudes. He wrote a commentary on the first two books on the arithmetic of Diophantus, and this was published by Xylander, Bale, 1575, a work on Hindu arithmetic in which he introduced the use of the Arabic numerals into the Eastern Empire. This was published by C. J. Gerhardt, Halle, 1865, and another on proportions which is now in the National Library at Paris. Barlaam. The next was a Calabrian monk named Barlaam, who was born in 1290 and died in 1348. He was the author of a work on the Greek methods of calculation, from which we derive a good deal of our information as to the way in which the Greeks practically treated fractions. This was published in Paris in 1606. Barlaam seems to have been a man of great intelligence. He was sent as an ambassador to the Pope at Avignon, and acquitted himself credibly of a difficult mission, where there he taught Greek to Petrarch. He was famous at Constantinople for the ridicule he threw on the preposterous pretensions of the monks at Mount Athos, who taught that those who joined them who could, by standing naked, resting their beards on their breasts, and steadily regarding their stomachs, see a mystic light which was the essence of God. Barlaam advised that to substitute the light of reason for that of their stomachs, a piece of advice which nearly cost him of his life. Argyrus. The last of these monks was Isaac Argyrus, who died in 1372. He wrote three astronomical tracts, the manuscripts of which are in the libraries at the Vatican, Leyden, and Vienna. One on geodesy, the manuscript of which is at the Escurial. One on geometry, the manuscript of which is in the National Library at Paris. One on the arithmetic of Nicomachus, the manuscript of which is in the National Library at Paris, and one on trigonometry, the manuscript of which is at the Bodleian at Oxford. Nicholas Rhabdas. In the 14th or perhaps the 15th century, Nicholas Rhabdas of Smyrna wrote two papers on arithmetic which are now in the National Library at Paris and have been edited by P. Tannery, Paris, 1886. He gave an account of the finger symbolism, see above, which the Romans had introduced into the East and was then current there. This is described by Bede, and therefore would seem to have been known as far west as Britain. Jerome also alludes to it. Pachymeres. Early in the 15th century, Pachymeres wrote tracts on arithmetic, geometry, and for mechanical machines. Moschopulus. A few years later, Emmanuel Moschopulus, who died in Italy circa 1460, wrote a treatise on magic squares. A magic square consists of a number of integers arranged in the form of a square so that the sum of the numbers in every row, in every column, and in each diagonal are the same. If the integers be the consecutive numbers from 1 to n squared, then the square is said to be of the nth order. and it is easily seen that in this case the sum of the numbers of any row, any column, or diagonal is equal to half n multiplied by the quantity n squared plus 1. Thus the first 16 integers arranged in either of the forms shown here form a magic square of the fourth order, the sum of the numbers in every row, every column, and in each diagonal being 34. The first square, a 4 by 4 magic square, and I will recite the numbers by row. 1, 15, 14, 4. 12, 6, 7, 9. 8, 10, 11, 5. 13, 3, 2, and 16. The next magic square. 15, 10, 3, 6. 4, 5, 16, 9. 14, 11, 2, 7. And 1, 8, 13, 12. In the mystical philosophy then current, certain metaphysical ideas were often associated with particular numbers, and thus it was natural that such arrangements of numbers should attract attention and be deemed to possess magical properties. The theory of the formation of magic squares is elegant, and several distinguished mathematicians have written on it, but I need hardly to say it is not useful. It is largely due to De la Hire, who gave rules for the construction of a magic square of any order higher than the second. Moschopoulos seems to have been the earliest European writer who attempted to deal with the mathematical theory, but his rules apply only to odd squares. The astrologers of the 15th and 16th centuries were much impressed by such arrangements. In particular, the famous Cornelius Agrippa (1486 to 1535) constructed magic squares of order 3, 4, 5, 6, 7, 8, and 9, which were associated respectively with the 7 astrological planets, namely Saturn, Jupiter, Mars, the Sun, Venus, Mercury, and the Moon. He taught that a square of one cell in which unity was inserted represented the unity and eternity of God, while the fact that a square of the second order could not be constructed illustrated the imperfection of the 4 elements air, earth, fire, and water, and later writers added that it was symbolic of original sin. A magic square engraved on a silver plate was often prescribed as a charm against the plague, and one, namely the first magic square whose numbers I just previously listed, is drawn in the picture of Melancholy painted about the year 1500 by Albrecht Dürer. Such charms are worn still in the East. Constantinople was captured by the Turks in 1453, and the last semblance of a Greek school of mathematics then disappeared. Numerous Greeks took refuge in Italy. In the West the memory of Greek science had vanished, and even the names of all but a few Greek writers were unknown. And thus the books brought by these refugees came as a revelation to Europe, and, as we shall see later, gave an immense stimulus to the study of science. End of chapter 6. Read by Paul King, pjk.scripps.mit.edu. This is chapter 7 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 7. Systems of Numeration and Primitive Arithmetic. I have in many places alluded to the Greek method of expressing numbers in writing, and I have thought it best to defer this chapter to the whole of what I wanted to say on the various systems of numerical notation which were displaced by the systems introduced by the Arabs. First, as to symbolism and language. The plan of indicating numbers by the digits of one or both hands is so natural that we find it in universal use among early races, and the members of all tribes now extant are able to indicate by signs numbers at least as high as 10. It is stated that in some languages the names for the first 10 numbers are derived from the fingers used to denote them. For larger numbers, we soon however reach a limit beyond which primitive man is unable to count, while as far as language goes it is well known that many tribes have no word for any number higher than 10, and some have no word for any number beyond 4, all higher numbers being expressed by words plenty or heap. In connection with this, it is worth remarking that the Egyptians used a symbol for the word heap to denote the unknown quantity in algebra. The number 5 is generally represented by the open hand, and it is said that in almost all languages the words 5 and hand are derived from the same root. It is possible that in early times men did not readily count beyond 5, and things if more numerous were counted by multiples of it. Thus the Roman symbol x for 10 probably represents two v's, placed apex to apex, and seems to point to a time when things were counted by 5s. In connection with this, it is worth noticing that both in Java and also among the Aztecs, a week consisted of 5 days. The members of nearly all races which have now any knowledge seem however to have used the digits of both hands to represent numbers. They could thus count up to and including 10, and therefore were led to take 10 as their radix of notation. In the English language, for example, all the words for numbers higher than 10 are expressed on the decimal system. Those for 11 and 12, which at first sight seem to be exceptions, being derived from Anglo-Saxon words for 1 and 10 and 2 and 10 respectively. Some tribes seem to have gone further, and by making use of their toes were accustomed to count by multiples of 20. The Aztecs, for example, are said to have done so. It may be noticed that we still count some things, e.g. sheep, by scores. The word score signifying a notch or a scratch made on the completion of 20, while the French also talk about 80, as though at one time they counted things by multiples of 20. I am not, however, sure whether the latter argument is worth anything, for I have an impression that I have seen the word octant, octante, in old French books, and there is no question that septa and nona were at one time common words for 70 and 90, and indeed they are still retained in some dialects. The only tribes of whom I have read did not count in terms of either 5 or some multiple of 5 are the Bolans of West Africa, who are said to have counted by multiples of 7, and the Maoris, who are said to have counted by multiples of 11. Up to 10 it's comparatively easy to count, but primitive people found and still find great difficulty in counting higher numbers. Apparently at first this difficulty was only overcome by the method, still in use in South Africa, of getting 2 men, one to count the units up to 10 on his fingers and the other to count the number of groups of 10 so formed. To us it is obvious that it is equally effectual to make a mark of some kind on the completion of each group of 10, but it is alleged that the members of many tribes never succeeded in counting numbers higher than 10 unless by the aid of 2 men. Most races who shewed any aptitude for civilization proceeded further and invented a way of representing numbers by means of pebbles or counters arranged in sets of 10, and this in its turn developed into the abacus or swan pan. This instrument was in use among the nations so widely separated as the Etruscans, the Greeks, the Egyptians, the Hindus, the Chinese, and the Mexicans, and was, it is believed, invented independently at several different centers. It is still in common use in Russia, China, and Japan. In its simplest form, the abacus consists of a wooden board with a number of grooves cut in it, or of a table covered with sand in which grooves are made with the fingers. To represent a number, as many counters or pebbles (calculi) are put on the first groove as there are units, as many on the second as there are tens, and so on. When by its aid a number of objects are counted, for each object a pebble is put on the first groove, and as soon as there are 10 pebbles there, they are taken off and one pebble put on the second groove, and so on. It was sometimes, as in the Aztec quipus, made with a number of parallel wires or strings stuck in a piece of wood on which the beads could be threaded, and in that form it is called a swan pan. Some races counted from left to right, others from right to left, but this is a mere matter of convention. The Roman abaci seems to have been rather more elaborate. They contain 2 marginal grooves or wires, one with 4 beads to facilitate the addition of fractions whose denominators were 4, and one with 12 beads for fractions whose denominators were 12, but otherwise they did not differ in principle from those described above. They were generally made to represent numbers up to 100 million. There are no Greek abaci now in existence, but there is no doubt that they were similar to the Roman ones. The Greeks and Romans used their abaci as boards on which they played a game of something like backgammon. In the Russian choktu, the instrument is improved by having the wires set in a rectangular frame, and 10 or 9 beads are permanently threaded on each of the wires being considerably longer than is necessary to hold them. If the frame be held horizontal, all the beads be towards one side, say the lower side of the frame. It is possible to represent any number by pushing towards the other or upper side as many beads on the first wire as there are units in the number, as many beads on the second wire as there are tens in the number, and so on. Calculations can be made somewhat more rapidly if the 5 beads on each wire next to the upper side be colored differently to those next to the lower side, and they can be still further facilitated if the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth counters in each column be respectively marked with symbols for the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Gerbert is said to have introduced the use of such marks, called apices, toward the close of the 10th century. As to Chinese and Japanese swan pans, there the development is carried one step further, and 5 beads on each wire are replaced by a single bead of a different form or on a different division, but apices are not used. I am told that an expert Japanese can, by the aid of a swan pan, add numbers as rapidly as can be read out to him. On the Chinese and Japanese swan pans it is possible for 2 numbers to be represented at the same time on it. The use of the abacus in addition and subtraction is evident. It can be used also in multiplication and division. The rules for these processes, illustrated by examples, are given in the arithmetic known as the Ground of Arts, which was published by Record at London in 1540. The abacus is obviously only a concrete way of representing a number in the decimal system of notation, that is, by means of the local value of the digits. Unfortunately, the method of writing numbers developed on a different line, and it was not until about the 13th century of our era when a symbol 0 used in conjunction with 9 other symbols was introduced as a corresponding notation in writing adopted in Europe. Next, as to the means of representing numbers in writing, in general we may say that in the earliest times a number was, if represented by a sign and not a word, indicated by the requisite number of strokes. Thus, in an inscription from Tralles and Caria of the date 398 BC, the phrase 7th year is represented by iteos followed by 7 strokes. These strokes may have been mere marks, Or perhaps they originally represented fingers, since in the Egyptian hieroglyphics the symbols for the numbers 1, 2, 3 are 1, 2, and 3 fingers respectively, though in the later hieratic writing the symbols had become reduced to straight lines. Additional symbols for 10 and 100 were soon introduced, and the oldest extant Egyptian and Phoenician writings repeat the symbol for unity as many times, up to 9, as was necessary, and then repeat the symbol for 10 as many times, up to 9, as was necessary, and so on. No specimens of Greek numeration of a similar kind are in existence, but there is every reason to believe the testimony of Iamblichus, who asserts that this was the method by which the Greeks first expressed numbers in writing. This way of representing numbers remained in current use throughout Roman history, and for greater brevity they or the Etruscans added separate signs for 5, 50, and so on. The Roman symbols are generally merely the initial letters of the names of the numbers. Thus C stood for centum or 100, M for mia or 1000. The symbol V for 5 seemed to have originally represented an open palm with the thumb extended. The symbols for L for 50 and D for 500 are said to represent the upper halves of the symbols used in early times for C and M. The subtractive forms like IV for III are probably of a later origin. Similarly, in Attica, 5 was denoted by capital Pi, the first letter of Fente, sometimes by gamma, capital Gamma, 10 by capital Delta, the initial letter of Deca, 100 denoted by capital Nu for Eketon, 1000 by capital Chi for Chile, while 50 was represented by a capital Delta written inside a capital Pi, and so on. These Attic symbols continued to be used for inscriptions and formal documents until a late date. This, if a clumsy, is a perfectly intelligible system, but the Greeks at some time in the 3rd century before Christ abandoned it for one which offers no special advantages in denoting a given number, while it makes all the operations of arithmetic exceedingly difficult. In this, which is known from the place where it is introduced as the Alexandrian system, the numbers from 1 to 9 are represented by the first 9 letters of the alphabet, the tens from 10 to 90 by the next 9 letters, and the hundreds from 100 to 900 by the next 9 letters. To do this, the Greeks wanted 27 letters, and as their alphabet contained only 24, they reinserted 2 letters, the digamma and the kappa, which had formerly been in it, but had become obsolete, and introduced at the end another symbol taken from the Phoenician alphabet. Thus the 10 letters alpha to iota stood respectively for the numbers 1 to 10, and the next 8 letters for the multiples of 10 from 20 to 90, and the last 9 letters for 100, 200, and etc. up to 900. Intermediate numbers like 11 were represented as the sum of 10 and 1, that is, by the symbol iota alpha. This afforded a notation for all numbers up to 999, and by a system of suffixes and indices it was extended so as to represent the numbers up to 100 million. There is no doubt that these signs were at first only used as a way of expressing a result attained by some concrete or experimental method, and the idea of operating with the symbols themselves in order to obtain the results is of a later growth, and is one with which the Greeks have never become familiar. The non-progressive character of Greek arithmetic may be partly due to their unlucky adoption of the Alexandrian system, which caused them for most practical purposes to rely on the abacus, and to supplement it by a table of multiplications which was learned by heart. The results of the multiplication or division of numbers other than those in the multiplication table might have been obtained by use of the abacus, but in fact they were generally got by repeated additions and subtractions. Thus, as late as 944, a certain mathematician who in the course of his work wanted to multiply 400 by 5 finds the result by addition. The same writer, when he wants to divide 6152 by 15, tries all the multiples of 15 until he gets to 6000, and this gives him 400 and a remainder of 152. He then begins again with all the multiples of 15 until he gets to 150, and this gives him 10 and a remainder of 2. Hence the answer is 410 with a remainder 2. A few mathematicians, however, such as Hero of Alexandria, Theon, and Eutocius, multiplied and divided in what is essentially the same way as we do. Thus, to multiply 18 by 13, we get 13 times 18 equals the quantity 10 plus 3 times the quantity 10 plus 8 equals 10 times the quantity 10 plus 8 plus 3 times the quantity 10 plus 8 equals 100 plus 80 plus 30 plus 24, which finally equals 234. I suspect that the last step, which they had to add 4 numbers together, was obtained by the aid of the abacus. These, however, were men of exceptional genius, and we must recollect that for all ordinary purposes the art of calculation was performed only by the use of the abacus and the multiplication table, while the term arithmetic was confined to the theories of ratio, proportion, and of numbers. All the systems here described were more or less clumsy, and they have been displaced among civilized races by the Arabic system, in which there are 10 digits and symbols, namely 9 for the first 9 numbers and another for 0. In this system, an integral number is denoted by a succession of digits, each digit representing the product of that digit as a power of 10, and the number being equal to the sum of those products. Thus, by means of the local value attached to 9 symbols and a symbol for 0, any number in the decimal scale of notation can be expressed. The history of the development of the science of arithmetic with this notation will be considered in a subsequent chapter. End of chapter 7. Read by Paul King. http pjk.scripts.mit.edu/pkj. Chapter 8 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Second period, the mathematics of the Middle Ages and of the Renaissance. This period begins about the 6th century and may be said to end with the invention of the analytical geometry and infinitesimal calculus. The characteristic feature of this period is the creation of modern arithmetic, algebra, and trigonometry. I commenced this history by dividing it in 3 periods. I have discussed the history of mathematics under Greek influence, and I now come to that of the mathematics of the Middle Ages and the Renaissance. The history of this period has not been investigated with the same fullness as that of earlier or of later times, and the relative importance of some mathematicians who lived in this period has been estimated differently by different writers. I shall consider first in chapter 8 the rise of learning in Western Europe and the mathematics of the Middle Ages. Next, in chapter 9, I shall discuss the nature and history of Arabian mathematics, and in chapter 10, their introduction into Europe. I shall then, in chapter 11, trace the subsequent progress of arithmetic to the year 1637. Next, in chapter 12, I shall treat of the general history of mathematics during the Renaissance from the invention of printing to the beginning of the 17th century, say from 1450 to 1637. This contains an account of the commencement of the scientific treatment of algebra, arithmetic, and trigonometry. Lastly, in chapter 13, I shall consider the revival of interest in mechanics, experimental methods, and pure geometry, which marks the last few years of this period, and serves as a connecting link between the mathematics of the Renaissance and the mathematics of modern times. Chapter 8. The rise of learning in Western Europe, circa 600 to 1200. Education in the 6th, 7th, and 8th centuries. The first few centuries of this second period of our history are singularly barren of interest, and indeed it would be strange if we found science or mathematics studied by those who lived in a condition of perpetual war. Broadly speaking, we may say that from the 6th to the 8th centuries the only places of study in Western Europe were the Benedictine monasteries. We may find there some slight attempts at a study of literature, but the science usually taught was confined to the use of the abacus, the method of keeping accounts, and a knowledge of the rule by which the date of Easter could be determined. Nor was this unreasonable, for the monk had renounced the world, and there was no reason why he should learn more science than was required for the services of the church and his monastery. The traditions of Greek and Alexandrian learning gradually died away. Possibly in Rome and a few favoured places, copies of the works of the great Greek mathematicians were obtainable, though with difficulty. But there were no students, the books were unvalued, and in time became very scarce. Three authors of the 6th century, Boethius, Cassiodorus, and Isidorus, may be named, whose writings serve as a connecting link between the mathematics of the classical and of the medieval times. As their works remain standard textbooks for some 6 or 7 centuries, it is necessary to mention them, but it should be understood that this is the only reason for doing so, and they shew no special mathematical ability. It will be noticed that these authors were contemporaries of the later Athenian and Alexandrian schools. Boethius. Anicius Manlius Severinius Boethius, or as the name is sometimes written Boetius, born in Rome about 475 and died in 526, belonged to a family which for the 2 preceding centuries had been esteemed one of the most illustrious in Rome. It was formerly believed that he was educated at Athens. This is somewhat doubtful, but at any rate he was exceptionally well read in Greek literature and science. He would seem to have wished to devote his life to literary pursuits, but recognizing that the world would be happy only when kings became philosophers or philosophers kings, he yielded to the pressure put on him and took an active share in politics. He was celebrated for his extensive charities, and what in those days was very rare, the care that he took to see that the recipients were worthy of them. He was elected consul at an unusually early age, and took advantage of his position to reform the coinage, and to introduce the public use of sundials, water clocks, and so on. He reached the height of his prosperity in 522 when his 2 sons were inaugurated as consuls. His integrity and attempts to protect the provincials from the plunder of the public officials brought on him the hatred of the court. He was sentenced to death while absent from Rome, seized at Ticinium, and in the baptistry of the church there tortured by drawing a cord round his head till the eyes were forced out of the sockets, and finally beaten to death with clubs on October 23, 526. Such at least is the account that has come down to us. At a later time his merits were recognized, and tombs and statues were erected in his honour by the state. Boethius was the last Roman of any note who studied the language and literature of Greece, and his works afforded to medieval Europe the means of entering into the intellectual life of the old world. His importance in the history of literature is thus very great, but it arises merely from the accident of the time at which he lived. After the introduction of Aristotle's works into the 13th century his fame died away, and he has now sunk into an obscurity which is as great as was once his reputation. He is best known by his Consolatio, which was translated by Alfred the Great into Anglo-Saxon. For our purposes it is sufficient to note that the teaching of early medieval mathematics was mainly founded on his geometry and arithmetic. His geometry consists of the enunciations only of the first book of Euclid and of a few selected propositions in the third and fourth books, but with numerous practical applications to finding areas and so on. He adds an appendix with proofs of the first three propositions to shew that the enunciations may be relied on. He also wrote an arithmetic founded on that of Nicomachus. These works have been edited by G. Friedelein, Leipzig, 1867. A textbook on music by him was also in use at Oxford within the present century. Cassiodorus. A few years later another Roman, Magnus Aurelius Cassiodorus, was born about 480 and died in 566. Published two works, De Institutione Divinarum Literarum and De Artibus ac Disciplinis, in which not only the preliminary trivium of grammar, logic, and rhetoric were discussed, but also the mathematical quadrivium of arithmetic, geometry, music, and astronomy. These were considered standard works during the Middle Ages. The former was printed at Venice in 1729. Isidorus. Isidorus, bishop of Seville, born in 570 and died in 636, was the author of an encyclopedic work in 20 volumes called Origenis, of which the third volume is given up to the quadrivium. It was published in Leipzig in 1833. The Cathedral and the Conventual Schools. When in the latter half of the 8th century Charles the Great had established his empire, he determined to promote learning so far as he was able, and he began by commanding that schools should be opened in connection with every cathedral and monastery in his kingdom, an order which was approved and materially assisted by the popes. It is interesting to us to know that this was done at the instance and under the direction of two Englishmen, Alcuin and Clement, who had attached themselves to his court, a fact which may serve to remind us that during the 8th century England and Ireland were in advance of the rest of Europe as far as learning went. Alcuin. One of the more prominent was Alcuin, who was born in Yorkshire in 735 and died at Tours in 804. He was educated at York under Archbishop Egbert, his beloved master, whom he succeeded as director of the school there. Subsequently he became abbot of Canterbury and was sent to Rome by Ophia to procure the pallium for Archbishop Eanbald. On his journey back he met Charles at Parma. The emperor took a great liking to him and finally induced him to take up his residence at the imperial court and there teach rhetoric, logic, mathematics, and divinity. Alcuin remained for many years one of the most intimate and influential friends of Charles, who constantly employed him as a confidential ambassador. Such as he spent the years 791 and 792 in England, and while there reorganized the studies at his old school at York. In 801 he begged permission to retire from the court so as to be able to spend the last years of his life in quiet. With difficulty he obtained leave, and went to the abbey of St. Martin at Tours, for which he had been made head in 796. He established a school in connection with the abbey, which became very celebrated, and he remained and taught there till his death in May 19, 804. Most of the extant writings of Alcuin deal with the theology or history, but they include a collection of arithmetical propositions suitable for instruction of the young. The majority of the propositions are easy problems, either determinate or indeterminate, and are, I presume, founded on works which he had become acquainted when at Rome. The following is one of the most difficult, and will give an idea of the character of the work. If 100 bushels of corn be distributed among 100 people in such a manner that each man receives 3 bushels, each woman 2, and each child half a bushel, how many men, women, and children were there? The general solution is 20 minus 3n men, 5n women, and 80 minus 2n children, where n may have any of the values 1, 2, 3, 4, 5, or 6. Alcuin only states the solution for which n equals 3, that is, he gives the answer 11 men, 15 women, and 74 children. This collection, however, was the work of a man of exceptional genius, and probably we shall be correct in saying that mathematics, if taught at all in a school, was generally confined to geometry of Boethius, the use of the abacus and multiplication table, and possibly the arithmetic of Boethius, while, except in one of these schools, or in a Benedictine cloister, it was hardly possible to get either instruction or opportunities for study. It was of course natural that the works used should come from Roman sources, for Britain and all the countries included in the empire of Charles had at one time formed part of the western half of the Roman Empire, and their inhabitants continued for a long time to regard Rome as a centre of civilization, while the higher clergy kept up a tolerably constant intercourse with Rome. After the death of Charles, many of the schools confined themselves to teaching Latin, music, and theology, that is, those subjects some knowledge of which was essential to the worldly success of the higher clergy. Hardly any science or mathematics was taught, but the continued existence of the schools gave an opportunity to any teacher whose learning or zeal exceeded the narrow limits fixed by tradition, and though there were few who availed themselves of the opportunity, yet the number of those desiring instruction was so large that it would seem as if anyone who could teach was certain to attract a considerable audience. A few schools at which this was the case became large and acquired a certain degree of permanence, but even in them the teaching was still usually confined to the trivium or quadrivium. The former comprised of the 3 arts of grammar, logic, and rhetoric, but practically meant the art of reading and writing Latin. Nominally the latter included arithmetic and geometry with their applications, especially to music and astronomy, but in fact it rarely meant more than arithmetic sufficient to enable one to keep accounts, music for the church services, geometry for the purpose of land surveying, and astronomy sufficient to enable one to calculate the feasts and fasts of the church. The 7 liberal arts are enumerated in the line lingua tropus, ratio, numerus, tonus, angulus, and astra. Any student who got beyond the trivium was looked on as a man of great erudition. Qui tria, qui septem, qui totum sibili novit, as a verse of the 11th century runs. The special questions which then and long afterwards attracted the best thinkers were logic and certain proportions of transcendental theology and philosophy. We may sum the matter up by saying that during the 9th and 10th centuries the mathematics taught was still usually confined to that comprised in the 2 works of Boethius, together with the practical use of the abacus and the multiplication table, though during the latter part of the time a wider range of reading was undoubtedly accessible. Gerbert. In the 10th century a man appeared who would in any age have been remarkable and who gave a great stimulus to learning. This was Gerbert, an Aquitanian by birth who died in 1003 at about age 50. His abilities attracted attention to him even when a boy, and procured his removal from the abbey school at Aurillac to the Spanish March, where he received a good education. He was in Rome in 971, and his proficiency in music and astronomy excited considerable interest. At that time he was not much more than 20, but he had already mastered all of the branches of the trivium and quadrivium as then taught except logic, and to learn this he moved to Reims, which Archbishop Adalbero had made the most famous school in Europe. Here he was at once invited to teach, and so great was his fame that to him Hugh Capet entrusted the education of his son Robert, who was afterwards king of France. Gerbert was especially famous for his construction of abaci and terrestrial and celestial globes. He was accustomed to use the latter to illustrate his lectures. These globes excited great admiration, which he utilized by offering to exchange them for copies of classical Latin works, which seemed already to have become very scarce, and the better to effect this he appointed agents in the chief towns of Europe. To his efforts it is believed that we owe the preservation of several Latin works, but he made a rule to reject the Christian fathers and Greek authors from this library. In 982 he received the abbey of Bobbio, and the rest of his life was taken up with political intrigues. He became archbishop of Reims in 991 and of Ravenna in 998, and in 999 he was elected pope, when he took the title of Sylvester II. As head of the church he once commenced an appeal to Christendom to arm and defend the Holy Land, thus forestalling Peter the Hermit by a century, but he died on May 12, 1003, before he had time to elaborate his plans. His library is, I believe, preserved in the Vatican. So remarkable a personality left deep impress on his generation, and all sorts of fables soon began to collect around his memory. It seems certain that he made a clock which was long preserved at Magdeburg, and an organ worked by steam which was still at Reims 2 centuries after his death. All this only tended to confirm the suspicions of his contemporaries that he had sold himself to the devil, and the details of his interviews with that gentleman, the powers he purchased, his effort to escape from his bargain when he was dying, may be read in the pages of William of Malmesbury, Orderic Vitalis, and Platina. To these anecdotes the first named writer adds the story of the statue inscribed with the words "Strike here," which, having amused our ancestors in the Gesta Romanorum, has been recently told again in the Earthly Paradise. Extensive though his influence was, it must not be supposed that Gerbert's writings shew any great originality. His mathematical works comprise of a treatise on the use of the abacus, one on arithmetic entitled De Numerorum Divisione, and one on geometry. An improvement in the abacus attributed by some writers to Boethius, but which is more probably due to Gerbert, is the introduction in every column of the beads marked by different characters called apices for each of the numbers 1 to 9, instead of 9 exactly similar counters or beads. The apices were probably of Indian or Arabic origin, and led to a representation of numbers essentially the same as the Gobar numerals reproduced below. There were, however, no symbol for 0. The step from this concrete system of denoting numbers by a decimal system on an abacus to the system of denoting them by similar symbols in writing seems to be a small one, but it would appear that Gerbert didn't make it. His work on geometry is of unequal ability. It includes few applications to land surveying and the determination of heights of inaccessible objects, but much of it seems to be copied from some Pythagorean textbook. In the course of it he however solves one problem which was of remarkable difficulty for that time. The question is to find the sides of a right angled triangle whose hypotenuse and area are given. He says in effect that if these latter be denoted respectively by c and h squared, then the lengths of the two sides will be 1/2 multiplied by open square bracket square root of c squared plus 4h squared plus square root of c squared minus 4h squared close bracket. and 1/2 times open bracket square root of c squared plus 4h squared minus square root of c squared minus 4h squared close bracket. Bernelius. One of Gerbert's pupils, Bernelius, published a work on the abacus, reprinted in Olleris's edition of Gerbert's works, which is, there is very little doubt, a reproduction of the teaching of Gerbert. It is valuable as indicating that the Arabic system of writing numbers was still unknown in Europe. The rise of the early medieval universities. At the end of the 11th century or the beginning of the 12th, a great revival of learning took place at several of these cathedral or monastic schools, or perhaps we should rather say, in some cases, teachers who were not members of the school settled in its vicinity and with the sanction of the authorities gave lectures which were in fact always on theology, logic, or civil law. As the students at these centres grew in numbers, it became possible and desirable to act together whenever any interest common to all was concerned. The association thus formed was a sort of guild or trades union, or in the language of the time, a universitas magistrorum et scholarium. This was the first stage in the development of the early medieval university. In some cases, as at Paris, the governing body of the university was formed by the teachers alone; in others, as at Bologna, by both teachers and students; but in all cases precise rules for the conduct of business and the regulation of the internal economy of the guild were formulated at an early stage in its history. The municipalities and numerous societies which existed in Italy supplied plenty of models for the construction of such rules. We are, almost inevitably, unable to fix the exact date of the commencement of these voluntary associations, but they existed at Paris, Bologna, Salerno, Oxford, and Cambridge before the end of the 12th century. Whether such a loosely associated and self-constituted guild of students can be correctly described as a university is a doubtful point. These societies seem to have arisen in connection with the schools established by some church or monastery, and I believe that nearly all the medieval universities grew up under the protection of some bishop or abbot. They were not, however, ecclesiastical organizations, and though the bulk of their members were ordained, their connection with the church arose chiefly from the fact that clerks were then the only class of the community who were left free by the state to pursue their studies. The guild was thus at first in some undefined manner subject to the special authority of the bishop or his chancellor, from the latter of whom the head of the university subsequently took his title. The schools from which the universities sprang continued for a long time to exist under the direct control of the cathedral or monastic authorities, by the side of the guilds formed by the teachers on the more advanced subjects. The next stage in the advancement of the university was its recognition by the sovereign of the kingdom in which it was situated. A universitas scholarium, if successful in attracting students and acquiring permanency, always sought special legal privileges, such as the right of fixing the price of provisions and the power of trying legal actions in which its members were concerned. These privileges generally led to a recognition, explicit or implicit, of the guild by the crown as a stadium generale, that is, a body with the power to grant degrees which conferred a right to teaching anywhere within the kingdom. The university was frequently incorporated at about the same time. I believe no university was thus acknowledged before the end of the 12th century. Paris received its charter in 1200, and probably was the earliest university in Europe thus recognized. A medical school existed at Salerno as early as the 9th century, and a legal school at Bologna as early as 1138, but at these the education was technical rather than general. I therefore consider that the universities to which these schools respectively gave rise should be referred to a later date. The last step in the evolution of a medieval university was the acknowledgment of its corporate existence by the Pope or Emperor, and the recognition of its degrees as a title to teach throughout Christendom. Thenceforward it became a recognized member of a body of closely connected corporations. Paris was thus recognized in 1283. A medieval university therefore passed through three stages. First, it was a self-constituted guild of students. Second, legal privileges were conferred on it by the state, and usually it was incorporated. Third, it was recognized by the Pope, and its degrees declared current throughout the whole of Christendom. In later times the university was confined to degree granting bodies, and any other place of higher education was termed a studium generale. The standard of education in mathematics has been largely fixed by the universities, and most of the mathematicians of subsequent times have been closely connected with one or more of them, and therefore I may be pardoned for adding a few words on the general course of studies in a university in medieval times, referring the reader who wishes for further details as to their organization of studies, their system of instruction, and their constitution to my History of the Study of Mathematics at Cambridge, 1889. The students entered when quite young, sometimes not being more than 11 or 12 years old when first coming into residence. It is misleading to describe them as undergraduates, for their age, their studies, the discipline to which they were subjected, and their position in the university show that they should be regarded as schoolboys. The first 4 years of their residence were supposed to be spent in the study of trivium, i.e. Latin, grammar, logic, and rhetoric. The majority of students in quite early times did not progress beyond the study of Latin grammar. They formed an inferior faculty and were eligible only for the degree of Master of Grammar. But the more advanced students, and in later times all students, spent these years in the study of the trivium. The title of Bachelor of Arts was conferred at the end of this course, and signified that the student was no longer a schoolboy and therefore in pupillage. The average age of a commencing bachelor may be taken as having been about 17 or 18. Thus at Cambridge, in the presentation for a degree, the technical term still used for an undergraduate is juvenius, while that for a bachelor is vir. A bachelor could not take pupils, could teach only under special restrictions, and probably occupied a position closely analogous to that of an undergraduate nowadays. Some few bachelors proceeded to the study of civil or canon law, but it was assumed in theory that they next studied the quadrivium, the course for which took 3 years, and which included about as much science as was to be found in the pages of Boethius and Isidorus. The degree of Master of Arts was given at the end of this course. In the 12th and 13th centuries it was merely a license to teach. No one sought it who did not intend to use it for that purpose and to reside, and only those who had a natural aptitude for such work were likely to enter so ill paid a profession as that of a teacher. The degree was obtainable by any student who had gone through the recognized course of study and shewn that he was of good moral character. Outsiders were also admitted, but not as a matter of course. I may here add that toward the end of the 14th century students began to find that a degree had pecuniary value, and most universities subsequently conferred it only a condition that the new master should reside and teach for at least a year. A few years later the universities took a further step and began to refuse degrees to those who were not intellectually qualified. This power was assumed on the precedent of a case which arose in Paris in 1426 when the university declined to confer a degree on a student, a Slavonian, one Paul Nicholas, who had thus the distinction of being the first student ever plucked who had performed the necessary exercises in a very indifferent manner. He took legal proceedings to compel the university to grant the degree, but their right to withhold it was established. Although science and mathematics were recognized as the standard subjects of study for a bachelor, it is probably that until the Renaissance the majority of the students devoted most of their time to logic, philosophy, and theology. The subtleties of the scholastic theology and logic which were the favourite intellectual pursuit of these centuries, may seem to us dreary and barren, but it is only just to say that they afforded an intellectual exercise which fitted men at a later time to develop science, and certainly were in advance of what had been previously taught. We have now arrived at a time when the results of Arab and Greek science became known in Europe. The history of Greek mathematics has been already discussed. I must now temporarily leave the subject of medieval mathematics and trace the development of the Arabian schools to the same date. And I must then explain how the schoolmen became acquainted with the Arab and Greek textbooks and how their introduction affected the progress of European mathematics. End of part 12. Chapter 9 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 9. The Mathematics of the Arabs. The story of Arabian mathematics is known to us in general outlines, but we are as yet unable to speak with certainty on many of its details. It is, however, quite clear that while part of the early knowledge of the Arabs was derived from Greek sources, part was obtained from Hindu works, and that it was on those foundations that Arab science was built. I will begin by considering in turn the extent of the mathematical knowledge derived from these sources. Extent of mathematics obtained from Greek sources. According to their traditions, in themselves very probable, the scientific knowledge of the Arabs was at first derived from the Greek doctors who attended the caliphs at Baghdad. It is said that when the Arabian conquerors settled in towns they became subject to diseases which had been unknown to them in their life in the desert. The study of medicine was then confined almost entirely to Greeks, and many of these, encouraged by the caliphs, settled at Baghdad, Damascus, and other cities. Their knowledge of all branches of learning was far more extensive and accurate than that of the Arabs, and the teaching of the young, as has often happened in similar cases, soon fell into their hands. The introduction of the European science was rendered the more easy as various small Greek schools existed in the countries subject to the Arabs. There had for many years been one at Edessa among the Nestorian Christians, and there were others at Antioch, Emesa, and even at Damascus, which had preserved the traditions and some of the results of Greek learning. The Arabs soon remarked that the Greeks rested their medical science on the works of Hippocrates, Aristotle, and Galen, and these books were translated into Arabic by order of the Caliph Harun al-Rashid about the year 800. The translations excited so much interest that his successor al-Mamun (813–833) sent a commission to Constantinople to obtain copies of as many scientific works as was possible, while an embassy for similar purpose was also sent to India. At the same time a large staff of Syrian clerks was engaged, whose duty it was to translate the works so obtained into Arabic and Syriac. To disarm fanaticism, these clerks were at first termed the caliph's doctors, but in 851 were formed into a college, and their most celebrated member, Honan ibn Ishaq, was made its first president by the caliph Mutawakkil, 847 to 861. Honain and his son Ishaq ibn Honain revised the translations before they were finally issued. Neither of them knew much mathematics, and several blunders were made in the works issued on that subject, but another member of the college, Tabat ibn Korah, shortly published fresh editions which thereafter became the standard texts. In this way, before the end of the 9th century, the Arabs obtained translations of the works of Euclid, Archimedes, Apollonius, Ptolemy, and others, and in some cases these editions are the only copies of the books now extant. It is curious, as indicating how completely Diophantus has dropped out of notice, that as far as we know the Arabs got no manuscript of his great work until 150 years later, by which time they were already acquainted with the idea of algebraic notation and processes. Extent of mathematics obtained from Hindu sources. The Arabs had considerable commerce with India, and a knowledge of one or both of the two great original Hindu works on algebra had been thus obtained in the Caliphate of Al-Mansur, 754 to 775, though it was not until after 50 or 60 years later that they attracted much attention. The algebra and arithmetic of the Arabs were largely founded on these treatises, and I therefore devote this section to the consideration of Hindu mathematics. The Hindus, like the Chinese, have pretended that they are the most ancient people on the face of the earth, and that to them all sciences owe their creation. But it would appear from all recent investigations that these pretensions have no foundation, and in fact no science or useful art, except a rather fantastic architecture and sculpture, can be traced back to the inhabitants of the Indian peninsula prior to the Aryan invasion. This invasion seems to have taken place at some time in the latter half of the 5th century or in the 6th century after Christ, when a tribe of the Aryans entered India by the northwest frontier and established themselves as rulers over a large part of the country. Their descendants, wherever they have kept their blood pure, may still be recognized by their superiority over the races they originally conquered, but as is the case with the modern Europeans, they found the climate trying and gradually degenerated. For the first 2 or 3 centuries they however retained their intellectual vigor and produced 1 or 2 writers of great ability. Aryabhata. The first of these is Aryabhata, who was born at Patna in the year 476. He is frequently quoted by Brahmagupta, and in the opinion of many commentators he created algebraic analysis, though it has been suggested that he may have seen Diophantus's arithmetic. The chief work of Aryabhata with which we are acquainted is his Aryabhatia, which consists of the enunciations of various rules and propositions written in verse. There are no proofs, and the language is so obscure and concise that it long defied all efforts to translate it. The book is divided into 4 parts. Of these are devoted to astronomy and the elements of spherical trigonometry. The remaining part contains the enunciations of 33 rules in arithmetic, algebra, and plane trigonometry. It is probable that Aryabhata, like Brahmagupta and Bhaskara, who are mentioned next, regarded himself as an astronomer and studied mathematics only so far as it was useful to him in astronomy. In algebra, Aryabhata gives the sum of the first, second, and third powers of the first n natural numbers, the general solution of a quadratic equation, and the solution in integers of certain indeterminate equations of the first degree. His solutions of numerical equations have been supposed to imply that he was acquainted with the decimal system of numeration. In trigonometry he gives a table of natural sines of the angles in the first quadrant, proceeding by multiples of 3 3/4 degrees, defining a sine as a semichord of double the angle. Assuming that for the angle 3 3/4 degrees the sine is equal to the circular measure, he takes for its value 225, i.e. the number of minutes in the angle. He then enunciates a rule which is nearly unintelligible but probably the equivalent of the statement sine of n plus 1 alpha minus sine of n alpha equals sine n alpha minus sine of n minus 1 alpha minus sine n alpha times cosecant alpha, where alpha stands for 3 3/4 degrees, and working with this formula he constructs a table of sines and finally finds the value of sine 90 degrees to be 3438. This result is correct if we take 3.1416 as the value of pi, and it is interesting to note that this is the number which in another place he does give for pi. The correct trigonometrical formula is sine of n plus 1 alpha minus sine n alpha equals sine n alpha minus sine n minus 1 alpha minus 4 sine n alpha times sine squared alpha. Aryabhata therefore took 4 sine squared alpha as equal to cosecant alpha, i.e. he supposed that 2 sine alpha equals 1 plus 2 alpha, thus using the approximate values of sine alpha and sine 2 alpha given in his table, and this reduces to 2 times 225 equals 1 plus 449, and hence to that degree of approximation his formula is correct. A large proportion of the geometrical propositions which he gives are actually wrong. Brahmagupta. The next Hindu writer of considerable note is Brahmagupta, who is said to have been born in 598 and probably was alive about 660. He wrote a work in verse entitled Brahmasvuta Siddhanta, and that is the Siddhanta, or System of Brahma in Astronomy. In this 2 chapters, chapters 12 and 18 are devoted to arithmetic, algebra, and geometry. The arithmetic is entirely rhetorical. Most of the problems are worked out by the rule of 3, and a large proportion of them are on the subject of interest. In his algebra, which is also rhetorical, he works out the fundamental propositions connected with an arithmetical progression and solves a quadratic equation, but gives only the positive value to the radical. As an illustration of the problems given, I may quote the following, which was reproduced in slightly different forms by various subsequent writers, but I replaced the numbers by letters. 2 apes lived at the top of a cliff, height h, whose base was distant mh from a neighbouring village. One descended a cliff and walked down to the village, and the other flew up to a height x and then flew in a straight line to the village. The distance traversed by each was the same. Find x. Brahmagupta gave the correct answer, namely x equals mh divided by the quantity m plus 2. In the question, as enunciated originally, h equaled 100 and m equals 2. Brahmagupta finds solutions in integers of several indeterminate equations of the first degree using the same method as that now practiced. He states one indeterminate equation of the second degree, namely nx squared plus 1 equals y squared, and gives as its solution x equals 2t divided by the quantity t squared minus n, and y equals t squared plus n all divided by the quantity t squared minus n. To obtain this general form, he proved that if one solution either of that or certain allied equations could be guessed, the general solution could be written down, but he did not explain how one solution could be obtained. He added that the equation y squared equals nx squared minus 1 could not be satisfied by integral values of x and y unless n could be expressed as the sum of the squares of two integers. Curiously enough, the former of these equations was sent by Fermat as a challenge to Wallis and Lord Brouncker in the 17th century, and the latter found the same solution as Brahmagupta had previously done. It is perhaps worth noticing that the early algebraists, whether Greeks, Hindus, Arabs, or Italians, drew no distinction between the problems which led to determinate and those which led to indeterminate equations. It was only after the introduction of syncopated algebra that attempts were made to give general solutions to equations, and the difficulty of giving such solutions of indeterminate equations other than those of the first degree has led to their practical exclusion from elementary algebra. In geometry, Brahmagupta provided the Pythagorean property of a right angled triangle, Euclid 147. He gave expressions for the area of a triangle and that of a quadrilateral inscribable in a circle in terms of their sides, and shewed that the area of the circle was equal to that of a rectangle whose sides were the radius and semiperimeter. He was less successful in his attempts to rectify a circle, and his result is equivalent to taking the square root of 10 for the value of pi. He also determined the surface and volume of a pyramid and cone, and problems over which Aryabhata had blundered badly. The next part of his geometry is almost unintelligible, but it seems to be an attempt to find expressions for several magnitudes connected with a quadrilateral inscribed in a circle in terms of its sides. Most of this is wrong. It must not be supposed that in the original work all of the propositions which deal with any one subject are collected together, and it is only for convenience that I have tried to arrange them in that way. It is impossible to say whether the whole of Brahmagupta's results given above are original. He knew of Aryabhata's work, for he reproduces the table of signs there given, and it is likely that some progress in mathematics had been made by Aryabhata's immediate successors, and that Brahmagupta was acquainted with their works, but there seems to be no reason to doubt that the bulk of Brahmagupta's algebra and arithmetic is original, although perhaps influenced by Diophantus's writings. The origin of the geometry is more doubtful, probably some of it derived from Hero's works. Bhaskara. To make this account of Hindu mathematics complete, I may depart from the chronological arrangement and say that the remaining great Indian mathematician was Bhaskara, who was born in 1114. He is said to have been the lineal successor of Brahmagupta as head of the astronomical observatory at Ujjain. He wrote an astronomy of which only 4 chapters have been translated. Of these, one termed Lilavati is on arithmetic, the second, termed Bija Ganita, is on algebra, and the third and fourth are on astronomy and the sphere. This work was, I believe, known to the Arabs almost as soon as it was written, and influenced their subsequent writings, although they failed to utilize or extend most of the discoveries contained in it. The results thus became indirectly known in the West before the end of the 12th century, but the text itself was not introduced into Europe till within recent times. The treatise is in verse, but there are exemplary notes in prose. It is not clear whether it is original or whether it is merely an exposition of the results then known in India. But in any case, it is most probable that Bhaskara was acquainted with the Arab works which had been written in the 10th and 11th centuries, and with the results of Greek mathematics as transmitted through Arabian sources. The algebra is syncopated and almost symbolic, which marks a great advance over that of Brahmagupta and of the Arabs. The geometry is also superior to that of Brahmagupta, but apparently this is due to the knowledge of various Greek works obtained through Arabs. The first book, or Lilivanti, commences with a salutation to the god of wisdom. The general arrangement of the work may be gathered from the following table of contents. Systems of weights and measures. Next, decimal numeration, briefly described. Then the 8 operations of arithmetic, namely addition, subtraction, multiplication, division, square, cube, square root, cube root. reduction of fractions to a common denominator, fractions of fractions, mixed numbers, and the 8 rules applied to fractions. The rules of cipher, namely a plus or minus 0 equals a, 0 squared equals 0, the square root of 0 equals 0, a divided by 0 equals infinity. The solution of some simple equations which are treated as questions of arithmetic, the rule of false assumption, simultaneous equations of the first degree with applications, solutions of a few quadratic equations, rules of 3 and compound rules of 3 with various cases, interest, discount, partnership, time of filling a cistern by several fountains, barter, arithmetical progressions, and sums of squares and cubes, geometrical progressions, problems on triangles and quadrilaterals, approximate value of pi, some trigonometrical formulae, contents of solids, indeterminate equations of the first degree. Lastly, the book ends with a few questions on combinations. This is the earliest known work which contains a systematic exposition of the decimal system of numeration. It is possible that Aryabhata was acquainted with it, and it is most likely that Brahmagupta was so. But in Bhaskara's arithmetic we meet with the Arabic or Indian numerals and a sign for 0 as part of a well recognized notation. It is impossible at present to definitively trace the numerals further back than the 8th century, but there is no reason to doubt the assertion that they were in use at the beginning of the 7th century. Their origin is a difficult and disputed question. I mention below the view in which on the whole seems most probable and perhaps is now generally accepted, and I reproduce there some of the forms used in early times. To sum up the matter briefly, it may be said that the Lilavati gives the rules now current for addition, subtraction, multiplication, and division, as well as the more common processes in arithmetic, while the greater part of the work is taken up with the discussion of the rule of 3, which is divided up into direct and inverse, simple and compound, and is used to solve numerous questions chiefly on interest and exchange, the numerical questions being expressed in the decimal system of notation with which we are familiar. Bhaskara was celebrated as an astrologer no less than as a mathematician. He learnt by this art the event of his daughter Lilavati marrying would be fatal to himself. He therefore declined to allow her to leave his presence, but by way of consolation he not only called the first book of his work by her name, but propounded many of his problems in the form of questions addressed to her. For example, lovely and dear Lilavati, whose eyes are like a fawn's, tell me, what are the numbers resulting from 135 multiplied by 12? If thou be skilled in multiplication, whether by whole or by parts, whether by division or separation of digits, tell me, auspicious damsel, what is the quotient of the product when divided by the same multiplier? I may add here that the problems in the Indian works give a great deal of interesting information about the social and economic condition of the country in which they were written. Thus Bhaskara discusses some questions on the price of slaves, and incidentally remarks that a female slave was generally supposed to be most valuable when 16 years old, and subsequently to decrease in value in inverse proportion to the age. For instance, if when 16 years old she were worth 32 nishkas, her value when 20 would be represented by 16 multiplied by 32 divided by 20 nishkas. It would appear that, as a rough average, the female slave of 16 was worth about 8 oxen, which had worked for 2 years. The interest charged for money in India varied from 3.5% to 5% per month. Amongst other data thus given will be found the price of provisions and labour. The chapter termed Bijaganita commences with a sentence so ingeniously framed that it could be read as the enunciation of a religious or a philosophical or a mathematical truth. Bhaskara, after alluding to his Lilavati or arithmetic, states that he intends in his book to proceed to the general operations of analysis. The idea of the notation is as follows. Abbreviations and initials are used for symbols. Subtraction is indicated by a dot preceded above the coefficient of the quantity to be subtracted. Addition by the juxtaposition merely, but no symbols are used for multiplication, equality, or inequality, these being written at length. A product is denoted by the first syllable of the word subjoined to the factors between which a dot is sometimes placed. In a quotient or fraction, the divisor is written under the dividend without a line of separation. The two sides of an equation are written one under the other, confusion being prevented by the recital in words of all of the steps which accompany the operation. Various symbols for the unknown quantity are used, but most of them are the initials of names of colors, and the word color is often used as synonymous with unknown quantity. Its Sanskrit equivalent also signifies a letter, and letters are sometimes used either from the alphabet or from the initial syllables of subjects of the problem. In one or two cases, symbols are used for the given as well as for the unknown quantities. The initials of the words square and solid denote the second and third powers, and the initial syllable of the square root marks a surd. Polynomials are arranged in powers, the absolute quantity being always placed last and distinguished by an initial syllable denoting known quantity. Most of the equations have numerical coefficients, and the coefficients is always written after the unknown quantity. Positive or negative terms are indiscriminately allowed to come first, and every power is replaced on both sides of an equation, with a zero for the coefficient when the term is absent. After explaining his notation, Bhaskara goes on to give the rules for addition, subtraction, multiplication, division, squaring, and extracting the square root of algebraical expressions. He then gives the rules of cipher as in the Lilavati, solves a few equations, and lastly concludes with some operations on surds. Many of the problems are given in poetical settings with allusions to fair damsels and gallant warriors. Other chapters on algebra, trigonometry, and geometrical applications exist, and fragments of them have been translated by Colebrooke. Amongst the trigonometrical formulae is one which is equivalent to the equation d sine theta equals cos theta d theta. I have departed from the chronological order in treating here of Bhaskara, but as he was the only remaining Hindu writer of exceptional eminence, I thought it better to mention him at the same time as I was discussing his compatriots. It must be remembered, however, that he flourished subsequently to all the Arab mathematicians considered in the next section. The works with which the Arabs first became acquainted were those of Aryabhata and Brahmagupta, and it is doubtful if they ever made much use of the great treatise of Bhaskara. It is probable that the attention of the Arabs was called to the works of the first two of these writers by the fact that the Arabs adopted the Indian system of arithmetic and were thus led to look at the mathematical textbooks of the Hindus. The Arabs had always had considerable commerce with India, and with the establishment of their empire the amount of trade naturally increased. At that time, circa 700, they found the Hindu merchants beginning to use the system of numeration with which we are familiar and adopted it at once. This immediate acceptance of it was made the easier as they had no collection of science or literature written in another system, and it is doubtful whether they then proposed any but the most primitive system of notation for expressing numbers. The earliest definite date assigned for the use in Arabia of the decimal system of numeration is 773. In that year some Indian astronomical tables were brought to Baghdad, and it is almost certain that in these Indian numerals, including a zero, were employed. The development of mathematics in Arabia. In the preceding sections of this chapter I have indicated the two sources from which the Arabs derived their knowledge of mathematics, and have sketched out roughly the amount of knowledge obtained from each. We may sum the matter up by saying that before the end of the 8th century the Arabs were in possession of a good numerical notation and of Brahmagupta's work on arithmetic and algebra, while before the end of the 9th century they were acquainted with the masterpieces of Greek mathematics. Chapter 10 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball. Chapter 10. The Introduction of Arabian Works into Europe circa 1150 to 1450. In the last chapter but one I discussed the development of European mathematics to a date which corresponds roughly with the end of the Dark Ages, and in the last chapter I traced the history of the mathematics of the Hindus and the Arabs to the same date. The mathematics of the 2 or 3 centuries that follow and are treated in this chapter are characterized by the introduction of the Arabian mathematical textbooks and of Greek books derived from Arabian sources, and the assimilation of the new ideas thus presented. It was however from Spain and not from Arabia that Arabian mathematics came into Western Europe. The Moors had established their rule in Spain in 1747, and by the 10th or 11th century had attained a high degree of civilization. Though their political relations with the caliphs at Baghdad were somewhat unfriendly, they gave a ready welcome to the works of the great Arabian mathematicians. In this way the Arab translations of Euclid, Archimedes, Apollonius, Ptolemy, and perhaps of other Greek writers, together with the works of the Arabian algebraists, were read and commented on at the 3 great Moorish universities or schools of Granada, Cordova, and Seville. It seems probable that these works indicate the full extent of Moorish learning, but as all knowledge was jealously guarded from Christians, it is impossible to speak with certainty either on this point or on that of the time when Arab books were first introduced into Spain. The 11th century. The earliest Moorish writer of distinction of whom I find mention is Geber ibn Afla, who was born at Seville and died toward the latter part of the 11th century at Cordova. His works, which deal chiefly with astronomy and trigonometry, were translated into Latin by Gerard and published at Nuremberg in 1533. He seems to have discovered the theorem that the sines of the angles of a spherical triangle are proportional to the sines of the opposite sides. Another Arab of about the same date was Arzakel, who was living at Toledo in 1080. He suggested that the planets moved in ellipses, but his contemporaries with scientific intolerance declined to argue about a statement which was contrary to that made by Ptolemy in the Almagest. The 12th century. During the course of the 12th century, copies of the books used in Spain were obtained in Western Christendom. The first step towards procuring a knowledge of Arab and Moorish science was taken by an English monk, Adelhard of Bath, who, under the disguise of a Mohammedan student, attended some lectures at Cordova about 1120 and obtained a copy of Euclid's Elements. This copy, translated into Latin, was the foundation of all the editions known in Europe till 1533, when the Greek text was recovered. How rapidly a knowledge of the work spread we may judge when we recollect that before the end of the 13th century Roger Bacon was familiar with it, while before the close of the 14th century the first 5 books formed part of the regular curriculum of some, if not all, universities. The Enunciations of Euclid seem to have been known before Abelhard's time and possibly as early as the year 1000, though copies were rare. Abelhard also procured a manuscript of or contemporary on Al-Khwarizmi's work, which he likewise translated into Latin. He issued a textbook also on the use of the abacus. During the same century other translations of the Arab textbooks or commentaries on them were obtained. Amongst those who were most influential in introducing Moorish learning into Europe I may mention Abraham ben Ezra. Ben Ezra was born at Toledo in 1097, died at Rome in 1167. He was one of the most distinguished Jewish rabbis who had settled in Spain, where it must be recollected they were tolerated and even protected by the Moors on account of their medical skill. Besides some astronomical tables and an astrology, Ben Ezra wrote an arithmetic, a short analysis of which was published by O. Tequem in Liouville's journal for 1841. In this he explains the Arab system of numeration with 9 symbols and a 0, gives the fundamental processes of arithmetic, and explains the rule of 3. Another European who was induced by the reputation of the Arab schools to go to Toledo was Gerard, who was born at Crenoma in 1114 and died in 1187. He translated the Arab edition of the Almagest, the works of the Alhazen, and the works of the Alpharabius, whose name is otherwise unknown to us. In this translation of Ptolemy's work, which was made in 1136, the Arabic numerals are introduced. Gerard also wrote a short treatise on algorism, which exists in manuscript in the Bodleian Library at Oxford. He was acquainted with one of the Arab editions of Euclid's Elements, which he translated into Latin. Among the contemporaries of Gerard was John Hispalensis of Seville, who was originally a rabbi but was converted to Christianity and baptized under the name given above. He made translations of several Arab and Moorish works and also wrote an algorism which contains the earliest examples of the extraction of the square roots of numbers by the aid of the decimal notation. The 13th century. During the 13th century there was a revival of learning throughout Europe, but the new learning was, I believe, confined to a very limited class. The early years of this century are memorable for the development of several universities and for the appearance of 3 remarkable mathematicians, Leonardo of Pisa, Jordanus, and Roger Bacon, the Franciscan monk of Oxford. Leonardo Fibonacci, Filius Bonacci, generally known as Leonardo of Pisa, was born at Pisa in 1175. His father Bonacci was a merchant and was sent by his fellow townsmen to control the custom house at Bugia in Barbary. There Leonardo was educated, and he thus became acquainted with the Arabic system of numeration and also with Al-Khwarizmi's work on algebra, which was described in the last chapter. It would seem that Leonardo was entrusted with some duties in connection with the custom house which required him to travel. He returned to Italy about 1200 and in 1202 published a work called Algebra e Muqabala, the title being taken from Al-Khwarizmi's work, but generally known as the Liber Abaci. He there explains the Arabic system of numeration and remarks on its great advantages over the Roman system. He then gives an account of algebra and points out the convenience of using geometry to get rigid demonstrations of algebraical formulae. He shews how to solve simple equations, solves a few quadratic equations, and states some methods for the solution of indeterminate equations. These rules are illustrated by problems on numbers. All the algebra is rhetorical. This work had a wide circulation, and for the last 2 centuries remained a standard authority. The Liber Abaci is especially interesting in the history of arithmetic, since it practically introduced the use of the Arabic numerals into Christian Europe. The language of Leonardo implies that they were previously unknown to his countrymen, and he says that having to spend some years in Barbary, he there learned the Arabic system, which he found much more convenient than that used in Europe. He therefore published it in order that the Latin race might no longer be deficient in that knowledge. Now, Leonardo had read very widely and travelled Greece, Sicily, and Italy, and there is therefore every presumption that the system was not then commonly employed in Europe. Though Leonardo introduced its use into commercial affairs, it is probable that a knowledge of it as a method which was current in the East was previously not uncommon among travellers and merchants, for the intercourse between Christians and Mohammedans was sufficiently close for each to learn something of the language and common practices of the other. We can also hardly suppose that the Italian merchants were ignorant of the method of keeping accounts used by some of their best customers, and we must recollect too that there were numerous Christians who had escaped or been ransomed after serving the Mohammedans as slaves. It was however Leonardo that brought the system into general use, and by the middle of the 13th century a large proportion of the Italian merchants employed it by the side of the old system. The majority of the mathematicians must have already known the system from the works of Ben Ezra, Gerard, and John Hispalensis, but shortly after the appearance of Leonardo's book Alfonso of Castile in 1252 published some astronomical tables founded on observations made in Arabia, which were computed by Arabs and which were expressed in Arabic notation. Alfonso's tables had a wide circulation among men of science and were largely instrumental in bringing these numerals into universal use among mathematicians. By the end of the 13th century it was generally assumed that all scientific men would be acquainted with the system. Thus Roger Bacon, writing in that century, recommends the algorism, that is, the arithmetic founded on Arab notation, as a necessary study for theologians who ought, he says, to abound in the power of numbering. We may then consider that by the year 1300 or at least 1350 these numerals were familiar both to mathematicians and to Italian merchants. So great was Leonardo's reputation that the emperor Frederick II stopped at Pisa in 1225 in order to hold a sort of mathematical tournament to test Leonardo's skill, of which he had heard such marvellous accounts. The competitors were informed beforehand of the questions to be asked, some or all of which were composed by John of Palermo, who was one of Frederick's suite. This is the first time that we meet with an instance of those challenges to solve particular problems which were so common in the 16th and 17th centuries. The first question propounded was to find a number which was a square when either increased or decreased by 5 would remain a square. Leonardo gave an answer which is correct, namely 41/12. The next question, which was to find by the methods used in the 10th book of Euclid a line whose length x should satisfy the equation x cubed plus 2x squared plus 10x equals 20. Leonardo shewed by geometry that the problem was impossible, but he gave an approximate value of the root of the equation, namely approximately 1.3688081075, and is correct to 9 places of decimals. Another question was as follows. 3 men, A, B, and C, possess a sum of money, U, and their slaves being in the ratio 3:2:1. A takes away x, keeps half of it, and deposits the remainder with D. B takes away y, keeps 2/3 of it, deposits the remainder with D.
C takes away all that is left, namely z, keeps 5/6 of it, and deposits the remainder with D. The deposit with D is found to belong to A, B, and C in equal proportions. Find u, x, y, and z. Leonardo shewed that the problem was indeterminate and gave as one solution u equals 47, x equals 33, y equals 13, and z equals 1. The other competitors failed to solve any of these questions. The chief work of Leonardo is the Liber Abaci alluded to above. This work contains a proof of the well-known result: quantity a squared plus b squared times quantity c squared plus d squared equals quantity ac plus bd all squared plus bc minus ad quantity squared equals ad plus bc quantity squared plus bd minus ac quantity squared. He also wrote a geometry termed Practica Geometria, which was issued in 1220. This is a good compilation, and some trigonometry is introduced. Among other propositions and examples, he finds the area of a triangle in terms of its sides. Subsequently, he published a Liber Quadratorum dealing with the problem similar to the first of the questions propounded at the tournament. He also issued a tract dealing with determinate algebraical problems. These are all solved by the rule of false assumption in the manner explained above on page 104. Frederick II. The emperor Frederick II, who was born in 1194, succeeded to the throne in 1210 and died in 1250, was not only interested in science, but did as much as any other single man of the 13th century to disseminate a knowledge of the works of the Arab mathematicians in Western Europe. The universities of Naples and Padua remain as monuments of his munificence, having founded the former in 1224 and the latter in 1238. I have already mentioned that the presence of the Jews had been tolerated in Spain on account of their medical skill and scientific knowledge, and as a matter of fact the titles of physician and algebraist were for a long time nearly synonymous. Thus the Jewish physicians were admirably fitted both to get copies of the Arab works and to translate them. Frederick II made use of this fact to engage a staff of learned Jews to translate the Arab works which he obtained, though there is no doubt that he gave his patronage to them the more readily because it was singularly offensive to the Pope with whom he was engaged in a quarrel. At any rate, by the end of the 13th century the copies of Euclid, Archimedes, Apollonius, and Ptolemy, and some of the Arab works in algebra were obtainable from this source, and by the end of the next century were not uncommon. From this time, then, we may say that the development of science in Europe was independent of the aid of the Arabian schools. Jordanus. Among Leonardo's contemporaries was a German mathematician whose works were until the last few years almost unknown. This was Jordanus Neomarius, sometimes called Jordanus de Saxona or Teutonicus. Of the details of his life we know but little, save that he was elected general of the Dominican order in 1222. Professor Kurtze, who has made a special study of the subject, confers that the following works are due to Jordanus: Geometria Verdi Trianguli and De Similibus Arcubi, published by M. Kurtze in 1887 in volume 6 of the Releases of the Copernicus Society of Turin, published in German; De Isoperimetrie in Latin, and Arithmetic Demonstrated, also published in Latin, published by Faber Stapulensis at Paris in 1496, second edition, 1514. Algorithmus Demonstratus, published by J. Schoner at Nuremberg in 1534, and De Meris Datis, published by P. Trottlein in 1879 and edited in 1891 with comments by M. Kurtze in volume 36 of the Journal of Mathematics and Physics, published in German, or another publication of weights, published in Latin by P. Appian at Nuremberg in 1533 and reissued in Venice in 1565. And lastly, 2 or 3 tracts on Ptolemaic astronomy. If we assume, as Professor Kerza does, that these works have not been added to or improved by subsequent annotators, we must esteem Jordanus as one of the most eminent mathematicians of the Middle Ages. His knowledge of geometry is illustrated by his De Triangulis, De Similibus Arcubis, and De Isoperimetris. His most important book of these is the De Triangulis, which is divided into 4 books. The first book, besides a few definitions, contains 13 propositions on triangles which are based on Euclid's Elements. The second book contains 19 propositions mainly on the ratios of straight lines and their application to compare the areas of triangles. For example, one problem is to find a point inside a triangle so that the lines joining it to the angular points may divide the triangle into 3 equal parts. The third book contains 12 propositions, mainly concerning arcs and chords of circles. The fourth book contains 28 propositions, partly on the regular polygons and partly on miscellaneous questions such as the duplication and trisection problems. The Algorithmus Demonstratus contains practical use for the 4 fundamental processes, and Arabic numerals are generally but not always used. It is divided into 10 books dealing with properties of numbers, primes, perfect numbers, polygonal numbers, etc., ratios, powers, and the progressions. It would seem from it that Jordanus knew the general expression for the square of any algebraic multinomial. The De Numeris Datis consists of 4 books containing solutions to 115 problems. Some of these lead to simple or quadratic equations involving more than one unknown quantity. He shews a knowledge of proportions, but many of the demonstrations of his general propositions are only numerical illustrations of them. In several of the propositions of the Algorithmus de Numeris Datis, letters are employed to denote both known and unknown quantities, and they are used in the demonstrations of the rules of arithmetic as well as of algebra. As an example of this, I quote the following proposition from the De Numeris Datis, book 1, proposition 3, the object of which is to determine the 2 quantities whose sum and product are known. The translation says toward the end that if we subtract 84 minus x squared to get 16, we can solve for x to find that by taking away 16 from 84 we can solve for x squared, and then taking the square root of 64 we can then see that x is equal to 8. It will be noticed that Jordanus, like Diophantus and the Hindus, denotes addition by juxtaposition. Expressed in modern notation, his argument is as follows. Let the numbers be a plus b, which I will denote by gamma, and c. Then gamma plus c is given, hence gamma plus c quantity squared is known, denote it by e. Again gamma times c is given, denote it by d. Hence 4 times gamma times c, which is equal to 4 times d, is known, denoted by f. Then gamma minus c quantity squared is equal to e minus f, which is known, denoted by g. Therefore gamma minus c equals the square root of g, which is known, denoted by h. Hence gamma plus c and gamma minus c are known, and therefore gamma and c can be at once found. It is curious that he should have taken a sum like a plus b for one of his unknowns. In his numerical illustration he takes the sum to be 10 and the product to be 21. The above works are the earliest instances known in European mathematics of syncopated algebra, in which letters are used for algebraical symbols. It is probable that the Algorithmus was not generally known until it was printed in 1534, and it is doubtful how far the works of Jordanus exercised any considerable influence on the development of algebra. In fact, it constantly happens in the history of mathematics that improvements in notation or discoveries are made long before they are generally adopted or their advantages realized. Thus the same thing may be discovered over and over again, and it is not until the general standard of knowledge requires some such improvement, or it is enforced by someone whose zeal or attainments compel attention, that it is adopted and becomes part of the science. Jordanus, in using letters or symbols to represent any quantities which occur in analysis, was far in advance of his contemporaries. A similar notation was tentatively introduced by the other and later mathematicians, but it was not until it had been thus independently discovered several times that it came into general use. It is not necessary to describe in detail the mechanics, optics, or astronomy of Jordanus. The treatment of mechanics throughout the Middle Ages was generally unintelligent. No mathematicians of the same ability as Leonardo and Jordanus appear in the history of the subject for over 200 years. Their individual achievements must not be taken to imply the standard of knowledge then current, but their works were accessible to students in the following 2 centuries, though there were not many who seem to have derived much benefit therefrom, or who attempted to extend the bounds of arithmetic and algebra as there expounded. During the 13th century the most famous centres of learning in Western Europe were Paris and Oxford, and I must now refer to the more eminent members of those schools. Hollywood. I will begin by mentioning John de Hollywood, whose name is perhaps better known in the Latinized form of Sacrobosco. Hollywood was born in Yorkshire and educated at Oxford, but after taking his master's degree he moved to Paris and taught there until his death in 1244 or 1246. His lectures on algorism and algebra are the earliest of which I can find mention. His work on arithmetic was for many years a standard authority. It was printed at Paris in 1496 and was reissued in Halliwell's Rara Mathematica, London, 1841. He also wrote a treatise on the sphere which was made public in 1256. This had wide circulation and indicates how rapidly a knowledge of mathematics was spreading. Besides these, 2 pamphlets by him entitled respectively De Computo Ecclesiastico and De Astrolabio are still extant. Roger Bacon. Another contemporary of Leonardo and Jordanus was Roger Bacon, who for physical science did work somewhat analogous to what they did for arithmetic and algebra. Roger Bacon was born near Ilchester in 1214 and died at Oxford in June 11, 1294. He was the son of royalists, most of whose property had been confiscated at the end of the civil wars. At an early age he was entered as a student at Oxford, and is said to have taken orders in 1233. In 1234 he removed to Paris, then the intellectual capital of Western Europe, where he lived for some years, devoting himself especially to languages and physics, and there he spent on books and experiments all that remained of his family property and his savings. He returned to Oxford soon after 1240, and there for the following 10 or 12 years he laboured incessantly, being chiefly occupied in teaching science. His lecture room was crowded, but everything that he earned was spent in buying manuscripts and instruments. He tells us that altogether at Paris and Oxford he spent over £2000 in this way, a sum which represents at least £20,000 nowadays. Bacon strove hard to replace logic in the university curriculum by mathematical and linguistic studies, but the influences of the age were too strong for him. His glowing eulogy on the divine mathematics, which should form the foundation of a liberal education and which alone can purge the intellect and fit the student for the acquirement of all knowledge, fell on deaf ears. We can judge how small was the amount of geometry which was implied in the quadrivium when he tells us that in geometry few students at Oxford read beyond Euclid 1.5, though we might perhaps have inferred as much from the character of the work of Boethius. At last, worn out, neglected, and ruined, Bacon was persuaded by his friend Grosseteste, the great bishop of Lincoln, to renounce the world and take on the Franciscan vows. The society to which he now found himself confined was singularly uncongenial to him, and he beguiled the time by writing on scientific questions and perhaps lecturing. The superior of the order heard of this, and in 1257 forbade him to lecture or publish anything under penalty of the most severe punishments, and at the same time directed him to take up his residence at Paris, where he could be more closely watched. Clement IV, when in England, had heard of his abilities, and in 1266, when he became pope, invited Bacon to write. The Franciscan order reluctantly permitted him to do so, but they refused him any assistance. With great difficulty Bacon obtained sufficient money to get paper and the loan of books, and within the short space of 15 months he produced in 1267 his Opus Majus, with 2 supplements which summarized all that was then known in science, and laid down the principles of which not only science but philosophy and literature should be studied. He stated as the fundamental principle that the study of natural science must rest solely on experiment, and in the 4th part he explained in detail how all sciences rest ultimately on mathematics, and progress only when their fundamental principles are expressed in mathematical form. Mathematics, he says, should be regarded as the alphabet of all philosophy. The results that he arrived at in this and his other works are nearly in accordance with modern ideas, but were too far in advance of that age to be capable of appreciation or perhaps even of comprehension, and it was left for later generations to rediscover his works and give him that credit of which he never experienced in his lifetime. In astronomy he laid down the principles for a reform of the calendar, explained the phenomenon of shooting stars, and stated that the Ptolemaic system was unscientific insofar as it rested on the assumption that circular motion was the natural motion of a planet, while the complexity of the explanations required make it improbable that the theory was true. In optics he enunciated the laws of reflection and, in a general way, of refraction of light, and used them to give a rough explanation of the rainbow and of magnifying glasses. Most of his experiments in chemistry were directed to the transmission of metals and led to no result. He gave the composition of gunpowder, but there is no doubt that it was not his own invention, though it is the earliest European mention of it. On the other hand, some of his results in these subjects appear to be guesses which are more or less ingenious, while certain statements he makes are certainly erroneous. In the years immediately following the publication of his Opus Majus, he wrote numerous works which developed in detail the principles there laid down. Most of these have now been published, but I do not know of the existence of any complete edition. They deal only with the applied mathematics and physics. Clement took no notice of the great work for which he had asked, except to obtain leave for Bacon to return to England. On the death of Clement, the general of the Franciscan order was elected pope and took the title of Nicholas IV. Bacon's investigations had never been approved of by his superiors, and he was now ordered to return to Paris, where we are told he was immediately accused of magic. He was condemned in 1280 to imprisonment for life, and was released only about a year before his death. Campanus. The only other mathematician of this century whom I need mention is Giovanni Campano, or in the Latinized form Campanus, a canon of Paris. A copy of Adelhard's translation of Euclid's Elements fell into the hands of Campanus, who issued it as his own. He added a commentary thereon in which he discussed the properties of a regular reentrant pentagon. This edition was printed by Ratdolt in Venice in 1482. Besides some minor works, Campanus wrote Theory of the Planets, which was a free translation of the Almagest. The 14th century. The history of the 14th century, like that of the one preceding it, is mostly concerned with the introduction and assimilation of the Arabian mathematical textbooks and the Greek books derived from Arabian sources. Bradwardine. A mathematician of this time, who is perhaps sufficiently influential to justify a mention here, is Thomas Bradwardine, an archbishop of Canterbury. Bradwardine was born at Chester at about 1290. He was educated at Merton College, Oxford, and subsequently lectured in that university. From 1335 to the time of his death he was chiefly occupied with the politics of the church and state. He took a prominent part in the invasion of France, the capture of Calais, and the victory over Cressy. He died at Lambeth in 1349. His mathematical works, which were probably written when he was at Oxford, are 1. Treatise of the Proportions in Latin, printed at Paris in 1495. Speculative Arithmetic, also in Latin, printed at Paris in 1502. Speculative Geometry, printed in Latin at Paris in 1511. And the Quadrature of the Circle, also in Latin, printed at Paris in 1495. They probably give a fair idea of the nature of the mathematics then read at an English university. Oresmus. Nicholas Oresmus was another writer of the 14th century who is said in most histories of mathematics to have influenced the development of the subject. He was born at Caen in 1323, became the confidential adviser of Charles V, by whom he was made tutor to Charles VI, and subsequently was appointed bishop of Lisieux, at which city he died in July 11, 1382. He wrote the Algorismus Proportionum, in which the idea of fractional indices is introduced, and in the eyes of his contemporaries was prominent as a mathematician not less than as an economist and theologian. But I do not propose to discuss his writings. The treatise on which his reputation chiefly rests deals with the question of coinage and commercial exchange. From the mathematical point of view it is noticeable only for the use of vulgar fractions and the introduction of symbols for them. By the middle of this century Euclidean geometry as expounded by Campanus and algorism were fairly familiar to all professed mathematicians, and the Ptolemaic astronomy was also generally known. About this time the almanacs began to add to the explanation of the Arabic symbols of the rules for addition, subtraction, multiplication, and division, de algorismo. The more important calendars and other treatises also inserted a statement of the rules of proportion, illustrated by various practical questions. In the latter half of this century there was a general revolt of the universities against the intellectual tyranny of the schoolmen. This was largely due to Petrarch, who to his own generation was celebrated as a humanist rather than as a poet, and who exerted all his power to destroy scholasticism and encourage scholarship. The result of these influences on the study of mathematics may be seen in the changes then introduced in the study of the quadrivium. The stimulus came from the University of Paris, where a statute to that effect was passed in 1366, and a year or two later similar regulations were made at Oxford and Cambridge. Unfortunately, no textbooks are mentioned. We can however form a reasonable estimate of the range of mathematical reading required by looking at the statutes of the universities of Prague, founded in 1348, of Vienna, founded in 1365, and of Leipzig, founded in 1389. By the statutes of Prague, dated 1384, candidates for the bachelor's degree were required to have read Hollywood's treatise on the sphere, and candidates for the master's degree to be acquainted with the first 6 books of Euclid, optics, hydrostatics, the theory of the lever, and astronomy. Lectures were actually delivered on arithmetic, on the art of reckoning with the fingers, and the algorithm of integers, on almanacs, which probably meant elementary astrology, and on the Almagest, that is, on Ptolemaic astronomy. There is, however, some reason for thinking that mathematics received far more attention here than was then usual at other universities. At Vienna in 1389 the candidate for a master's degree was required to have read 5 books of Euclid: Common Perspective, Proportional Parts, the Measurement of Superficies, and the Theory of the Planets. The last book named is the treatise by Campanus, which was founded on that by Ptolemy. This was a fairly respectable mathematical standard, but I would remind the reader that there was no such thing as plucking in a medieval university. The student had to keep an act or give a lecture on certain subjects, but whether he did it well or badly he got his degree, and it is probable that it was only the few students whose interests were mathematical who really mastered the subjects mentioned above. The 15th century. A few facts gleaned from the history of the 15th century tend to shew that the regulations about the study of the quadrivium were not seriously enforced. The lecture lists for the years 1437 and 1438 of the University of Leipzig, the statutes of which are almost identical with those of Prague as quoted above, are extant and shew that the only lectures given there on mathematics in those years were confined to astrology. The records of Bologna, Padua, and Pisa seem to imply that there also astrology was the only scientific subject taught in the 15th century, and even as late as 1598 the professor of mathematics at Pisa was required to lecture on the Quadripartitum, an astrological work purporting, probably falsely, to have been written by Ptolemy. The only mathematical subjects mentioned in the registers of the University of Oxford, as read there between the years 1449 and 1463, were Ptolemy's astronomy, or some commentary on it, and the first 2 books of Euclid. Whether most students got as far as this is doubtful. It would seem from the edition of Euclid published at Paris in 1536 that after 1452 candidates for the master's degree at that university had to take an oath that they had attended lectures on the first 6 books of Euclid's Elements. Beldomondi. The only writer of this time that I need mention here is Protosimo Beldomondi of Padua, born about 1380, who wrote an algoristic arithmetic published in 1410, which contains a summation of a geometrical series and some geometrical works. For further details see Boncampagne's Bulletino de Bibliographia, volumes 12 and 18. By the middle of the 15th century printing was invented, and the facilities it gave for disseminating knowledge were so great as to revolutionize the progress of the science. We have now arrived at a time when the results of Arab and Greek science were known in Europe, and this perhaps then is as good a date as can be fixed for the close of this period and the commencement of that of the Renaissance. The mathematical history of the Renaissance begins with the career of Regiomontanus, but before proceeding with the general history it will be convenient to collect together the chief facts connected with the development of arithmetic during the Middle Ages and the Renaissance. To this the next chapter is devoted. End of part 14.
Chapter 11 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 11. The development of arithmetic, circa 1300 to 1637. We have seen in the last chapter that by the end of the 13th century the Arabic arithmetic had been fairly introduced into Europe and was practiced by the side of the older arithmetic which was founded on the work of Boethius. It will be convenient to depart from the chronological arrangement and briefly to sum up the subsequent history of arithmetic, but I hope by references in the next chapter to be the inventions and the improvements in arithmetic here described, I shall be able to keep the order of events and discoveries quite clear. The older arithmetic consisted of two parts: practical arithmetic, or the art of calculation, which was taught by means of the abacus and possibly the multiplication table, and theoretical arithmetic, by which was meant the ratios and proportions of the numbers taught according to Boethius, a knowledge of the latter being confined to professed mathematicians. The theoretical part of this system continued to be taught till the middle of the 15th century, and the practical part of it was used by the smaller tradesmen in England, Germany, and France till the beginning of the 17th century. The new Arabian arithmetic was called algorism, or the art of al-Khwarizmi, to distinguish it from the old or Boethian arithmetic. The textbooks on algorism commenced with the Arabic system of notation and began by giving rules for addition, subtraction, multiplication, and division. The principles of proportion were then applied to various practical problems, and the books usually concluded with the general rules for many of the common problems of commerce. Algorism was in fact a mercantile arithmetic, though at first it also included all that was then known as algebra. Thus, algebra had its origin in arithmetic, and to most people the term universal arithmetic, by which it was sometimes designated, conveys a more accurate impression of its objects and methods than the more elaborate definitions of modern mathematicians, certainly better than the definitions of Sir William Hamilton as the science of pure time, or that of De Morgan as the calculus of succession. No doubt logically there is a marked distinction between arithmetic and algebra, for the former is a theory of discrete magnitude while the latter is that of continuous magnitude, but a scientific distinction such as this is of quite recent origin, and the idea of continuity was not introduced into mathematics before the time of Kepler. Of course, the fundamental rules of this algorithm were not at first strictly proved, that is, the work of advanced thought, but until the middle of the 17th century there was some discussion of the principles involved. Since then, very few arithmeticians have developed to justify or prove the process used, or to do more than enunciate the rules and illustrate their use by numerical examples. I have alluded frequently to the Arabic system of numerical notation. I may therefore conveniently begin by a few notes on the history of the symbols now current. Their origin is obscure and has been much disputed. On the whole, it seems probable that the symbols for the numbers 4, 5, 6, 7, and 9, and possibly 8 too, are derived from the initial letters of the corresponding words in the Indo-Bactrian alphabet, in use in the north of India, perhaps 150 years before Christ. That the symbols for the numbers 2 and 3 are derived respectively from 2 and 3 parallel pen strokes written cursively, and similarly that the symbol for the number 1 represents a single pen stroke. Numerals of this type were in use in India before the end of the 2nd century of our era. The origin of the symbol for 0 is unknown. It is not impossible that it was originally a dot inserted to indicate a blank space, or it may represent a closed hand, but these are mere conjectures. There is reason to believe that it was introduced in India towards the close of the 5th century of our era, but the earliest writing now extant in which it occurs is assigned to the 8th century. The numerals used in India in and after the 8th century are termed Devanagari numerals, and their forms are shewn in the first line of the table given on the next page.
These forms were slightly modified by the Eastern Arabs, and the resulting symbols were again slightly modified by the Western Arabs or Moors. It is perhaps probable that at first the Spanish Arabs discarded the use of the symbol for 0 and only reinserted it when they found how inconvenient the omission proved. The symbols finally used by the Arabs are termed Gobar numerals. From Spain or Barbary, the Gobar numerals are passed into Western Europe. The further evolution of the forms of the symbols to those which we are now familiar is seen by facsimiles of the numerals used at different times. From 1500 onwards, the symbols employed are practically the same as those now in use. The evolution of the symbols by the Arabs proceeded almost independently of European influence. There are minute differences in the forms used by various writers, and in some case alternative forms. But leaving now the history of the exotic symbols, I proceed to discuss their introduction into the general use and the development of algoristic arithmetic. I have already explained how men of science, and particularly astronomers, have become acquainted with the Arabic system by the middle of the 13th century. The trade of Europe during the 13th and 14th centuries was mostly in Italian hands, and the obvious advantages of the algoristic system led to its general adoption in Italy for the mercantile purposes, though not without considerable opposition. Thus an edict was issued at Florence in 1299 forbidding bankers to use Arabic numerals, and the authorities of the University of Padua in 1348 directed that a list should be kept of books for sale with the prices marked non per cifras sed per litteras claras. The rapid spread of the use of Arabic numerals and arithmetic through the rest of Europe seems to have been quite as largely due to the makers of almanacs and calendars as to the merchants and men of science. These calendars had quite a wide circulation in medieval times. They were of two distinct types. Some of them were composed with a special reference to ecclesiastical purposes and contained the dates of the different festivals and fasts of the church for a period of some 7 or 8 years in advance, as well as notes on church ritual. Nearly every monastery and church of any pretensions possessed one of these, and numerous specimens are still extant. Those of the second type were specially written for the use of astrologers and physicians, and the better specimens contain notes on various scientific subjects, especially medicine and astronomy. These were not then uncommon, but since it was only rarely that they found their way into any corporate library, specimens are now rather scarce. It was the fashion to use the Arabic symbols in ecclesiastical works, while their occurrence in all astronomical tables and their oriental origin, which savoured of magic, secured their use in calendars intended for scientific purposes. Thus the symbols were generally employed in both kinds of almanacs, and there were few if any specimens in calendars issued after the year 1300 in which an explanation of their use is not included. Toward the middle of the 14th century, the rules of arithmetic del algorismo were also added, and by the year 1400 we may consider that the Arabic symbols were generally known throughout Europe, and were used in most scientific and astronomical works. Most merchants outside Italy continued, however, to keep their accounts in Roman numerals till about 1550, and monasteries and colleges till about 1650, though in both cases it is probable that in and after the 15th century the processes of arithmetic were performed in the algoristic manner. No instance of a date or number being written in Arabic numerals is known to occur in any English parish register or in the court rolls of any English manor before the 16th century, but in the rent roll of the St Andrews Chapter, Scotland, the Arabic numerals were used in writing an entry for the year 1490. The Arabic numerals were introduced into Constantinople by Planudes about the same time as into Italy. The history of mercantile arithmetic in Europe begins then with its use by Italian merchants, and it is especially to the Florentine traders and writers that we owe its early development and improvement. It was they who invented the system of bookkeeping by double entry. In this system, every transaction is entered onto the credit side in one ledger and on the debtor side in another. Thus, if cloth be sold to A, A's account is debited with the price, and the stock book containing the transactions in cloth is credited with the amount sold. It was they too who arranged the problems to which arithmetic could be applied in different cases, such as the rule of three, interest, profit and loss, etc. They also reduced the fundamental operations of arithmetic to seven in reverence, says Pacioli, of the seven gifts of the Holy Spirit, namely numeration, addition, subtraction, multiplication, division, raising to powers, and extraction of roots. Brahmagupta has enumerated 20 processes besides 8 subsidiary ones, and has stated that a distinct and several knowledge of these was essential to all who wished to be calculators. And whatever may be thought of Pacioli's reason for the alteration, the consequent simplification of the elementary processes was satisfactory. The operations of algoristic arithmetic were at first very cumbersome. The chief improvements subsequently introduced into the early Italian algorithm was 1. The simplification of the 4 fundamental processes, 2. The introduction of signs for plus, minus, and equality, and, though not so important, for multiplication and division. 3. The invention of logarithms, and 4. The use of decimals. I will consider these in succession. 1. In addition and subtraction, the Arabs usually worked from left to right. The modern plan of working from right to left is shorter. It is said to have been introduced by an Englishman named Garth, of whose life I can find no account. The old plan continued in partial use till about 1600. Even now, it would be more convenient in approximations where it is necessary to keep only a certain number of places of decimals. The Indians and Arabs had several systems of multiplication. These were all somewhat laborious, and were made the more so as multiplication tables, if not unknown, were at any rate used but rarely. The operation was regarded as one of considerable difficulty, and the test of the accuracy of the result by casting out the nines was invented by the Arabs as a check on the correctness of the work. Various other systems of multiplication were subsequently employed in Italy, of which several examples are given by Pacioli and Tartaglia, and the use of multiplication table, at least as far as 5 times 5, became common. From this limited table, the resulting product of the multiplication of all numbers up to 10 times 10 can be deduced by what was termed the regula ignavi. This is a statement of the identity 5 plus a times 5 plus b equals 5 minus a times 5 minus b plus 10 multiplied by the quantity a plus b. The rule was usually enunciated in the following form. Let the number 5 be represented by the open hand, the number 6 by the hand with one finger closed, the number 7 by the hand with 2 fingers closed, the number 8 by the hand with 3 fingers closed, and the number 9 by the hand with 4 fingers closed. To multiply one number by another, let the multiplier be represented by one hand and the number multiplied by the other according to the above convention. Then the required answer is the product of the number of fingers, counting the thumb as a finger, open in the one hand by the number of fingers open in the other, together with 10 times the total number of fingers closed. The system of multiplication now in use seems to have been first introduced at Florence. The difficulty which all but professed mathematicians experience in the multiplication of large numbers led to the invention of several mechanical ways of effecting the processes. Of these, the most celebrated is that of Napier's rods, invented in 1617. In principle, it is the same as a method which had been long in use in both India and Persia, and which has been described in the diaries of several travellers, and notably in the Travels of Sir John Chardin in Persia, published in London 1686. To use the method, a number of rectangular slips of bone, wood, metal, or cardboard are prepared, and each of them divided by cross lines into 9 little squares, a slip being generally about 3 inches long and a third of an inch across. In the top square, one of the digits is engraved, and the results of multiplying it by 2, 3, 4, 5, 6, 7, 8, and 9 are respectively entered in the 8 lower squares. Where the result is a number of 2 digits, the 10 digit is written above and to the left of the unit digit and separated from it by a diagonal line. The slips are usually arranged in a box. Suppose we wish to multiply 2985 by 317. The process as affected by the use of these slips is as follows. The slips headed 2, 9, 8, and 5 are taken out of the box and put side by side, arranged with their columns adjacent. The 7th row of those columns contain the product of multiplying each of these digits by 7. 14, 63, 56, and 35. Each of those numbers arranged along a diagonal, 1 above the 4, 6 above the 3, 5 above the 6, and 3 above the 5, with the tens digit above the diagonal and the units digit below. One may now take each of these tens digits and place them along a row to obtain 1653. The ones digits of these numbers may be placed beneath this arrangement but shifted 1 column to the right, such that we're adding 1653 to 4365, except that the 4365 is shifted 1 column to the right. Adding 5 to nothing gets 5, 3 and 6 make 9, 5 and 3 make 8, 6 and 4 make 10, carry the 1, 1 and 1 is 2. The result of multiplying 2985 by 7 is the number 20,895. Hence the result of multiplying by 7, 1, and 3 can be successively determined in the same way, and the required answer, namely the product of 2985 by 713, is then obtained by addition. The whole process is written such that the result is 946,245. The modification introduced by Napier in his Radiologia, published in 1617, consisted merely in replacing each slip by a prism with square ends, which he called a rod, each lateral face being divided and marked in the same way as one of the slips above described. These rods not only economized space but were easier to handle, and were arranged in such a way as to facilitate the operations required. If multiplication was considered difficult, division was first regarded as a feat which could only be performed by skilled mathematicians. The method commonly employed by the Arabs and Persians for the division of one number by another will be sufficiently illustrated by a concrete instance. Suppose we require to divide 17,978 by 472. A sheet of paper is divided into as many vertical columns as there are figures in the number to be divided. The number to be divided is written at the top and the divisor at the bottom, the first digit of each number being placed at the left hand side of the paper. Then, taking the left hand column, 4 will go into 1 no times. Hence the first figure in the dividend is 0, which is written under the last figure of the divisor. This is represented in figure 1. Next, rewrite the 472 immediately above its former position, but shifted 1 place to the right, and cancel the old figures. The 4 will go into 17 4 times. But as on trial it is found that the 4 is too big for the first digit of the dividend, 3 is selected, 3 is therefore written below the last digit of the divisor next to the digit of the dividend last found. The process of multiplying the divisor by 3 and subtracting from the number to be divided is indicated in figure 2, and shews that the remainder is 3,818. A similar process is then repeated, i.e. 472 is divided into 3818, shewing that the quotient is 38 and the remainder is 42. Thus represented as in the next figure, which shews that the whole operation. The method described above never found much favour in Italy. The present system was in use there as early as the beginning of the 14th century, but the method generally employed was that known as the galley or scratch system. The following example from Tartaglia, in which it is required to divide 1330 by 84, will serve to illustrate this method. The process is as follows. First, write the 84 beneath the 1330, such that 84 is below the middle two digits. Then 84 will go into 133 once, hence the first figure in the quotient is 1. Now 1 times 8 is 8, which is subtracted from 13 leaves 5. Write this above the 13 and cancel the 13 and the 8, which we have as the result of the first step. Now 1 times 4 equals 4, which subtracted from 53 leaves 49. Insert the 49 and cancel the 53 and the 4, and we have as the next step showing a remainder of 490. We have now to divide 490 by 84, hence the next figure in the quotient will be 5, and rewriting the divisor we have 15. The medieval writers were acquainted with the method now in use, but considered the scratch method more simple. In some cases the latter is very clumsy, and as may be illustrated by the following example to take from Pacioli. The object is to divide 234 by 100. The result obtained fills up with zeros, we get 234. The galley method was used in India, and the Italians may have derived it thence. In Italy it became obsolete somewhere about 1600, but it continued in partial use for at least another century in other countries. I should add that Napier's rods can be and sometimes were used to obtain the result of dividing one number by another. 2. The signs plus and minus to indicate addition and subtraction occur in Widman's arithmetic published in 1489. But were first brought into general notice, at any rate, as symbols of operation by Stiefel in 1554. I believe I am correct in saying that Vieta in 1591 was the first well-known writer who used these signs consistently throughout his work, and it was not until the beginning of the 17th century that they became recognized and well-known symbols. The equal sign to denote equality was introduced by Ricord in 1557. 3. The invention of logarithms, without which many of the numerical calculations which have constantly to be made would be practically impossible, was due to Napier of Merchistown. The first public announcement of the discovery was made in the Mercifi Logarithmorium Canonis Descriptio, published in 1614, and of which an English translation was issued in the following year, but he had privately communicated a summary of his results to Tycho Brahe as early as 1594. In this work Napier explains the nature of logarithms by a comparison between corresponding terms of an arithmetical and geometrical progression. He illustrates their use and gives tables of the logarithms, the sines and tangents of all angles in the first quadrant for differences of every minute, calculated to 7 places of decimals. His definition of the logarithm of a quantity n was what we should now express by 10 to the power of 7 natural log 10 to the 7 divided by n. This work is the more interesting to us as it is the first valuable contribution to the progress of mathematics which was made by any British writer. The method by which the logarithms were calculated was explained in the Constructio, a posthumous work issued in 1619. It seems to have been very laborious and depended either on direct involution and evolution or on the formations of geometrical means. The method by finding the approximate value of a convergent series was introduced by Newton, Cotes, and Euler. Napier had determined to change the base to one which was a power of 10, but died before he could effect it. The rapid recognition throughout Europe of the advantages of using logarithms in practical calculations was mainly due to Briggs, who was one of the earliest to recognize the value of Napier's invention. Briggs at once realized that the base to which Napier's logarithms were calculated were very inconvenient. He accordingly visited Napier in 1616 and urged a change to a decimal base, which was recognized by Napier as an improvement. On his return, Briggs immediately set to work to calculate tables of a decimal base, and in 1617 brought out a table of logarithms of the numbers from 1 to 1000, calculated to 14 places of decimals. He subsequently, in 1624, published tables of the logarithms of additional numbers and of various trigonometrical functions. His logarithms of the natural numbers are equal to those to base 10 when multiplied by 10 to the 8, and of the sines of the angles to those to the base 10 when multiplied by 10 to the 12. A table of the logarithms to 7 places of decimals of the sines and tangents of angles in the first quadrant have been brought out in 1620 by Edmund Gunter, one of the Gresham lecturers, who was the inventor of the words cosine and cotangent. The calculation of the logarithms of 70,000 numbers which had been omitted by Briggs from his tables in 1624 was performed by Adrian Vlach and published in 1628. With this addition, the table gave the logarithms of all numbers from 1 to 101,000. The Arithmetica Logarithmica of Briggs and Vlach are subsequently the same as the existing tables. Parts have at different times been recalculated, but no tables of an equal range and fullness entirely founded on fresh computations have been published since. These tables were supplemented by Briggs' Trigonometrica Britannica, which contains tables not only of the logarithms of the trigonometrical functions, but also of their natural values. It was published posthumously in 1633. By 1630, tables of logarithms were in general use. 4. The introduction of the decimal notation for fractions is also, in my opinion, due to Briggs. Stevinus had in 1585 used a somewhat similar notation, for he wrote a number such as 25.379 in the form of 25, 3 followed by a tick, 7 followed by 2 ticks, and 9 followed by 3 ticks, or in the form 25 and a 0 circle followed by a 3 with a 1 circle, followed by a 7 with a 2 and a circle, and followed finally by 9, followed by a 3 in a circle. And Napier in 1617 in his essay on rods had adopted the former notation. But these writers had employed the notation only as a concise way of stating the results, and made no use of it as an operative form. The same notation occurs, however, in the tables published by Briggs in 1617, and would seem to have been adopted by him in all of his works, and though it is difficult to speak with absolute certainty, I have myself but little doubt that there be employed the symbol as an operative form. In Napier's Posthumous Constructio, published in 1619, it is defined and used systematically as an operative form, and as this work was written after consultation with Briggs circa 1615 to 16, and probably was revised by the latter before it was issued, I think it confirms the view that the invention is due to Briggs and was communicated by him to Napier. At any rate, it was not employed as an operative form by Napier in 1617, and, if Napier were then acquainted with it, it must be supposed that he regarded its use as unsuitable in ordinary arithmetic. Before the 16th century, fractions were commonly written in the sexagesimal notation. In Napier's work of 1619, the point is written in the form now adopted,
but Briggs underlined the decimal figures and would have printed a number such as 25.379 in the form 25379 with the 379 underlined. Subsequent writers have added another line and would have written it as 25 with a vertical line 379 with the 379 being underlined. Nor was it till the beginning of the 18th century that the notation now current was generally employed. End of part 15. Recording by Paul King, pjk.scripps.mit.edu/pkj. Chapter 12, Part 1 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 12, The Mathematics of the Renaissance, 1450 to 1637. The last chapter is a digression from the chronological arrangement to which as far as possible I have throughout adhered, but I trust by references in this chapter to keep the order of events and discoveries clear. I return now to the general history of mathematics in Western Europe. Mathematicians had barely assimilated the knowledge obtained from the Arabs, including their translations of Greek writers, when the refugees who escaped from Constantinople after the fall of the Eastern Empire brought the original works and traditions of the Greek science into Italy. Thus, by the middle of the 15th century, the chief results of Greek and Arabian mathematics were accessible to European students. The invention of printing about that time rendered the dissemination of discoveries comparatively easy. It is almost a truism to remark that until printing was introduced, a writer appealed to a very limited class of readers. But we are perhaps apt to forget that when a medieval writer published a work, the results were known only to a few of his contemporaries. This had not been the case in classical times, for then and until the 4th century of our era, Alexandria was the recognized center for the reception and dissemination of new works and discoveries. In medieval Europe, on the other hand, there was no common center through which men of science could communicate with one another. And to this cause, the slow and fitful development of medieval mathematics may be partially ascribed. The introduction of printing marks the beginning of the modern world in science as in politics, for it was contemporaneous with the assimilation by the indigenous European school, which was born from scholasticism and whose history was traced in Chapter 8, of the results of the Indian and Arabian schools, whose history and influence were traced in Chapters 9 and 10, and of the Greek schools, whose history was traced in Chapters 2 to 5. The last 2 centuries of this period in our history, which may be described as the Renaissance, were distinguished by great mental activity in all branches of learning. The creation of a fresh group of universities, including those in Scotland, of a somewhat less complex type than the medieval universities above described, testified to the general desire for knowledge. The discovery of America in 1492 and the discussions that preceded the Reformation flooded Europe with new ideas which by the invention of printing were widely disseminated. But the advance in mathematics was at least as well marked as that in literature and that in politics. During the first part of this time, the attention of mathematicians was to a large extent concentrated on syncopated algebra and trigonometry. The treatment of these subjects is discussed in the first section of this chapter, but the relative importance of the mathematicians of this period is not very easy to determine. The middle years of the Renaissance were distinguished by the development of symbolic algebra. This is treated in the second section of this chapter. The close of the 16th century saw the creation of the science of dynamics. This forms a subject of the first section of chapter 13. About the same time and in the early years of the 17th century considerable attention was paid to pure geometry. This forms the subject of the second section of chapter 13. The development of syncopated algebra and trigonometry. Regiomontanus. Amongst the many distinguished writers of this time, Johann Regiomontanus was the earliest and one of the most able. He was born at Königsberg on June 6, 1436, and died at Rome on July 6, 1476. His real name was Johann Müller, but following the custom of that time, he issued his publications under a Latin pseudonym, which in his case was taken from his birthplace. To his friends, his neighbors, and tradespeople he may have been Johann Müller, but the literary and scientific world knew him as Regiomontanus, just as they knew Copernic as Copernicus and Schwarzerd as Melanchthon. It seems to me as pedantic as it is confusing to refer to an author by his actual name when he is universally recognized under another. I shall therefore in all cases as far as possible use that title only, whether Latinized or not, by which a writer is generally known. Regiomontanus studied mathematics at the University of Vienna, then one of the chief centres of mathematical studies in Europe, under Purbach, who was a professor there. His first work, done in conjunction with Purbach, consisted of an analysis of the Almagest. In this, the trigonometrical functions sine and cosine were used, and a table of natural signs were introduced. Purbach died before the book was finished, and it was finally published at Venice, but not until 1496. As soon as this was completed, Regiomontanus wrote a book on astrology, which contained some astronomical tables and a table of natural tangents. This was published in 1490. Leaving Vienna in 1462, Regiomontanus travelled for some time in Italy and Germany, and at last in 1471 settled for a few years at Nuremberg, where he established an observatory, opened a printing press, and probably lectured. 3 tracts on astronomy by him were written here. A mechanical eagle which flapped its wings and saluted the Emperor Maximilian I on his entry into the city bears witness to his mechanical ingenuity and was reckoned among the marvels of the age. Thence
Regiomontanus moved to Rome
to an invitation from Sixtus IV, who wished him to reform the calendar. He was assassinated shortly after his arrival at the age of 40.
Regiomontanus
Was among the first to take advantage of the recovery of the original texts of the Greek mathematical works in order to make himself acquainted with the methods of reasoning and the results there used. The earliest notice in modern Europe of the algebra of Diophantus is a remark of his that he had seen a copy of it at the Vatican. He was also well read in the works of the Arab mathematicians. The fruit of this study was shewn in De Trianguli, written in 1464. This is the earliest modern systematic exposition on trigonometry, plane and spherical, though the only trigonometrical functions introduced are those of the sine and cosine. It is divided into 5 books. The first 4 are given up to plane trigonometry, and in particular to determining triangles from the 3 given conditions. The 5th book is devoted to spherical trigonometry.
The work was printed in 5 volumes at Nuremberg in 1533, nearly a century after the death of Regiomontanus.
As an example of the mathematics of this time, I quote one of his propositions at length. It is required to determine a triangle when the difference of the 2 sides, the perpendicular on the base, and the difference between the segments into which the base is thus divided are given. Book 2, proposition 23. The following is the solution given by
Regiomontanus. Si talis triangulus ABG, cujus duo latera AB et AG differentia habeant nota HG, ductaque perpendiculari AD duorum casuum BD et DG differentia set EG. Hae duae differentiae sint datae et ipsa perpendicularis AD data. Digo quod omnia latera trianguli nota clagudentur. Per artem res sensus hoc problema absolvimus.
2 égale differentia laterum ut 3 differentia casium duodecim et perpendicularis decim. Prono probassi unum rem e pro aggregato laterum 4 res, ne proportio basis ad congerium laterum et un hg ad ge silicet unius ad 4. Eret ergo BD dimediere minus 6, sed AB eret duo resdemptis dimedie 3. Duco AB and C producontur 4 census et duo quadrantum demptis 6 rebus. Item BD incet faci quarte census et trigantia 6 minus 6 rebus, huic ado quadrantum de decem qui est centum. Colliguntur quartae census et centum trigintia 6 minus 6 rebus, ae qualis videlicet 4 censibus et duo quartae demptis 6 rebus. Restaurando itaque defectus et offerendo utrobique equalia. Quimad modum ars ipse percipit, habimus census aliquat aliquales numero. Unde cognitio repetibit, et inda tria latera trianguli mores suo inutescet. To explain the language of the proof, I should add that Regiomontanus always called the unknown quantity res, and its square census or zensus. But though he uses these technical terms, he writes the words in full. He commences by saying that he will solve the problem by means of a quadratic equation per artum re et census, and that he will suppose that the difference of the sides of the triangle to be 3, the difference of the segments of the base to be 12, and the altitude of the triangle to be 10. He then takes for his unknown quantity unum rem or x the basis of the triangle. Therefore the sum of the sides will be 4 times x. Therefore BD will be equal to half x minus 6 dimedire minus 6, and AB will be equal to 2x minus 3 halves duo res demptis dimedie 3. Hence AB squared, AB in C, will be 4x squared plus 2 1/4 minus 6x. Quarto census et duo et quarte demptus 6 rebus, and BD squared will be 1/4 x squared plus 36 minus 6x. To BD squared he adds AD squared, quadrantum de decem, which is 100, and states that the sum of these two are equal to AB squared. This, he says, will give the value of x squared, census, whence a knowledge of x, cognitio rei, can be obtained, and the triangle determined. To express this in the language of modern algebra, we have AG squared minus DG squared equals AB squared minus DB squared. Therefore AG squared minus AB squared equals DG squared minus DB squared. But by the given numerical conditions, AG minus AB equals 3 equals 1/4 of the quantity DG minus DB. Therefore AG plus AB equals 4 multiplied by the quantity DG plus DB, which equals 4x. Therefore AB equals 2x minus 3 halves, and BD equals half x minus 6. Hence the quantity 2x minus 3 halves all squared equals the quantity half x minus 6 all squared plus 100, from which x can be found and all the elements of the triangle determined. It is worth noticing that Regiomontanus merely aimed at giving a general method, and the numbers are not chosen with any special reference to the particular problem. Thus in his diagram he does not attempt to make GE anything like 4 times as long as GH, and since x is ultimately found to be equal to 1/3 of the square root of 321,
the point D really falls outside the base. The order of the letters ABG used to denote the triangle is of course derived from the Greek alphabet. Some of the solutions which he gives are unnecessarily complicated, but it must be remembered that algebra and trigonometry were still only in the rhetorical stage of development, and when every step of the argument is expressed in words at full length, it is by no means easy to realize all that is contained in a formula. It will be observed from the above example that Regiomontanus did not hesitate to apply algebra to the solution of geometrical problems. Another illustration of this is to be found in his discussions of a question which appears in Brahmagupta's Siddhanta. The problem was to construct a quadrilateral having its sides of given lengths which should be inscribable in a circle. The solution given by Regiomontanus was effected by means of algebra and trigonometry. This was published by C.G. von Meur in Nuremberg in 1786. The Algorithmus Demonstratus of Jordanus, which was first printed in 1534, was until recently universally attributed to Regiomontanus. This work, which is concerned with algebra and arithmetic, was known to Regiomontanus, and it is possible that the text which has come down to us contains additional matter contributed by him. Regiomontanus was the most prominent mathematician of his generation, and I have dealt with his works in some detail as typical of the most advanced mathematics of the time. Of his contemporaries I shall do little more than mention the names of a few of those who are best known. None were quite of the first rank, and I should sacrifice the proportion of the parts of the subject were I to devote much space to them. Purbach. I may begin by mentioning George Purbach, first the tutor, then the friend of Regiomontanus, born near Linz on May 14, 1423, and died at Vienna on April 8, 1461, who wrote a work on planetary motions which was published in 1460, an arithmetic published in 1511, a table of eclipses published in 1514, and a table of natural signs published in 1541. Cusa. Next I may mention Nicholas von Cusa, who was born in 1401 and died in 1464. Although the son of a poor fisherman and without influence, he rose rapidly in the church, and in spite of being a reformer before the Reformation, became a cardinal. His mathematical writings deal with the reform of the calendar and the quadrature of the circle. He argued in favour of the diurnal rotation of the earth. Chouquet. I may also here notice a small treatise on arithmetic known as Le Tripartite by Nicolas Chouquet, a bachelor of medicine in the University of Paris, which was written in 1484. This work indicates that the extent of mathematics then taught was somewhat greater than was generally believed a few years ago. It contains the earliest known use of the radical sign with indices to mark the root taken, 2 for a square root, 3 for a cube root, and so on, and also a definite statement on the rules of signs. The words plus and minus are denoted by the contraction P with a bar over it and M with a bar over it. The work is in French. Introduction of the signs plus and minus. In England and Germany, algorists were less fettered by precedent and tradition than in Italy, and introduced some improvements in notation which were hardly likely to occur to an Italian. Of these the most prominent were the introduction of the current symbols for addition, subtraction, and equality. The earliest instances of the use of the signs plus and minus, of which we have any knowledge, occur in the 15th century. Johannes Widman of Eger, born about 1460, matriculated at Leipzig in 1480, and probably by profession a physician, wrote Mercantile Arithmetic, published at Leipzig in 1489. In this book these signs are used, not however as symbols of operation, but apparently merely as marks signifying excess or deficiency. The corresponding use of the word surplus or overplus is still retained in commerce. It is noticeable that the signs generally occur only in practical mercantile questions. Hence it has been conjectured that they were originally warehouse marks. Some kinds of goods were sold in a sort of wooden chest called a ladle, which when full was apparently expected to weigh roughly either 3 or 4 centners. If one of these cases were a little higher, say 5 pounds, than 4 centners, Widman describes it as 4c minus 5 pounds. If it were 5 pounds heavier than the normal weight, it is described as 4c plus 5 pounds, and there are some slight reasons for thinking that these marks were chalked on the chests as they came into the warehouses. The symbols are used as if they would be familiar to his readers. It will be observed that the vertical line in the symbol for excess printed above is somewhat shorter than the horizontal line. This is also the case with Stifel and most of the early writers who used the symbol. Some presses continued to print it in its earliest form till the end of the 17th century. Xylander, on the other hand, in 1575 has the vertical bar much longer than the horizontal line, and the symbol is something like plus. We infer that the more usual case was for a chest to weigh a little less than its reputed weight, and as the sign minus placed between the two numbers was a common symbol to signify some connection between them, that seems to have been taken as the standard case, while the vertical bar was originally a small mark superadded on the sign minus to distinguish the two symbols. I am far from saying that this account of the origin of our symbols plus and minus is established beyond doubt, but it is the most plausible that has yet been advanced. Another suggested derivation is that plus is a contraction of p, the initial letter in the old German of plus, while minus is the limiting form of m for minus written rapidly. De Morgan proposed yet another derivation. The Hindus sometimes used a dot to indicate subtraction, and this dot might be thought to have been elongated into a bar, and thus give the sign for minus, while the origin of the sign for plus was derived from it by a superadded bar as explained above. But I take it that at a later time he abandoned this theory for what has been called the warehouse explanation. Another conjecture, ingenious but unsupported by any evidence, is that the symbol for plus is derived from the Latin abbreviation ampersand for et, while that for minus is obtained from the bar from which it is often written over the contracted form of a word to signify that certain letters have been left out. I should perhaps here add that till the close of the 16th century the sign plus connecting two quantities like a and b was also used in the sense that if a were taken as the answer to some question, one of the given conditions would be too little by b. This was a relation which constantly occurred in the solutions of questions by the rule of false assumption. Lastly, I would repeat again that these signs in Widman are only abbreviations and not symbols of operation. He attached little or no importance to them, and no doubt would have been amazed if he had been told that their introduction was preparing the way for a revolution of the processes used in algebra. The Algorithmus of Jordanus was not published until 1534. Widman's work was hardly known outside Germany, and it is to Pacioli that we owe the introduction into general use of syncopated algebra, that is, the use of abbreviations for certain of the more common algebraical quantities and operations, but where in using them the rules of syntax are observed. Pacioli. Lucas Pacioli, sometimes known as Lucas di Burgo, and sometimes but more rarely as Lucas Paciolus, was born in Burgo in Tuscany about the middle of the 15th century. We know little of his life except that he was a Franciscan friar and that he lectured in mathematics at Rome, Pisa, Venice, and Milan, and that at the last named city he was the first occupant of a chair of mathematics founded by Sforza. He died at Florence about the year 1510.
His chief work was printed at Venice in 1494 and is termed Summa di Arithmetica Geometrica Proporzioni e Proporzionalità. It consists of two parts, first dealing with arithmetic and algebra, the second with geometry. This was the earliest printed book on arithmetic and algebra. It is mainly based on the writings of Leonardo of Pisa, and its importance in the history of mathematics is largely due to its wide circulation. In arithmetic, Pacioli gives rules for the four simple processes and a method for extracting square roots. He deals pretty fully with all questions connected with mercantile arithmetic, in which he works out numerous examples, and in particular discusses at great length bills of exchange and the theory of bookkeeping by double entry. This part was the first systematic exposition of algoristic arithmetic and has already been alluded to in chapter 11. It and similar work by Tartaglia are the two standard authorities on the subject. Most of the problems are solved by the method of false assumption, but there are several numerical mistakes. The following example will serve as an illustration of the kind of arithmetical problems discussed. I buy for 1,440 ducats at Venice 2,400 sugar loaves, whose net weight is 7,200 lire. I pay as a fee to the agent 2%, to the weighers and porters on the whole 2 ducats. I afterwards spend in boxes, cords, canvas, and in fees to the ordinary packers in the whole 8 ducats. For the tax or octroi duty on the first amount 1 ducat per cent. Afterwards for duty and tax at the office of exports 3 ducats per cent. For writing directions on the boxes and booking their passage 1 ducat. For the bark on Rimini 13 ducats. In compliments to the captains and in drink for the crews of armed barks on several occasions 2 ducats. In expenses for provisions for myself and servant for 1 month 6 ducats. For expenses for several short journeys overland here and there, for barbers, for washing of linen, and of boots for myself and servant 1 ducat. Upon my arrival in Rimini, I pay to the captain of the port for port dues in the money of that city 3 lire. For porters, disembarkation on land, and carriage to the magazine 5 lire. As tax upon entrance 4 soldi a load, which are in number 32, such being the custom. For booth at the fair 4 soldi per load. I further find that the measures used at the fair are different to those used at Venice, and that 140 lire of weight are there equivalent to 100 at Venice, and that 4 lire of their silver coinage are equal to a ducat of gold. I ask therefore at how much must I sell 100 lire in Rimini in order that I may gain 10% upon my whole adventure, and what is the sum which I must receive in Venetian money. In the algebra he finds expressions for the sum of the squares and the sum of the cubes of the first n natural numbers. The larger part of this book is taken up with simple and quadratic equations and problems on numbers which lead to such equations. He mentions the Arabic classification of cubic equations, but adds that their solution appears to be as impossible as the quadrature of the circle. The following is the rule he gives for solving a quadratic equation of the form x squared plus x equals a. It is rhetorical and not syncopated, and will serve to illustrate the inconvenience of that method. Si res e census numero coi quantur, a rebus dimidius sumpto censum producere debus. Addereque numero cudius a redice totiens tol semis rerum, census latusque redibit. He confines his attention to the positive roots of equations. Though much of the matter described above is taken from Leonardo's Liber Abaci, yet the notation in which it is expressed is superior to that of Leonardo. Pacioli follows the Arabs in calling the unknown quantity the thing, in Italian cosa.
Hence algebra was sometimes known as the Cossack art, or in Latin res, and sometimes denotes it by co or r or rj. He calls the square of it census or zensus, and sometimes denotes it by che ce or z. Similarly, the cube of it, or cuba, is sometimes represented by q cu or c. The fourth power, or censo di censo, is written either at length or as che di che ce space di space ce or as cece. It may be noticed that all his equations are numerical, so that he did not rise to the conception of representing known quantities by letters as Jordanus has done and as is the case in modern algebra. But M. Libri gives two instances in which in a proportion he represents a number by a letter. He indicates addition and equality by the initial letters of the word plus and equalis, but he generally evades the introduction of a symbol for minus by writing his quantities on that side of the equation which makes them positive, though in a few places he denotes it by m with a bar over it for minus, or by de for demptus. This is a commencement of syncopated algebra. There is nothing striking in the results he arrives at in the second or geometrical part of the work, nor in two other tracts on geometry which he wrote, in which were printed at Venice in 1508 and 1509. It may be noticed, however, that like Regiomontanus he applies algebra to aid him in investigating the geometrical properties of figures. The following is a problem which will illustrate the kind of geometrical questions he attacked. The radius of the inscribed circle of a triangle is 4 inches, and the segments into which one side is divided by the point of contact are 6 inches and 8 inches respectively. Determine the other sides. To solve this, it is sufficient to remark that RS equals the triangle, which equals the square root of s times the quantity s minus a times the quantity s minus b times the quantity s minus c, which gives 4s equals the square root of s times the quantity s minus 14 times 6 times 8, all under the square root. Hence s equals 21. Therefore the required sides are 21 minus 6 and 21 minus 8, that is 15 and 13. But Pacioli makes no use of these formulae with which he was acquainted, but gives an elaborate geometrical construction and then uses algebra to find the lengths of the various segments of the lines he wants. The work is too long for me to reproduce here, but the following analysis of it will afford sufficient materials for its reproduction. Let ABC be the triangle, DEF be the points of contact with the sides, and O the center of the given circle. Let H be the point of intersection of OB and DF, and K that of OC and DE. Let L and M be the feet of the perpendiculars drawn from E and F on BC. Draw EP parallel to AB and cutting BC in P. Then Pacioli determines in succession the magnitudes of the following lines: OB, OC, FD, FH, ED, and EK. He then forms a quadratic equation from the solution of which he obtains the values MB and MD. Similarly, he finds the values LC and LD. He now finds in succession the values of EL, FM, EP, and LP, and then by similar triangles obtains the value of AB, which is 13. This proof was, even 60 years later, quoted by Cardan as incomparably simple and excellent, and the very crown of mathematics. I cite it as an illustration of the involved and inelegant methods then current. The problems enunciated are very similar to those in the De Triangulis of Regiomontanus. Leonardo da Vinci. The fame of Leonardo da Vinci as an artist has overshadowed his claim to consideration as mathematician,
but he may be said to have prepared the way for a more accurate conception of mechanics and physics, while his reputation and influence drew some attention to the subject. He was an intimate friend of Pacioli. Leonardo was the illegitimate son of a lawyer of Vinci in Tuscany, was born in 1452, and died in France in 1519 while on a visit to Francis I. Several manuscripts by him were seized by the French revolutionary armies at the end of the last century, and Venturi, at the request of the Institute, reported on those concerned with physical or mathematical subjects. Leaving out of account Leonardo's numerous and important artistic works, his mathematical writings are concerned chiefly with mechanics, hydraulics, and optics, his conclusions being usually based on experiments. His treatment of hydraulics and optics involves but little mathematics. The mechanics contain numerous and serious errors. The best portions are those dealing with the equilibrium of a lever under any forces, the laws of friction, the stability of a body as affected by the position of its center of gravity, the strength of beams, and the orbit of a particle under a central force. He also treated a few easy problems by virtual moments. A knowledge of the triangle of forces is occasionally attributed to him, but I think it is most probable that his views on the subject were somewhat indefinite. Generally, one may say that all his mathematical work is unfinished and consists largely of suggestions which he had not the patience to verify or discuss in detail. Dürer. Albrecht Dürer was another artist of the same time who was also known as a mathematician. He was born at Nuremberg in May 21st, 1471, and died there on April 6, 1528. His chief mathematical work was issued in 1525 and contains a discussion of perspective and some geometry and certain graphical solutions. Latin translations of it were issued in 1532, 1555, and 1605. Copernicus. An account of Nicholas Copernicus, born at Thorn on February 19, 1473, and died at Frauenburg on May 7, 1543, and his conjecture that the earth and planets all revolved around the sun belong to astronomy rather than to mathematics. I may however add that Copernicus wrote a short textbook on trigonometry published at Wittenberg in 1542, which is clear though it contains nothing new. It is evident from this and his astronomy that he was well read in the literature of mathematics and was himself a mathematician of considerable power. I describe his statement as to the motion of the earth as a conjecture because he advocated it only on the ground that it gave a simple explanation of natural phenomenon. Galileo in 1632 was the first to try to supply anything like a proof of this hypothesis. By the beginning of the 16th century, the printing press began to be active, and many of the works of the earlier mathematicians became now for the first time accessible to all students. This stimulated inquiry, and before the middle of the century numerous works were issued, which, though they did not include any great discoveries, introduced a variety of small improvements, all tending to make algebra more analytical. Record. The sign now used to denote equality was introduced by Robert Record. Record was born at Tenby in Pembrokeshire about 1510 and died at London in 1558. He entered at Oxford and obtained a fellowship at All Souls College in 1531. Thence he migrated to Cambridge, where he took a degree in medicine in 1545. He then returned to Oxford and then lectured there, but finally settled in London and became physician to Edward VI and to Mary. His prosperity must have been short-lived, for at the time of his death he was confined to the King's Bench prison for debt. In 1540 he published an arithmetic termed the Ground of Arts, in which he employed the signs plus for plus and minus for minus, plus sign which betokeneth too much, as this line minus plain without a cross line betokeneth too little. And there are faint traces of his having used these signs as symbols of operation and not as mere abbreviations. In this book the equality of two ratios is indicated by two equal and parallel lines whose opposite ends are joined diagonally, for example a greater than or equal to sign. A few years later, in 1557, he wrote an algebra under the title Whetstone of Wit. This is interesting as it contains the earliest introduction of the sign equals for equality, and he says he selected that particular symbol because then two parallel straight lines, no two things can be more equal. M. Charles Henry has however pointed out that this sign is a not uncommon abbreviation for the word est in medieval manuscripts, and this would seem to indicate a more probable origin. In this work records shewed how the square root of an algebraical expression could be extracted. He also wrote on astronomy. These works give a clear view of the knowledge of the time. Rudolf Riess. About the same time in Germany, Rudolf and Riess took up the subjects of algebra and arithmetic. Their investigations formed the basis of Stieffel's well-known work. Christoph Rudolf published his algebra in 1525. It is entitled Die Cross, and it is founded on the writings of Pacioli and perhaps of Jordanus. Rudolf introduced the sign of surd for the square root, the symbol being the corruption of the initial letter of the word radix, and similarly 3 surds denoted a cube root and 2 surds denoted a fourth root. Adam Riess was born near Bamberg, Bavaria in 1489 of humble parentage, and after working for some years as a miner set up a school. He died at Annaberg on March 30th, 1559. He wrote a treatise on practical geometry, but his most important book was his well-known Arithmetic, which may be described as algebraical, issued in 1536 and founded on Pacioli's work. Riess used the symbols plus and minus. End of section 16. Recording by Paul King, pjk.scripts.mit.edu/pkj. Chapter 12, Part 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 12, Part 2. The Mathematics of the Renaissance, 1450 to 1637. Part 2. Stiefel. The methods used by Rudolf and Riess and their results were brought into general notice through Stiefel's work, which had wide circulation in Germany. Michael Stiefel, sometimes known by the Latin name of Stiefelius, was born at Essling in 1486 and died at Jena in April 19th, 1567. He was originally an Augustine monk, but he accepted the doctrines of Luther, of whom he was a personal friend. He tells us in his algebra that his conversion was finally determined by noticing that Pope Leo X was the beast mentioned in the Revelation. To shew this, it was only necessary to add up the numbers represented by the letters in Leo Decimus. The M had to be rejected since it clearly stood for mysterium, and the result amounts to exactly 10 less than 666, 666, thus distinctly implying that it was Leo the 10th. Luther accepted his conversion, but frankly told him that he had better clear his mind of any nonsense about the number of the beast. Unluckily for himself, Stifel did not act on this advice. Believing that he had discovered the true way of interpreting the biblical prophecies, he announced that the world would come to an end on October 3rd, 1533. The peasants of Holsdorf, of which place he was pastor, knowing of the scientific reputation, accepted his assurance on this point. Some gave themselves up to religious exercises, others wasted their goods in dissipation, but all abandoned their work. When the day foretold had passed, many of the peasants found themselves ruined. Furious at having been deceived, they seized the unfortunate prophet, and he was lucky in finding a refuge in the prison at Wittenberg, from which he was after some time released by the personal intercession of Luther. Stifel wrote a small treatise on algebra, but his chief mathematical work is his Arithmetica Integra, published at Nuremberg in 1544, with a preface by Melanchthon. The first two books of the Arithmetica Integra deal with surds and incommensurables, and are Euclidean in form. The third book is on algebra, and is noticeable for having called general attention to the German practice of using the signs plus and minus to denote addition and subtraction. There are faint traces of these signs being occasionally employed by Stifel as symbols of operation and not only as abbreviations. This application of them was apparently new. He not only employed the usual abbreviation for the Italian words which represent the unknown quantity and its powers, but in at least one case where there was several unknown quantities he represented them respectively by the letters A, B, C, and so on, thus reintroducing the general algebraic notation which had fallen into disuse since the time of Jordanus. It used to be said that Stifel was the real inventor of logarithms, but it is now certain that this opinion was due to a misapprehension of a passage in which he compares the geometrical and arithmetical progressions. Tartaglia. Niccolo Fontana, generally known as Nicholas Tartaglia, that is, Nicholas the Stammerer, was born at Brescia in 1500 and died in Venice in December 14, 1557. After the capture of the town by the French in 1512, most of the inhabitants took refuge in the cathedral, and were then massacred by the soldiers. His father, who was a postal messenger at Brescia, was amongst the killed. The boy himself had his skull split through in 3 places, while both his jaws and his palate were cut open. He was left for dead, but his mother got into the cathedral, and finding him still alive managed to carry him off. Deprived of all resources, she recollected that dogs when wounded always lick the injured place, and to that remedy he attributed his ultimate recovery, but the injury to his palate produced an impediment in his speech, from which he received his nickname. His mother managed to get sufficient money to pay for his attendance at school for 15 days, and he took advantage of it to steal a copybook, from which he subsequently taught himself how to read and write. But so poor were they that he tells us that he could not afford to buy paper, and was thus obliged to make use of the tombstones as slates on which to work his exercises. He commenced his public life by lecturing at Verona, but he was appointed at some time before 1535 to a chair of mathematics at Venice, where he was living when he became famous, through his acceptance of a challenge from a certain Antonio de Fiori or Florido. Fiori had learnt from his master, one Scipione Ferreo, who died at Bologna in 1526, an empirical solution of a cubic equation of the form x cubed plus qx equals r. This solution was previously unknown in Europe, and it is probable that Ferreo had found the result in an Arab work. Tartaglia, in answer to a request from Colla in 1530, stated that he could effect a solution of a numerical equation of the form x cubed plus px squared equals r. Fiori, believing that Tartaglia was an impostor, challenged him to a contest. According to this challenge, each of them was to deposit a certain stake with the notary, and whoever could solve the most problems out of a collection of 30 propounded by the other was to get the stakes, 30 days being allowed for the solution of the questions proposed. Tartaglia was aware that his adversary was acquainted with the solution of a cubic equation of some particular form, and suspecting that the questions proposed to him would all depend on the solution of such a cubic equation, set himself the problem to find a general solution, and certainly discovered how to obtain a solution of some if not all cubic equations. His solution is believed to have depended on a geometrical construction, but led to a formula which is often but unjustly described as Cardan's. When the contest took place, all the questions proposed to Tartaglia were, as he had suspected, reducible to the solution of a cubic equation, and he succeeded within 2 hours in bringing them to particular cases of the equation x cubed plus qx equals r, of which he knew the solution. His opponent failed to solve any of the problems proposed to him, which as a matter of fact were all reducible to numerical equations of the form x cubed plus px squared equals r. Tartaglia was therefore the conqueror. He subsequently composed some verses commemorative of his victory. The chief works of Tartaglia are as follows. His Nova Scienza, published in 1537. In this he investigated the fall of bodies under gravity, and he determined the range of a projectile, stating that it was a maximum when the angle of projection was 45 degrees. But this seems to have been a lucky guess. 2. An arithmetic, published in 2 parts in 1556. 3. A treatise on numbers, published in 4 parts in 1560. And sometimes treated as a continuation of the arithmetic. In this he shewed how the coefficients of x in the expansion of 1 plus x to the power n could be calculated from those in the expansion of 1 plus x quantity to the power of n minus 1 for the cases where n is equal to 2, 3, 4, 5, or 6. It is possible that he also wrote a treatise on algebra and the solution of cubic equations, but if so, no copy is now extant. The other works were collected into a single edition and republished at Venice in 1606. The treatise on arithmetic and numbers is one of the chief authorities for our knowledge of the early Italian algorism. It is verbose, but gives a clear account of the different arithmetical methods then in use, and he has numerous historical notes which, as far as we can judge, are reliable, and are the authorities for many of the statements in the last chapter. It contains an immense number of questions on every kind of problem which would be likely to occur in mercantile arithmetic, and there are several attempts to frame algebraical formulae suitable for particular problems. These problems give incidentally a good deal of information as to the ordinary life and commercial customs of the time. Thus we find that the interest demanded on first-class security in Venice ranged from 5 to 12% a year, while the interest on commercial transactions ranged from 20% a year upwards. Tartaglia illustrates the evil effects of the law forbidding usury by the manner in which it was evaded in farming. Farmers who were in debt were forced by their creditors to sell all their crops immediately after the harvest, the market being thus glutted. The price obtained was very low, and the moneylenders purchased the corn in the open market at an extremely cheap rate. The farmers then had to borrow their seed corn on condition that they replaced an equal quantity, or paid the then price of it, in the month of May, when corn was dearest. Again, Tartaglia, who had been asked by the magistrates at Verona to frame for them a sliding scale by which the price of bread would be fixed by that of corn, enters into a discussion on the principles which it was then supposed should regulate it. In another place he gives the rules at that time current for preparing medicines. Pacioli had given in his arithmetic some problems of an amusing character, and Tartaglia imitated him by inserting a large collection of mathematical puzzles. He half apologizes for introducing them by saying that it was not uncommon at dessert to propose arithmetical questions to the company by way of amusement, and he therefore adds some suitable problems. He gives several questions on how to guess a number thought of by one of the company, or the relationships caused by the marriage of relatives, or difficulties arising from inconsistent bequests. Other puzzles are such as the following. There are three men, young, handsome, and gallant, who have three beautiful ladies for wives. All are jealous, as well as the husbands of the wives, as the wives of the husbands. They find on the bank of a river over which they have to pass a small boat which can hold no more than 2 persons. How can they pass so as to give rise to no jealousy? A ship carrying as passengers 15 Turks and 15 Christians encounters a storm, and the pilot declares that in order to save the ship and crew, 1/2 of the passengers must be thrown into the sea. To choose the victims, the passengers are placed in a circle, and it is agreed that every 9th man shall be cast overboard, reckoning from a certain point. In what manner must they be arranged so that the lot may fall exclusively upon the Turks? 3 men robbed a gentleman of a vase containing 24 ounces of balsam. Whilst running away they met in a wood with a glass seller, of whom in a great hurry they purchased 3 vessels. On reaching a place of safety they wish to divide the booty, but they find that their vessels contain 5, 11, and 13 ounces respectively. How can they divide the balsam into equal portions? These problems, some of which are of Oriental origin, form the basis of the collections of mathematical recreations by Bachet de Meziriac, Ozanam, and Montucla. Cardan. The life of Tartaglia was embittered by a quarrel with his contemporary Cardan, who, having under a pledge of secrecy obtained Tartaglia's solution of a cubic equation, and published it. Girolamo Cardan was born at Pavia on September 24, 1501, and died at Rome on September 21, 1576. His career is an account of the most extraordinary and inconsistent acts. A gambler, if not a murderer, he was also the ardent student of science, solving problems which had long baffled all investigation. At one time of his life he was devoted to intrigues which were a scandal even in the 16th century. At another he did nothing but rave on astrology, and yet at another he declared that philosophy was the only subject worthy of men's attention. His was the genius that was closely allied to madness. He was the illegitimate son of a lawyer of Milan, and was educated at the universities of Pavia and Padua. After taking his degree he commenced the life of a doctor, and practised his profession at Sacco and Milan from 1524 to 1550. It was during this period that he studied mathematics and published his chief works. After spending a year or so in France, Scotland, and England, he returned to Milan as a professor of science, and shortly afterwards was elected to a chair at Pavia. Here he divided his time between debauchery, astrology, and mechanics. His 2 sons were as wicked and passionate as himself. The elder was in 1560 executed for poisoning his wife, and about the same time Cardan in a fit of rage cut off the ears of the younger, who had committed some offence. For this scandalous outrage he suffered no punishment, as the Pope Gregory XIII took him under his protection. In 1562 Cardan moved to Bologna, but the scandals connected with his name were so great that the university took steps to prevent his lecturing, and only gave way under pressure from Rome. In 1570 he was imprisoned for heresy on account of his having published the horoscope of Christ, and when released he found himself so generally detested that he determined to resign his chair. At any rate, he left Bologna in 1571, and shortly afterwards moved to Rome. Cardan was the most distinguished astrologer of his time, and when he settled at Rome he received a pension in order to secure his services as astrologer to the papal court. This proved fatal to him, for, having foretold that he should die on a particular day, he felt obliged to commit suicide in order to keep up his reputation, or so at least the story runs. The chief mathematical work of Cardan is the Ars Magna, published at Nuremberg in 1545. Cardan was much interested in the contest between Tartaglia and Fiori, and as he had already begun writing this book he asked Tartaglia to communicate his method of solving a cubic equation. Tartaglia refused, whereupon Cardan abused him in the most violent terms, but shortly afterwards wrote, saying that a certain Italian nobleman had heard of Tartaglia's fame and was most anxious to meet him, and begged him to come to Milan at once. Tartaglia came, and though he found no nobleman awaiting him at the end of his journey, he yielded to Cardan's importunity and gave him the rule he wanted. Cardan on his side, taking a solemn oath that he would never reveal it, and would not even commit it to writing in such a way that after his death anyone could understand it. The rule is given in some doggerel verses which are still extant. Cardan asserts that he was given merely the result, and that he obtained the proof himself, but this is doubtful. He seems to have at once taught the method, and one of his pupils, Ferrari, reduced the equation of the fourth degree to a cubic, and so solved it. When the Ars Magna was published in 1545, the breach of faith was made manifest. Tartaglia was not unnaturally very angry, and after acrimonious controversy he sent a challenge to Cardan to take part in a mathematical duel. The preliminaries were settled, and the place of meeting was to be a certain church in Milan, but when the day arrived Cardan failed to appear, and sent Ferrari in his stead. Both sides claimed the victory, though I gather that Tartaglia was the more successful. At any rate his opponents broke up the meeting, and he was fortunate in escaping with his life. Not only did Cardan succeed in his fraud, but modern writers generally attribute the solution to him, so that Tartaglia has not even that posthumous reputation which is at least his due. The Ars Magna is a great advance on any algebra previously published. Hitherto algebraists had confined their attention to those roots of equations which were positive. Cardan discussed negative and even imaginary roots, and proved that the latter would always occur in pairs, though he declined to commit himself to any explanation as to the meaning of these sophistic quantities, which he said were ingenious though useless. Most of his analysis of cubic equations seemed to have been original. He shewed that if the three roots were real, Tartaglia's solution gave them in a form which involved imaginary quantities. Except for the somewhat similar researches of Bombelli a few years later, see below, page 231, that the theory of imaginary quantities received little further attention from mathematicians until Euler took the matter up after the lapse of nearly 2 centuries. Gauss first put the subject on a systematic and scientific basis, introduced the notation of complex variables, and used the symbol I to denote the square root of -1. The modern theory is chiefly based on his researches. Cardan found the relations connecting the roots with the coefficients of an equation. He was also aware of the principle that underlies Descartes' rule of signs. But as he followed the then general custom of writing his equations as the equality of two expressions, in each of which all the terms were positive, he was unable to express the rule concisely. He gave a method of approximating to the root of a numerical equation founded on the fact that if a function has opposite signs when two numbers are substituted on it, the equation obtained by equating the functions to 0 will have a root between those two numbers. Cardan's solution of a quadratic equation is geometrical and substantially the same as that given by Al-Khwarizmi. His solution of a cubic equation is also geometrical and may be illustrated by the following case, which he gives in chapter 11. To solve the equation x squared plus 6x equals 20, or any equation of the form x squared plus qx equals r, take two cubes such that the rectangle under their respective edges is 2 or 1/3 q, and the difference of their volumes is 20 or r. the x will be equal to the difference between the edges and the cubes. To verify this, he first gives a geometrical lemma to shew that if from a line AC a portion CB be cut off, then the cube on AB will be less than the difference between the cubes on AC and BC by 3 times the right parallelepiped whose edges are respectively equal to AC, BC, and AB. This statement is equivalent to the algebraical identity a minus b quantity cubed equals a cubed minus b cubed minus 3ab multiplied by the quantity a minus b. And the fact that x satisfies the equation is then obvious. To obtain the lengths of the edges of the two cubes, he has only to solve a quadratic equation for which the geometrical solution previously given sufficed. Like all previous mathematicians, he gives separate proofs of his rule for the different forms of equations which can fall under it. Thus he proves the rule independently for equations of the form x cubed plus px equals q, x cubed equals px plus q, x cubed plus px plus q equals 0, and x cubed plus q equals px. It will be noticed that with geometrical proofs this was almost a necessity, but he did not suspect that the resulting formulae were general. The equations he considers are numerical, but in some of his analysis he uses literal coefficients. Shortly after Cardan came a number of mathematicians who did good work in developing the subject, who are hardly of sufficient importance to require a detailed mention here. Of these, the most celebrated are perhaps Ferrari and Rheticus. Ferrari. Ludovico Ferraro, usually known as Ferrari, whose name I have already mentioned in connection with the solution of a biquadratic equation, was born at Bologna on February 2, 1522, and died on October 5, 1565. His parents were poor, and he had taken into Cardan's service as an errand boy, but was allowed to attend his master's lectures and subsequently became the most celebrated pupil. He is described as a neat, rosy little fellow, with a bland voice, a cheerful face, and an agreeable short nose, fond of pleasure, of great natural powers, but with the temper of a fiend. His manners and numerous accomplishments procured him a place in the service of the Cardinal Ferrando Gonzaga, where he managed to make a fortune. His dissipations told on his health, and he retired in 1565 to Bologna, where he began to lecture on mathematics. He was poisoned the same year either by his sister, who seems to have been the only person for whom he had any affection, or by her paramour. Such work as he produced is incorporated in Cardan's Ars Magna or Bombelli's Algebra, but nothing can be definitely assigned to him except the solution of a biquadratic equation. Colla had proposed the solution of the equation x to the fourth plus 6x squared plus 36 equals 60x as a challenge to mathematicians. This particular equation had probably been found in some Arabic work. Nothing is known about the history of this problem except that Ferrari succeeded where Tartaglia and Cardan had failed. Rheticus. Georg Joachim Rheticus, born at Feldkirch in February 15, 1514, and died at Kaschau on December 4, 1576, was professor at Wittenberg and subsequently studied under Copernicus, whose works were produced under the direction of Rheticus. Rheticus constructed the various trigonometrical tables, some of which were published by his pupil Otho in 1596. These were subsequently completed and extended by Vieta and Pitiscus and are the basis of those still in use. Rheticus also found the values of sine of 2 theta and sine of 3 theta in terms of sine theta and cosine theta. I add here the names of some other celebrated mathematicians of about the same time, though their works are now of little value to any save antiquarians. Franciscus Maurolicus, born at Messina of Greek parents in 1494 and died in 1575, translated numerous Latin and Greek mathematical works, and discussed the conics regarded as sections of a cone. His works were published at Venice in 1575. Jean Borel, born in 1492 and died at Grenoble in 1572, wrote an algebra founded on that of Stifel, and a history of the quadrature of the circle. His works were published at Lyons in 1559. Wilhelm Xylander, born at Augsburg on December 26, 1532, and died on February 10, 1576 at Heidelberg, where since 1558 he had been a professor, brought out an edition of the works of Psellus in 1556, an edition of Euclid's Elements in 1562, an edition of the Arithmetic of Diophantus in 1575, and some of the minor works which were collected and published in 1577. Federigo Commendino, born at Urbino in 1509 and died there on September 3, 1575, published a translation of the works of Archimedes in 1558, selections from Apollonius and Pappus in 1566, Euclid's Elements in 1572, and selections from Aristarchus, Ptolemy, Hero, and Pappus in 1574, all being accompanied by commentaries. Jacques Peltier, born at Le Mans on July 25, 1517 and died at Paris in July 1582, wrote several textbooks on algebra and geometry. Most of the results of Stifel and Cardan are included in the former. Adrian Romanos, born at Louvain on September 29, 1561 and died on May 4, 1625, professor of mathematics and medicine at the University of Louvain, was the first to prove the usual formula for the sine of a plus b. And lastly, Bartholomeus Pitiscus, born on August 24, 1561 and died at Heidelberg, where he was professor of mathematics on July 2, 1613, published his Trigonometry in 1599. This contains the expression for the sine of a plus b and the sine of a minus b, and also the cosine of a plus b and the cosine of a minus b in terms of the trigonometrical ratios of a and b. About this time also several books were produced which, if they did not extend the boundaries of the subject, they systematized it. In particular I may mention those of Ramus and Bombelli. Ramus. Peter Ramus was born at Cuth in Picardy in 1515 and was killed at Paris in the massacre of St. Bartholomew on August 24, 1572. He was educated at the University of Paris, and on taking his degree he astonished and charmed the university with the brilliant declamation he delivered on the thesis that everything Aristotle had taught was false. He lectured, for it will be remembered that in the early days there were no professors, first at Le Mans and afterwards at Paris, and at the latter he founded the first chair of mathematics. Besides some works on philosophy, he wrote treatises on arithmetic, algebra, geometry, founded on Euclid, astronomy, founded on the works of Copernicus, and physics, which were long regarded on the continent as the standard textbooks on these subjects. They are collected in an edition of his works published at Bâle in 1569. Bombelli. Closely following the publication of Cardan's great work, Raffaello Bombelli published in 1572 an algebra which is a systematic exposition of what was then known on the subject. In the preface he alludes to Diophantus, who, in spite of the notice of Regiomontanus, was still unknown in Europe, and traces the history of the subject. He discusses radicals, real and imaginary. He treats the theory of equations and shews that in the irreducible case of a cubic equation the roots are all real, and he remarks that the problem to trisect a given angle is the same as that of the solution of the cubic equation. Finally, he gave a large collection of problems. Bombelli is chiefly distinguished in connection with the improvement of the notation of algebra which he introduced. The symbols then ordinarily used for the unknown quantity and its powers were letters which stood for the abbreviations of these words. Those most frequently adopted were R or Rj for radix or res x, Z or C for zensus or census x squared, C or K for cubus x cubed, etc. Thus x squared plus 5x minus 4 would have been written 1z p period 5r m period 4, where p stands for plus and m stands for minus. Xylander, in his edition of the Arithmetic of Diophantus in 1575, used other letters, and the symbols plus and minus would have been written in the above expressions thus: 1q plus 5n minus 4. A similar notation was sometimes used by Vieta and even by Fermat. The advance made by Bombelli was that he introduced a symbol like a semicircle holding a 1 above it, which I'll just call cup 1 for the unknown quantity, and cup 2 for its square, and cup 3 for its cubed, and so on, and therefore he wrote x squared plus 5x minus 4 as 1 cup 2 p period 5 cup 1 m period 4. Stevenius in 1586 employed 1 in a circle, 2 in a circle, and 3 inside a circle in a similar way, which I'll call circle 1, circle 2, circle 3, and suggested, though he did not use a corresponding notation for fractional indices, he would have written the above expression as 1 circle 2 plus 5 circle 1 minus 4 circle 0. But whether the symbols were more or less convenient, they were still only abbreviations for words, and were subject to all the rules of syntax. They merely afforded a sort of shorthand which the various steps and results could be expressed concisely. The next advance was the creation of symbolic algebra, and the chief credit of that is due to Vieta. The development of symbolic algebra. We have now reached a point beyond which any considerable development of algebra, so long as it was strictly syncopated, could hardly proceed. It is evident that Stifel and Bombelli and other writers of the 16th century had introduced or were on the point of introducing some of the ideas of symbolic algebra. But so far as the credit of inventing symbolic algebra can be put down to any one man, we may perhaps assign it to Vieta, while we may say that Harriot and Descartes did more than any other writers to bring it into the general use. It must be remembered, however, that it took time before all these innovations became generally known, and they were not familiar to the mathematicians until the lapse of some years after they had been published. End of section 17. Recording by Paul King. pjk.scripts.mit.edu/pkj Chapter 12, Part 3 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 12, Part 3. The Mathematics of the Renaissance, 1450 to 1637. Vieta. Franciscus Vieta, Francois Viete, born in 1540 at Fontenay near La Rochelle and died in Paris in 1603. He was brought up as a lawyer and practiced for some time at the Parisian bar. He then became a member of the provincial parliament in Brittany, and finally in 1580, through the influence of the Duc de Rohan, he was made Master of Requests, an office attached to the Parliament at Paris. The rest of his life was spent in the public service. He was a firm believer in the divine right of kings, and possibly a zealous Catholic. After 1580 he gave up most of his leisure to mathematics, though his great work In Artem Analyticam Isagoge, in which he explained how algebra could be applied to the solution of geometrical problems, was not published till 1591. His mathematical reputation was already considerable when one day the ambassador from the Low Countries remarked to Henry IV. That France did not possess any geometricians capable of solving a problem which had been propounded in 1593 by his countryman Adrian Romanus to all the mathematicians of the world, and which required the solution of an equation of the 45th degree. The king thereupon summoned Vieta and informed him of the challenge. Vieta saw that the equation was satisfied by a chord of a circle of unit radius which subtends an angle 2π/45 at the centre, and in a few minutes he gave back to the king two solutions of the problem written in pencil. In explanation of this feat I should add that Vieta had previously discovered how to form the equation connecting sin n theta with sin theta and cos theta. Vieta in his turn asked Romanus to give the geometrical construction to describe a circle which should touch three given circles. This was the problem which Apollonius had treated in his De Tactionibus, a lost book which Vieta at a later time conjecturally restored. Romanus solved the problem with the aid of the conic sections, but failed to do it by Euclidean geometry. Vieta gave a Euclidean solution which so impressed Romanus that he travelled to Fontenay, where the French court was then settled, to make Vieta's acquaintance, an acquaintanceship which rapidly ripened into a warm friendship. Henry was much struck with the ability shewn by Vieta in this matter. The Spaniards had at the time a cipher containing nearly 600 characters, which was periodically changed, and which they believed to be impossible to decipher. A despatch having been intercepted, the king gave it to Vieta, and asked him to try to read it and find the key to the system. Vieta succeeded, and for 2 years the French used it greatly to their profit in the war which was then raging. So convinced was Philip II. That the cipher could not be discovered, that when he found his plans known he complained to the Pope that the French were using sorcery against him, contrary to the practice of the Christian faith. Vieta wrote numerous works on algebra and geometry. The most important are In Artem Analyticam Isagoge, Tours 1591, the Supplementum Geometriae, and the collection of geometrical problems, Tours 1593, and the De Numerosa Potestatum Resolutione, Paris 1600. All of these were printed for private circulation only, but they were collected by F. van Schooten and published in one volume at Leyden in 1646. Vieta also wrote the De Equationum Recognitione et Emendatione, which was published after his death in 1615 by Alexander Anderson. The In Artem is the earliest work on symbolic algebra. It also introduced the use of letters for both known and unknown quantities, a notation for the powers of quantities, and enforced the advantage of working with homogeneous equations. To this an appendix called Logistes Speciosa was added on addition and multiplication of algebraical quantities and on the powers of a binomial up to the sixth. Vieta implies that he knew how to form the coefficients of these 6 expansions by means of the arithmetical triangle as Tartaglia had previously done. But Pascal was the first to give the general rule for forming it for any order, which is equivalent to saying that he could write down the coefficients of x in the expansion 1 plus x quantity to the power n if those in the expansion of 1 plus x quantity to the power n minus 1 were known. Newton was the first to give the general expression for the coefficient of x raised to the power p in the expansion of 1 plus x quantity to the power n. Another appendix known as Zetetica on the solution of equations was subsequently added to the In Artem. The In Artem is memorable for 2 improvements in algebraic notation which were introduced here, though it is probable that Vieta took the idea from both other authors.
One of these improvements was that he denoted the known quantities by the consonants b, c, d, etc., and the unknown quantities by the vowels a, e, I, etc. Thus in any problem he was able to use a number of unknown quantities. In this particular point he seems to have been forestalled by Jordanus and Stifel. The present custom of using the letters at the beginning of the alphabet a, b, c to represent known quantities, and those toward the end x, y, z to represent the unknown quantities, was introduced by Rene Descartes in 1637. The other improvement was this. To this time it had been the custom to introduce new symbols to represent the square, cube, and so on of quantities which had already occurred in the equations. Thus if r or n stood for x, z, c, or q stood for x squared, and c or k for x cubed, etc. So long as this was the case, the chief advantage of algebra was that it afforded a concise statement of results, every statement of which was reasoned out. But when Vieta used a to denote the unknown quantity x, he sometimes employed a quadratus a cubus to represent x squared and x cubed, which at once shewed the connection between the different powers. And later the successive powers of a were commonly denoted by the abbreviations aq, ac, aqq, etc. Thus Vieta would have written the equation 3ba squared minus da plus a cubed equals z as b3 in a quadratur minus d plano in a plus a cubo equatur z solido. It will be observed that the dimensions of the constants b, d, and z are chosen so as to make the equation homogeneous. This is characteristic of all his work. It will also be noticed that he does not use a sign for equality. In fact, the particular sign equals, which we use to denote equality, was employed by him to represent the difference between. Vieta's notation is not so convenient as that previously used by Bombelli and Stevinus, but it was more generally adopted. Occasional instances of an approach to index notation, such as a to the power q, are said to occur in Vieta's works. These two steps were almost essential to any further progress in algebra. In both of them Vieta had been forestalled, but it was his good luck in emphasizing their importance to be the means of making them generally known at a time when opinion was ripe for such an advance. The De Equationem Recognitione et Emendatione is mostly on the theory of equations. Vieta here shewed that the first member of an algebraical equation, phi of x equals 0, could be resolved into linear factors, and explained how the coefficients of x could be expressed as functions of the roots. He also indicated how from a given equation another could be obtained whose roots were equal to those of the original, increased by a given quantity or multiplied by a given quantity, and he used this method to get rid of the coefficients of x in a quadratic equation and of the coefficient of x squared in a cubic equation, and was thus enabled to give the general algebraic solution of both. His solution of a cubic equation is as follows. First, reduce the equation to the form x cubed plus 3a squared x equals 2b cubed. Next, let x equal a squared over y minus y, and we get y to the sixth plus 2b cubed y cubed equals a to the sixth, which is a quadratic in y cubed. Hence y can be found, and therefore x can be determined. His solution of a biquadratic is similar to that known as Ferrari's. He first got rid of the term involving x cubed, thus reducing the equation to the form x to the fourth plus a squared x squared plus b cubed x equals c to the power 4. He then took the terms involving x squared and x to the right hand side of the equation and added x squared y squared plus a quarter y to the fourth to each side, so that the equation became quantity x squared plus half y squared all squared equals x squared multiplied by the quantity y squared minus a squared, subtract b cubed x plus a quarter y to the fourth plus c to the fourth. He then chose y so that the right hand side of this equality is a perfect square. Substituting this value of y, he was able to take the square root of both sides and thus obtain two quadratic equations for x, each of which can be solved. The De Numerosa Potestatem Resolutione deals with the numerical equations. In this, a method of approximating to the values of positive roots is given, but it is prolix and of little use, though the principle, which is similar to that of Newton's rule, is correct. Negative roots are uniformly rejected. This work is hardly worthy of Vieta's reputation. Vieta's trigonometrical researches are included in various tracts which are collected in Schutten's edition. Besides some trigonometrical tables, he gave the general expression for the sine or chord of an angle in terms of the sine and cosine of its submultiples. Delambre considers this as the completion of the Arab system of trigonometry. We may take it then that from this time the results of elementary trigonometry were familiar to mathematicians. Vieta also elaborated the theory of right-angled spherical triangles. Among Vieta's miscellaneous tracts will be found a proof that each of the famous geometrical problems of the trisection of an angle and the duplication of the cube depends on the solution of a cubic equation. There are also some papers connected with an angry controversy with Clavius in 1594 on the subject of the reformed calendar, in which Vieta was not well advised. Vieta's works on geometry are good, but they contain nothing which requires mention here. He applied algebra and trigonometry to help him in investigating the properties of figures. He also, as I have already said, laid great stress on the desirability of always working with homogeneous equations, so that if a square or a cube were given, it should be denoted by expressions like a squared or b cubed, but not by terms like m or n which do not indicate the dimensions of the quantities they represent. He had a lively dispute with Scaliger on the latter publishing a solution of the quadrature of the circle, and succeeded in shewing the mistake into which his rival had fallen. He gave a solution of his own which as far as it goes is correct, and stated that the area of a square is to that of the circumscribing circle as the square root of a half times the square root of the quantity a half plus the square root of a half multiplied by the quantity in brackets the square root of a half plus the quantity square root of a half plus the square root of a half, end of quantity, ad infinitum. This is one of the earliest attempts to find the value of pi by means of an infinite series. He was well acquainted with the extant writings of the Greek geometricians, and introduced the curious custom, which during the 17th and 18th centuries became fashionable, of restoring lost classical works. He himself produced a conjectural restoration of De Tactionibus of Apollonius. Girard. Vieta's results in trigonometry and the theory of equations were extended by Albert Girard, a Dutch mathematician who was born in Lorraine in 1590 and died in 1633. In 1626 Girard published at The Hague a short treatise on trigonometry, to which were appended tables of the values of the trigonometrical functions. This work contains the earliest use of the abbreviations sin, sin, tan, tan, and sec, sec, for sine, tangent, and secant. The supplemental triangles in a spherical trigonometry are also discussed, and seem to have been discovered by Girard independently of Vieta, and he also gave the expression for the area of the spherical triangle in terms of the spherical excess. This was discovered independently by Calivari. In 1627 Girard brought out an edition of Malraux's geometry with considerable additions. Girard's chief discoveries are contained in his Invention nouvelle en algèbre, published at Amsterdam in 1629. This contains the earliest use of brackets, a geometrical interpretation of the negative sign, the statement that the number of roots in an algebraical equation is equal to its degree, the distinct recognition of imaginary roots, and probably implies also a knowledge that the first member of an algebraical equation phi of x equals 0 could be resolved into linear factors. Girard's researches were unknown to most of his contemporaries and exercised no appreciable influence on the development of mathematics. The invention of logarithms by Napier of Merchistown in 1614 and their introduction into England by Briggs and others have already been mentioned in chapter 11. Napier. John Napier was born in Merchistown in 1550 and died on April 4, 1617. He spent most of his time on the family estate near Edinburgh and took an active part in the political and religious controversies of the day. The business of his life was to shew that the Pope was the Antichrist, but his favourite amusement was the study of mathematics and science. As soon as the use of exponents became common in algebra, the introduction of logarithms would naturally follow, but Napier reasoned out that the result without the use of any symbolic notation to assist him, and the invention of logarithms was so far from being a sudden inspiration that it was the result of efforts of many years with a view to abbreviate the processes of multiplication and division. It is likely that Napier's attention may have been partly directed to the desirability of facilitating computations by the stupendous arithmetical efforts of some of his contemporaries, who seem to have taken a keen pleasure in surpassing one another in the extent to which they carried out multiplications and divisions. The trigonometrical tables by Rheticus, which were published in 1596 and 1613, were calculated in a most laborious way. Vieta himself delighted in arithmetical calculations which must have taken hours or days of hard work, and of which the results often served no useful purpose. L. van Keulen (1539 1610) practically devoted his life to finding a numerical approximation to the value of pi, finally in 1610 obtaining it correct to 35 places of decimals, while, to cite one more instance, P. A. Cataldi (1548 1626), who is chiefly known for his invention in 1613 of the form of continued fractions, though he failed to establish any of their properties, must have spent years in numerical calculations. In regard to Napier's other work, I may again mention that in his Rhabdologia, published in 1617, he introduced an improved form of rod by the use of which the product of two numbers can be found in a mechanical way. They can also be used for finding the quotient of one number by another. He also invented two other rods called virgulae, by which the square and the cube roots can be extracted. I should add that in spherical trigonometry he discovered certain formulae known as Napier's analogies, and also enunciated a rule of circular parts for the solution of right-angled spherical triangles. Briggs. The earliest table of common logarithms was constructed by Briggs and published in 1617. Henry Briggs was born near Halifax in 1556. He was educated at St. John's College, Cambridge, and took his degree in 1581 and obtained a fellowship in 1588. He was elected to the Gresham Professorship of Geometry in 1594, and in 1619 became Savilian Professor at Oxford, a chair which he held until his death on January 26, 1631. It may be interesting to add that the chair of geometry founded by Sir Thomas Gresham in 1596 was the earliest professorship of mathematics established in Great Britain. Some 20 years earlier Sir Henry Savile had given at Oxford open lectures on Greek geometry and geometricians, and in 1619 he endowed the chairs of geometry and astronomy in that university which are still associated with his name. Both in London and at Oxford Briggs was the first occupant of the chair of geometry. He began his lectures at Oxford with the ninth proposition of the first book of Euclid, that being the furthest point to which Savile had been able to carry his audiences. At Cambridge the Lucasian chair was established in 1663, the earliest occupants being Barrow and Newton. The almost immediate adoption through Europe of logarithms for astronomical and other calculations was mainly the work of Briggs. Amongst others he convinced Kepler of the advantages of Napier's discovery, and the spread of the use of logarithms was rendered more rapid by the zeal and reputation of Kepler, who by his tables of 1625 and 1629 brought them into vogue in Germany, while Cavalieri in 1624 and Edmund Wingate in 1626 did similar service for Italian and French mathematicians respectively. Harriot. Thomas Harriot, born at Oxford in 1560 and died in London on July 2, 1621, did a great deal to extend and codify the theory of equations. The early part of his life was spent in America with Sir Walter Raleigh. While there he made the first survey of Virginia and North Carolina, the maps of these being subsequently presented to Queen Elizabeth. On his return to England he settled in London and gave up most of his time to mathematical studies. The majority of the propositions I have assigned to Vieta are to be found in Harriot's writings, but it is uncertain whether they were discovered by him independently of Vieta or not. In any case it is probable that Vieta had not fully realized all that was contained in the propositions he had enunciated. The full consequences of these, with numerous extensions and systematic exposition of the theory of equations, were given by Harriot in his Artis Analyticae Praxis, which was first printed in 1631. The Praxis did not differ essentially from a good modern textbook. It is far more analytical than any algebra that preceded it, and marks a great advance in both symbolism and notation. It was widely read and proved one of the most powerful instruments in bringing analytical methods into general use. Harriot was, I believe, the earliest writer who realized the advantage to be obtained by taking all of the terms of an equation to one side of it. He was the first to use angle bracket signs to denote greater than and less than. When he denoted the unknown quantity by a, he represented a squared by a cubed by aaa, and so on. This is a distinct improvement on Vieta's notation. The same symbolism was used by Wallis as late as 1685, but concurrently with the modern index notation which was introduced by Descartes. Extracts from some of the other writings of Harriot were published by Rigaud in 1833. Oughtred. Among those who contributed to the general adoption in England of those various improvements and additions to algorism and algebra was William Oughtred, who was born at Eton on March 5, 1574, and died at his vicarage of Albury in Surrey on June 30, 1660. It is usually said that the cause of his death was the excitement and delight which he experienced at hearing the House of Commons had voted the king's return. But a recent critic adds that it should be remembered that by way of excuse that he, Oughtred, was then 86 years old. Oughtred was educated at Eton and King's College, Cambridge, of the latter of which colleges he was a fellow and for some time a mathematical lecturer. His Clavis Mathematica, published in 1631, is a good systematic textbook on arithmetic, and it contains practically all that was then known on the subject. In this work he introduced the symbol times for multiplication, and the symbol double colon in proportion, Previously to this time a proportion such as a colon b equals c colon d was usually written as a minus sine b minus sine c minus sine d, but he denoted it by a dot b colon colon c dot d. Wallace says that some found fault with the book on account of the style, but that they only displayed their own incompetence, for Oughtred's words would be always full but not redundant. Pell makes a somewhat similar remark. Oughtred also wrote a treatise on trigonometry published in 1657, in which abbreviations for sine, cosine, etc. were employed. This was really an important advance, but the works of Girard and Oughtred in which they were used were neglected and soon forgotten, and it was not until Euler reintroduced the contractions for the trigonometrical functions that they were generally adopted. We may say roughly that henceforth elementary arithmetic, algebra, and trigonometry were treated in a manner which is not substantially different from that now in use, and that the subsequent improvements introduced were additions to the subjects then known, and not a rearrangement of them on new foundations. The origins of the more common symbols in algebra. It may be convenient if I collect here in one place the scattered remarks I have made on the introduction of the various symbols of the more common operations in algebra. The latter Greeks and the Hindus and Jordanus indicated addition by mere juxtaposition. It will be observed that this is still the custom in arithmetic, where for example 2 1/2 stands for 2 plus 1/2. The Italian algebraists, when they gave up expressing every operation in words at full length, and introduced syncopated algebra, usually denoted plus by its initial letter p, or a line being sometimes drawn through the letter to shew that it was a symbol of operation and not a quantity, but the practice was not uniform. Pacioli, for example, sometimes denoted it by p with a bar on top, and sometimes by e, and Tartaglia commonly denoted it by the Greek letter phi. The German and English algebraists, on the other hand, introduced the sign plus almost as soon as they used algorism, but they spoke of it as signum additorem and employed it only to indicate excess. They also used it in the sense referred to previously. Widman used it as an abbreviation for excess in 1489. By 1630 it was part of the recognized notation of algebra and was used as a symbol of operation. Subtraction was indicated by Diophantus as an inverted and truncated Greek letter phi. The Hindus denoted it by a dot. The Italian algebraists, when they introduced syncopated algebra, generally denoted minus by m, big capital M or lowercase m, a line being sometimes drawn through the letter, but the practice was not uniform. Pacioli, for example, denoting it sometimes by m with a bar over it, and sometimes by de for demptus. The German and English algebraists introduced the present symbol by which they described signum subtractorum. It is most likely that the vertical bar in the symbol for plus was superimposed on the symbol for minus to distinguish the two. In origin both symbols were probably mercantile marks. It may be noticed that Pacioli and Tartaglia found the sign minus already used to denote a division, a ratio, or a proportion indifferently. The present sign was in general use by about the year 1630 and was then employed as a symbol of operation. Oughtred in 1631 used the sign times to denote multiplication. Harriot in 1631 denoted the operation by a dot. Descartes in 1637 indicated it by juxtaposition. I am not aware of any symbols for it which were in previous use. Leibniz in 1686 employed the sign an inverted semicircle facing down to denote multiplication and a semicircle facing up to denote division. Division was ordinarily denoted by the Arab way of writing quantities in the form of a fraction by means of a line drawn between them in any of the forms a b, a/b, or a/b. Oughtred in 1631 employed a dot to denote either division or a ratio. I do not know when the colon was first introduced to denote a ratio, but it occurs in a work by Clairaut published in 1760. I believe that the then current symbol for division, with a dash inside a colon, is only a combination of the dash and the colon. It was used by John Hendrik Run at Zurich in 1659 and John Pell in London in 1668. The current symbol for equality was introduced by Record in 1557. Xylander in 1575 denoted it by two parallel vertical lines, but in general till the year 1600 the word was written at length, and from then until the time of Newton, say about 1680, it was more frequently represented by an alpha or a reverse alpha than by any other symbol. Each of these latter signs were used as a contraction for the first two letters of the word aequalis. I may add that Vieta, Schouten, and others employed the sign equals to denote the difference between. Thus a equal sign b meant with them what we denote by a minus b. The symbol double colon to denote proportion or by the equality of two ratios was introduced by Oughtred in 1631 and it was brought into common use by Wallis in 1686. There is no object in having a symbol to indicate equality of two ratios which is different from that used to indicate equality of other things, and it is better to replace it by the sign equals. The sign right angle bracket for is greater than and the sign left angle bracket for is less than were introduced by Harriot in 1631, but Oughtred simultaneously invented different symbols for greater than less than, and these latter were frequently used until the beginning of the 18th century, e.g. by Barrow. The symbol equal sign with a stroke through it for is not equal to, a right angle bracket with a stroke through it for is not greater than, and a left angle bracket with a stroke through it for is not less than, are of recent introduction. The vinculum was introduced by Vieta in 1591, and the brackets were first used by Girard in 1629. The different methods of representing the power to which a magnitude was raised have already been briefly alluded to. The earliest known attempt to frame a symbolic notation was made by Bombelli in 1572 when he represented an unknown quantity by 1 inside an upturned semicircle, and its square by 2 inside an upturned semicircle, and its cube by a 3 inside an upturned semicircle, etc. In 1586 Stevinus used 1 written inside a circle, 2 written inside a circle, 3 written inside a circle in a similar way, and suggested, though he did not use a corresponding notation for fractional indices. In 1591 Vieta improved on this by denoting the different powers of a by a quad, a cub, etc., so that he could indicate the powers of different magnitudes. Harriot in 1631 further improved on Vieta's notation by writing AA for a squared, AAA for a cubed, etc. And this remained in use for 50 years concurrently with the index notation. In 1634 P. Herragonus in his Cursus Mathematicus, published in 5 volumes at Paris in 1634 to 1637, wrote A2, A3 for a squared, a cubed. The symbol surd to denote the square root was first introduced by Rudolph in 1526. A similar notation had been used by Bhaskara. The idea of using exponents to mark the power to which a quantity was raised was due to Descartes, and was introduced by him in 1637, but he used only positive integral indices, a to the 1, a squared, a cubed, and so on.
Wallis in 1659 explained the meaning of negative fractional indices in expressions such as x to the power of -1 or x to the power of 2/3, etc., the latter conception having been foreshadowed by Oresmus and perhaps by Stevinus. Finally, the idea of an index unrestricted in magnitude such as the n in the expansion of a to the power n, I believe, is due to Newton and was introduced by him in connection with the binomial theorem in the letters for Leibniz written in 1676. The symbol 8 written sideways for infinity was first employed by Wallis in 1655 in his Arithmetica Infinitorum, but does not occur again until 1713 when it is used in James Bernoulli's Ars Conjectandi. The sign was sometimes employed by the Romans to denote the number 1000, and it has been conjectured that this led to its being applied to represent any very large number. There are but few special symbols in trigonometry. I may however add here the following note which contains all that I have been able to learn on the subject. The current sexagesimal division of angles is derived from the Babylonians through the Greeks. The Babylonian unit angle was the angle of an equilateral triangle. Following their usual practice, this was divided into 60 equal parts or degrees. A degree was subdivided into 60 equal parts or minutes, and so on. The word sine was used by Regiomontanus and was derived from the Arabs. The terms secant and tangent were introduced by Thomas Finck, born in Denmark in 1561 and died in 1646, in his Geometriae Rotundae, Bale 1583. And the word cosecant, I believe, was first used by Rheticus in his Opus Palatinum 1596. The terms cosine and cotangent were first employed by E. Gunter in his Canon Triangularum, London 1620. The abbreviations sin, sin, tan, tan, sec for secant were used in 1626 by Albert Gerard, and those of cos, cos, and cot for cotangent by Oughtred in 1657, but these contractions did not come into general use till Euler reintroduced them in 1748. The idea of trigonometrical functions originated with John Bernoulli, and this view of the subject was elaborated in 1748 by Euler in his Introductio in Analysen Infinitorum. End of section 16. Recording by Paul King, pjk.scripts.mit.edu/pkj. Chapter 13 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 13. The close of the Renaissance, circa 1586 to 1637. The closing years of the Renaissance were marked by a revival of interest in nearly all branches of mathematics and science. As far as pure mathematics is concerned, we have already seen that during the last half of the 16th century there had been a great advance in algebra, theory of equations, and trigonometry. And we shall shortly see in the second section of this chapter that in the early part of the 17th century some new processes in geometry were invented. If, however, we turn to applied mathematics, it is impossible not to be struck by the fact that even as late as the middle or end of the 16th century no marked progress in the theory had been made from the time of Archimedes. Statics of solids and hydrostatics remained in much the state in which he had left them, while dynamics as a science did not exist. It was Stevinus who gave us the first impulse to the renewed study of statics, and Galileo who laid the foundation of dynamics, and to their works the first section of this chapter is devoted. The development of mechanics and experimental methods. Stevinus. Simon Stevinus was born in Bruges in 1548 and died at The Hague in the 17th century. We know very little of his life save that he was originally a merchant's clerk at Antwerp, and at a later period of his life was the friend of Prince Maurice of Orange, by whom he was made quartermaster general of the Dutch army. To his contemporaries he was the best known for his works on fortifications and military engineering, and the principles he laid down are said to be in accordance with those which are now usually accepted. To the general populace he was also well known on account of his invention of a carriage which was propelled by sails. This ran on the seashore, carried 28 people, and easily outstripped horses galloping by the side. His model of it was destroyed in 1802 by the French when they invaded Holland. It was chiefly owing to the influence of Stevinus that the Dutch and French began a proper system of bookkeeping in the national accounts. I have already alluded to the introduction in his arithmetic, published in 1585, of exponents to mark the power to which quantities were raised. He is said to have suggested the use of fractional but not negative exponents. For instance, he wrote 3x squared minus 5x plus 1 as 3 followed by 2 in a circle for x squared minus 5 followed by a 1 in a circle signifying x plus 1 followed by a solid dot in a circle. His notation for decimal fractions was of a similar character. In the same book he likewise suggested a decimal system of weights and measures. He also published a geometry which is ingenious, though it does not contain many results which were not previously known. It is however on his statics and hydrostatics, published in Flemish at Leyden in 1586, that his fame will rest. In this work he enunciated the triangle of forces, a theorem which some think was the first propounded by Leonardo da Vinci. Stevinus regarded this as the fundamental proposition of the subject. Previous to the publication of his work the science of statics had rested on the theory of the lever, but since then it has been usual to commence by proving the possibility of representing forces by straight lines, and so of reducing many theorems to geometrical propositions, and in particular to obtaining in that way a proof of the parallelogram, which is equivalent to the triangle of forces. Stevinus is not clear in his arrangement of the various propositions and discussions of their sequence, and the new treatment of the subject was not definitely established before the appearance in 1687 of Varignon's work on mechanics. Stevinus also found the force which must be exerted along the line of the greatest slope to support a given weight on an inclined plane, a problem the solution of which had long been in dispute. He further distinguished between stable and unstable equilibrium. In hydrostatics he discussed the question of the pressure which a fluid can exercise, and explained the so-called hydrostatic paradox. Stevinus was somewhat dogmatic in his statements and allowed no one to differ from his conclusions. And those, says he in one place, who cannot see this, may the author of nature have pity upon their unfortunate eyes, for the fault is not in the thing, but in the sight which we are not able to give them. Galileo. Just as the modern treatment of statics originates with Stevinus, so the foundation of the science of dynamics is due to Galileo. Galileo Galilei, born in Pisa on February 18, 1564, and died near Florence on January 8, 1642. His father, a poor descendant of an old and noble Florentine house, was himself a fair mathematician and a good musician. Galileo was educated at the monastery in Vallombrosa, where his literary ability and mechanical ingenuity attracted considerable attention. He was persuaded to become a novitate of the order in 1580, but his father, who intended him to be a doctor, at once removed him and sent him in 1581 to the University of Pisa to study medicine. It was there that he noticed that the great bronze lamp which still hangs from the roof of the cathedral performed its oscillations in equal times, quite independently of whether the oscillations were large or small, a fact which he verified by counting his pulse. He had been hitherto purposely kept in ignorance of mathematics, but one day, by chance hearing a lecture on geometry, he was so fascinated by the science that he thenceforward devoted all of his spare time to its study, and finally he got leave to discontinue his medical studies. He left university in 1586 and almost immediately commenced his original researches. He published in 1587 an account of the hydrostatic balance, and in 1588 an essay on the centre of gravity in solids. The fame of these works secured for him the appointment to the mathematical chair at Pisa, the stipend, as was the case with most professorships, being very small. During the next 3 years he carried on from the leaning tower that series of experiments on falling bodies which established the first principles of dynamics. Unfortunately, the manner in which he promulgated his discoveries and the ridicule he threw on those who opposed him gave not an unnatural offence, and in 1591 he was obliged to resign his position. At this time he seems to have been much hampered by want of money. Influence was however exerted on his behalf with the Venetian Senate, and he was appointed professor at Padua, a chair which he held for 18 years, 1592 to 1610. His lectures there seem to have been chiefly on the mechanics and hydrostatics, and the substance of them is contained in his treatise on mechanics, which was published in 1612. In these lectures he repeated his Pisan experiments and demonstrated that falling bodies did not, as was then believed, descend with velocities proportional, amongst other things, to their weights. He further shewed that, if it were assumed that they were descended with a uniformly accelerated motion, it was possible to deduce the relations of connecting velocity, space, and time, which did actually exist. At a later date, by observing the times of descent of bodies sliding down inclined planes, he shewed that this hypothesis was true. He also proved that the path of a projectile was a parabola, and in doing so implicitly used the principles laid down in the first 2 laws of motion as enunciated by Newton. He gave an accurate definition of momentum, which some writers have thought may be taken to imply a recognition of the truth of the third law of motion. The laws of motion are however nowhere enunciated in the precise and definite form, and Galileo must be regarded rather as preparing the way for Newton than as being himself the creator of the science of dynamics. In statics he laid down the principle that in machines what was gained in power was lost in speed, and in the same ratio. In the statics of solids he found the force which can support a given weight on an inclined plane. In hydrostatics he propounded the more elementary theorems on pressure and on floating bodies, while among hydrostatical instruments he invented the thermometer, though in a somewhat imperfect form. It is, however, as an astronomer that most people regard Galileo, and though strictly speaking his astronomical researches lie outside the subject matter of this book, it may be interesting to give the leading facts. It was in the spring of 1609 that Galileo heard that a tube containing lenses had been made by Lippershey in Holland, which served to magnify objects seen through it. This gave him the clue, which he constructed a telescope of that kind which still bears his name, and of which an ordinary opera glass is an example. Within a few moments he had produced instruments which were capable of magnifying 32 diameters, and within a year he had made and published observations on the solar spots, the lunar mountains, Jupiter's satellites, the phases of Venus, and Saturn's ring. Honours and emoluments were showered on him, and he was enabled in 1610 to give up his professorship and retire to Florence. In 1611 he paid a temporary visit to Rome, and exhibited in the gardens of the Vatican the new worlds revealed by the telescope. It would seem that Galileo had always believed in the Copernican system, but was afraid of promulgating it on account of the ridicule it excited. The existence of Jupiter's satellites seemed however to make this truth almost certain, and he now boldly preached it. The orthodox party resented his action, and on February 24, 1616, the Inquisition declared that to suppose the sun the centre of the solar system was absurd, heretical, and contrary to Holy Scripture. The edict of March 5, 1616, which carried this into effect, had never been repealed, though it has long been tacitly ignored. It is well known that toward the middle of the 17th century the Jesuits evaded it by treating the theory as an hypothesis from which, though false, certain results would follow. In January 1632 Galileo published his dialogues on the system of the world, in which in clear and forcible language he expounded the Copernican theory. In these, apparently through jealousy of Kepler's fame, he does not so much as mention Kepler's laws, the first two of which had been published in 1609 and the third in 1619, and he rejects Kepler's hypothesis that the tides are caused by the attraction of the moon. He rests the proof of the Copernican hypothesis on the absurd statement that it would cause tides because different parts of the earth would rotate with different velocities. He was more successful in shewing that mechanical principles would account for the fact that a stone thrown straight up would fall again to the place from which it was thrown, a fact which had previously been one of the chief difficulties in the way of any theory which supposed the earth to be in motion. The publication of this book was certainly contrary to the edict of 1616. Galileo was at once summoned to Rome, forced to recant, do penance, and was only released on good behaviour. The documents recently printed shew that he was threatened with the torture, but that there was no intention of carrying the threat into effect. When released he again took up his work on mechanics, and by 1636 had finished a book which was published under the title Discorsi intorno ad nuove scienze at Leyden in 1638. In 1637 he lost his sight, but with the aid of pupils he continued his experiments on mechanics and hydrostatics, and in particular on the possibility of using a pendulum to regulate a clock, and on the theory of impact. An anecdote of this time has been preserved which may or may not be true, but is sufficiently interesting to bear repetition. According to one version of the story, Galileo was one day interviewed by some members of a Florentine guild who wanted their pumps altered so as to raise water to a height which was greater than 30 feet, and thereupon he remarked it might be desirable to first find out why the water rose at all. A bystander interfered and said there was no difficulty about that because nature abhorred a vacuum. Yes, said Galileo, but apparently it is only a vacuum which is less than 30 feet. His favourite pupil Torricelli was present, and thus had his attention directed to the question, which he subsequently elucidated. Galileo's work may, I think, be fairly summed up by saying that his researches on mechanics are deserving of high praise, and that they are memorable for clearly enunciating the fact that science must be founded on laws obtained by experiment. His astronomical observations and his deductions therefrom were also excellent, and were expounded with a literary and scientific skill which leaves nothing to be desired. But though he produced some of the evidence which placed the Copernican theory on a satisfactory basis, he did not himself make any special advance in the theory of astronomy. Francis Bacon. The necessity of an experimental foundation for science was advocated with even greater effect by Galileo's contemporary Francis Bacon, Lord Verulam, who was born in London on January 22, 1561, and died on April 9, 1626. He was educated at Trinity College, Cambridge. His career in politics and at the bar culminated in his becoming Lord Chancellor with the title Lord Verulam. The story of his subsequent degradation for accepting bribes was well known. His chief work is the Novum Organum, published in 1620, which he lays down the principles which should guide those who are making experiments on which they propose to find a theory of any branch of physics or applied mathematics. He gave rules by which the results of induction could be tested, hasty generalizations avoided, and experiments used to check one another. The influence of this treatise in the 18th century was great, but it is probable that during the preceding century it was little read, and the remark repeated by several French writers that Bacon and Descartes are the creators of modern philosophy rests on a misapprehension of Bacon's influence on his contemporaries. Any detailed account of this book belongs, however, to the history of scientific ideas rather than to that of mathematics. Before leaving the subject of applied mathematics, I may add a few words on the writings of Guldinus, Wright, and Snell. Guldinus. Habakkuk Guldinus, born in St. Gall on June 12, 1577, and died at Graz, November 3, 1643, was of Jewish descent, but was brought up as a Protestant. He was converted to Roman Catholicism and became a Jesuit when he took the Christian name of Paul, and it was to him that the Jesuit colleges in Rome and Graz owed their mathematical reputation. The two theorems known by the name of Pappus, to which I alluded, were published by Guldinus in the fourth book of his De Centro Gravitatis, Vienna, 1635–1642. Not only were the rules in question taken without acknowledgment from Pappus, according to Montecle, the proof of them was given by Guldinus was faulty, even though he was successful in applying them to the determination of the volumes and surfaces of certain solids. The theorems were however previously unknown, and their enunciation excited considerable interest. Wright. I may here also refer to Edward Wright, who is worthy of mention for having put the art of navigation on a scientific basis. Wright was born in Norfolk at about 1560 and died in 1615. He was educated at Caius College, Cambridge, of which society he was subsequently a fellow. He seems to have been a good sailor, and he has special talent for the construction of instruments. About 1600 he was elected lecturer on mathematics by the East India Company. He then settled in London and shortly afterwards was appointed mathematical tutor to Prince Henry of Wales, the son of James I. His mechanical ability may be illustrated by an orrery of his construction, by which it was possible to predict eclipses for over 17,000 years in advance. It was shewn in the Tower as a curiosity as late as 1675. In the maps in use before the time of Gerard Mercator, a degree, whether of latitude or longitude, had been represented in all cases by the same length, and the course to be pursued by a vessel was marked on the map by a straight line joining the ports of arrival and departure. Mercator had seen that this led to considerable errors, and had realized that to make this method of tracing the course of a ship at all accurate, the space assigned on the map to a degree of latitude ought to gradually increase as the latitude increased. Using this principle, he had empirically constructed some charts which were published about 1560 or 1570. Wright set himself the problem to determine the theory on which such maps should be drawn, and succeeded in discovering the law of the scale of the maps, though his rule is strictly correct for small arcs only. The result was published in the second edition of Blundeville's Exercises. In 1599 Wright published his Certain Errors in Navigation Detected and Corrected, in which he explained the theory and inserted a table of meridional parts. The reasoning shews considerable geometrical power. In the course of the work he gives the declinations of 32 stars, explains the phenomenon of the dip, parallax, and refraction, and adds a table of magnetic declinations, but he assumes the earth to be stationary. In the following year he published some maps constructed on his principle. In these the northernmost point of Australia is shewn, the latitude of London is taken to be 51 degrees 32 minutes. Snell. A contemporary of Guldinus and Wright was Wilbrod Snell, whose name is still well known through his discovery in 1619 of the law of refraction in optics. Snell was born at Leyden in 1591 and occupied a chair of mathematics at the university there, and died there on October 30, 1626. He was one of those infant prodigies who occasionally appear. At the age of 12 he was acquainted with the standard mathematical works. I will here only add that in geodesy he laid down the true principles for measuring the arc of a meridian, and in spherical trigonometry he discovered the properties of the polar or supplemental triangle. Residual interest in pure geometry. The close of the 16th century was marked not only by the attempt to find a theory of dynamics based on laws derived from experiment, but also by a revived interest in geometry. This was largely due to the influence of Kepler. Johann Kepler, one of the founders of modern astronomy, was born of humble parents near Stuttgart on December 27, 1571, and died at Ratisbon on November 15, 1630. He was educated under Maestlin at Tübingen. In 1593 he was appointed professor at Graz, where he made the acquaintance of a wealthy and beautiful widow whom he married, but found too late that he had purchased his freedom from pecuniary troubles at the expense of domestic happiness. In 1599 he accepted an appointment as assistant to Tycho Brahe, and in 1601 succeeded his master as astronomer to the Emperor Rudolf II. But his career was dogged by bad luck. First his stipend wasn't paid, next his wife went mad and then died, and though he married again in 1611 this proved even more unfortunate venture than before, for though to secure a better choice he took the precaution to make a preliminary selection of 11 girls whose merits and demerits he carefully analyzed in a paper which is still extant, he finally selected the wrong one, while to complete his discomfort he was expelled from his chair and narrowly escaped condemnation for heterodoxy. During this time he depended for his income on telling fortunes and casting horoscopes, for, as he says, nature, which has conferred upon every animal the means of existence, has designed astrology as an adjunct and ally to astronomy. He seems however to have no scruple in charging heavily for his services, and to the surprise of his contemporaries was found at his death to have a considerable hoard of money. He died while on a journey to try and recover for the benefit of his children some of the arrears of his stipend. In describing Galileo's work I alluded briefly to the three laws in astronomy that Kepler had discovered, and in connection with which his name will be always associated, and I have already mentioned the prominent part he took in bringing logarithms into general use on the continent. These are familiar facts, but it is not known so generally that Kepler was also a geometrician and algebraist of considerable power, and that he, Desargues, and perhaps Galileo may be considered as forming a connecting link between the mathematicians of the Renaissance and those of modern times. Kepler's work in geometry consists rather in certain general principles which he laid down and illustrated by a few cases than in any systematic exposition of the subject. In a short chapter on conics inserted in his Paralipomena, published in 1604, he lays down what has been called the principle of continuity, and gives an example of the statement that a parabola is at once the limiting case of an ellipse and of a hyperbola. He illustrates the same doctrine by reference to the foci of conics. The word focus was introduced by him, and he also explains that the parallel lines should be regarded as meeting at infinity. In his Stereometrica, which was published in 1615, he determines the volume of certain vessels and the areas of certain surfaces by means of infinitesimals instead of by the long and tedious method of exhaustions. These investigations, as well as those of 1604, arose from a dispute with a wine merchant as to the proper way of gauging the contents of a cask. This use of infinitesimals was objected to by Guldinus and other writers as inaccurate, but though the methods of Kepler are not altogether free from objection, he was substantially correct, and by applying the law of continuity to infinitesimals he prepared the way for Cavalieri's method of indivisibles and the infinitesimal calculus of Newton and Leibniz. Kepler's work on astronomy lies outside the scope of this book. I will mention only that it was founded on the observations of Tycho Brahe, whose assistant he was. His three laws of planetary motion were the result of many and laborious efforts to reduce the phenomenon of the solar system to certain simple rules. The first two were published in 1609 and stated that the planets describe ellipses around the sun being a focus, and that the line joining the sun to any planet sweeps over equal areas in equal times. The third was published in 1619 and stated that the square of the periodic times of the planets are proportional to the cubes of the major axes of their orbits. I thought to add that he attempted to explain why these motions took place by a hypothesis which is not very different from Descartes' theory of vortices. Kepler also devoted considerable time to the elucidation of theories of visions and refractions in optics. While the conception of the geometry of the Greeks were being extended by Kepler, a Frenchman, whose name until recently was almost unknown, was inventing a new method of investigating the subject, a method which is now known as projective geometry. This was the discovery of Desargues, whom I put with some hesitation at the close of this period and not among the mathematicians of modern times.
Desargues. Gerard Desargues, born at Lyon in 1593 and died in 1662, was by profession an engineer and architect, but gave some courses of gratuitous lectures in Paris from 1626 to about 1630, which made a great impression upon his contemporaries. Both Descartes and Pascal had a high opinion of his work and abilities, and both made considerable use of the theorems he had enunciated. In 1636 Desargues issued a work on perspective, but most of his researches were embodied in his Brillant Project on conics, published in 1639, a copy of which was discovered by Charles in 1845. I take the following summary of it from Charles Taylor's work on conics. Desargues commences with the statement of the doctrine of continuity as laid down by Kepler. Thus the points at the opposite ends of a straight line are regarded as coincident. Parallel lines are treated as meeting at a point at infinity, and parallel planes on a line at infinity, while a straight line may be considered as a circle whose centre is at infinity. The theory of involution of 6 points with its special cases is laid down, and the projective property of pencils in involution is established. The theory of polar lines is expounded, and its analogue in space suggested. A tangent is defined as the limiting case of a secant, and an asymptote as a tangent at infinity. Desargues shews that the lines which join 4 points in a plane determine 3 pairs of lines in involution on any transversal, and from any conic through the 4 points another pair of lines can be obtained which are in involution with any 2 of the former. He proves that the points of intersection of the diagonals and the 2 pairs of opposite sides of any quadrilateral inscribed in a conic are a conjugate triad with respect to the conic, and when one of the 3 points is infinity its polar is a diameter. But he fails to explain the case in which the quadrilateral is a parallelogram, although he had formed the conception of a straight line which was wholly at infinity. The book therefore may be fairly said to contain the fundamental theorems on involution, homology, poles and polars, and perspective. The influence exerted by the lectures of Desargues on Descartes, Pascal, and the French geometricians of the 17th century was considerable, but the subject of projective geometry soon fell into oblivion, chiefly because the analytical geometry of Descartes was so much more powerful as a method of proof or discovery. The researches of Kepler and Desargues will serve to remind us that the geometry of the Greeks was not capable of much further extension. Mathematicians were now beginning to seek new methods of investigation, and were extending the conceptions of geometry. The invention of analytical geometry and of the infinitesimal calculus temporarily diverted attention from pure geometry. But at the beginning of the present century there was a revival of interest in it, and since then it has been a favourite subject of study with many mathematicians. Mathematical knowledge at the close of the Renaissance. Thus, by the beginning of the 17th century we may say that the fundamental principles of arithmetic, algebra, theory of equations, and trigonometry had been laid down, and the outlines of the subject as we know them have been traced. It must be however remembered that there were no good elementary textbooks on these subjects, and a knowledge of them was therefore confined to those who could extract it from the ponderous treatises in which it lay buried. Though much of the modern algebraical and trigonometrical notation had been introduced, it was not familiar to mathematicians, nor was it even universally accepted, and it was not until the end of the 17th century that the language of these subjects was definitely fixed. Considering the absence of good textbooks, I am inclined rather to admire the rapidity with which it came into universal use, than to cavil at the hesitation to trust it alone which many writers shewed. If we turn to applied mathematics, we find on the other hand that the science of statics had made but little advance in the 18 centuries that had elapsed since the time of Archimedes, while the foundations of dynamics were laid by Galileo only at the close of the 16th century. In fact, as we shall see later, it was not until the time of Newton that the science of mechanics was placed on a satisfactory basis. The fundamental conceptions of mechanics are difficult, but the ignorance of the principles of the subject shewn by mathematicians of this time is greater than would have been anticipated from their knowledge of pure mathematics. With this exception we may say that the principles of analytical geometry and of the infinitesimal calculus were needed before there was likely to be much further progress. The former was employed by Descartes in 1637, the latter invented by Newton and possibly independently by Leibniz some 30 or 40 years later, and their introduction may be taken as marking the commencement of the period of modern mathematics. End of section 19. Recorded by Paul King, Oakville, Ontario. http://pjk.scripts.mit.edu/pkj